Testing. Okay. I think it's working fine.
Ah, my phone got logged out. Let me do this. It's fine. I can set it up while. It's going to take a while. Let's come in. We'll start. Okay. Okay. Sorry for the wait. I hope this is working also. Thank you for joining us in our second version of this tutorial where we talk about Ramulator and DRAM Bender and all of the research that's been enabled by these tools. Today we are going to have a full agenda, so I will not delay you more. Again, sorry about the delay. We had some technical problems. I'm Nisa. I'm a PhD student at ETH Zurich. I mostly work on computer architecture, but more so with memory system performance and robustness. And this is Ataberk. Ataberk is another organizer, and he's also a PhD student. If you want to say hi.
Oh, hi. And thanks for your patience.
Yes, and we have some other organizers. Okay, so this is the agenda, and more organizers are around the room, and all of them will be very happy to discuss their work with you. So today's agenda again is packed. We will start with a talk from Professor Onur Mutlu, and then Ataberk will talk about DRAM Bender and introduce it. And then we will have an invited speaker sharing their experience with DRAM Bender and real DRAM device characterization and their research works. Then I will continue with the Ramulator side of the tutorial, where we will talk about the first version of Ramulator and then the newer version of Ramulator 2. And then Haocong will talk about our latest changes in the Ramulator 2.1. After that, we will highlight some research works that we had done recently. And then after that, we will have more invited talks from, again, like the community, from other groups that have used these tools and their experience. And after that, we will have a hands-on session. Hopefully you'll stay for that also. We would love to go into much more in depth of these tools and explain how they are used and so on. So these are invited speakers. Again, welcome and thank you for joining us. And without delaying further, I'd like to invite Professor Mutlu here. Okay, let me.
Yeah, sure. You can use this. Is it connected? Yes,
Yeah.
you can use that.
That's okay.
After you.
You can have
Okay.
Let's stand also, see how it feels. There's better air up here. No. No, I don't. That's it. Whatever it's just go down. All good? Okay. Welcome, everyone. This is the second time we're doing this. It's good to see that people are here early on a Saturday morning. Usually Saturday morning sessions are not very well attended, so I like the fact that we have a good audience. I'm going to try to be brief because we started a bit late, but it's okay. Feel free to ask questions. I'm going to give an overview of the tools for evaluating memory and memory-centric computing, which really this workshop is all about. And memory is becoming much more important in computing systems. Like from a broader perspective, memory has always been important. But from my perspective, memory is getting the attention it really deserves today. And it should deserve much more attention. We should be much more memory-centric in our approach and thinking, because that's where data lives. And we always operate on data, right? We cannot just do things without data. So computation has been, let's say, unfairly the most important thing for a really long time. But that is going to change in the future. And these tools that we're going to discuss today are going to be the enablers to enable that change. Okay, so this is we've been holding these workshops starting with ASP+ in Pittsburgh last time. This was the first. You can find the live streams. This is also being live streamed, so you can find it online. This is today. And if you happen to be in Belfast, Northern Ireland, after the 4th of July, you're welcome to attend this, or you can attend it online also. So we'll have another version with a different set of speakers talking about tools and how to make them better, etc. I should also say that we have a synergistic workshop on virtual memory, Virtuoso, which we held with ASP+ also, and we may hold it again. This is really this is another area where we need very strong tools so that we can evaluate hardware, software, co-designs for virtual memory. And virtual memory is really clearly related to what we're going to talk about in this workshop tutorial. So let me give you a perspective. So why do we design these tools? Basically, we want to evaluate new ideas for new architectures. In this particular case, the focus is mainly on memory, right? And the question always is, how do we assess how an idea will affect the target metric X? And we have lots of target metrics today. And we want to be able to assess things before we build everything, right? So there are a variety of evaluation methods available. Theoretical proof is one that we don't resort to that much in architecture because it's very difficult to do unless you restrict the problem to something almost non-interesting, right? Analytical modeling and estimation, that's also very important, and a lot of tools do that. This is something that's very rapid, and we use this method a lot. I'm not going to talk about that. This workshop is not about analytical modeling, although there could be some discussions about this because this is also very important to get to fast speeds. So simulation is at the core, at the center of this, and there could be varying degrees of abstraction and accuracy for simulation. I'm going to talk about this also. This is a tool that we resort to in computer architecture a lot because we want to evaluate some idea that's forward-looking, but we don't know even how to build the system. So how do you evaluate it? So you simulate it, basically. This is a method that's used in many fields. It's not just in computer architecture, clearly, physics, biology, etc. And we actually have some work. One of my PhD students did some work on agent-based simulation that was applicable to neuroscience, etc. So this is a very good method of exploring the unknown, let's say. So we're going to talk about some of this, of course. Prototyping is if you have a real system that you can modify a little bit, then you can build a prototype, and that can enable you to get insights into what might happen with your new idea. And we're going to talk about that also. You could today you have FPGAs that are quite common that enable that sort of prototyping, right? But there could be other methods of prototyping also. And finally, real implementation. Build a real system. You have a new idea, just build it, right? Well, while that's possible to do, it's very expensive. And in many cases, it may not be feasible depending on the idea, right? Your idea may require some, let's say, new designs, right? And building that may take many years. So that's expensive, clearly. So today, we're going to focus on simulation and prototyping. And I'll give you a brief overview of the testing platform, DRAM Bender, that Ataberk will introduce. But I'll introduce it before him a little bit. So maybe we'll reduce the redundancy, given that we started a bit late. So this is our DRAM Bender infrastructure, a version of it, I should say. We built this originally in 2011 or so. And this is a 2022 version. And you can do it basically, you have an FPGA, and you have a soft memory controller. And you can have fine-grained control over DRAM commands, timing parameters, temperature, voltage, measure power. So you can do a lot of things with this sort of infrastructure. This is the HBM2 version that Ataberk has been working on a lot. And this is our laboratory at ETH that has 120 of these setups, and it's expanding. So, and I'm going to give you why we're expanding it, hopefully. There's another picture of it. And this recent paper that we wrote for the ICS workshop that'll appear that describes essentially at a high level how this works, what are the goals, etc. So if you have to read only one paper related to this workshop, I'd recommend reading this one, although this does talk about only the DRAM Bender aspect of it, not the Ramulator aspect. We're going to get to that later. So we built a bunch of these infrastructures to test different DRAM types like DDR3, DDR4, HBM, etc. Every one of these require a different sort of RTL, memory controller design. So it takes time to actually port this infrastructure to different FPGAs as well as different types of memory. So if people are interested in doing that, there's a lot of opportunity to do good porting and discovering new things. This is the infrastructure that we had at CMU. It was in a cage at that time. Some of you may have visited CMU and may have seen it. And this was the original infrastructure that we had in 2011, actually. You can see that it's not, this was only one at that time. Okay, we open sourced these infrastructures. Initially, it was open source as SoftMC, soft memory controller. It was a bit harder to use, but it was still much better than, well, such an infrastructure was not available, basically, to the public when we open sourced it. And this is the paper that we wrote in HPCA 2017. More recently, we've introduced the DRAM Bender version of it, which is essentially a DDR4 and HBM version. And you can read the paper that Ataberk wrote. Now, let me give you an idea of what this sort of infrastructure enables. So how many people here have heard about Rowhammer? Probably quite a few, maybe not everyone. Okay. So this is essentially, I'll go through some of these very quickly. But we did a lot of Rowhammer research on this infrastructure. That was not the reason why we actually built this infrastructure. Our goal was to really understand the technology scaling issues that are happening in DRAM by testing DRAM rigorously. And when we built the infrastructure, our belief was that the biggest technology scaling issue in DRAM was retention time, refresh. Whenever you reduce the size of a DRAM cell, it becomes more leaky. And you need to determine how long a cell can retain its data so that you can figure out how often you need to refresh DRAM. The problem is, if you cannot determine how long a cell will retain data accurately, you may set a refresh rate that's overly conservative or overly aggressive. Basically, you may actually either get bit flips or you may have a performance energy overhead. So our goal was to actually figure out how to do the refresh appropriately. And we did actually a lot of work. Our first paper on this was on refresh. But then we said, oh, what about other issues in scaling? And Rowhammer was one of the things that we have looked at in read disturbance. Basically, the Rowhammer is the fact that you can induce bit flips in any DRAM chip that you can buy today at the device level. If you keep activating a row repeatedly, open, close, open, close, open, close, open, close, these activations cause perturbation or interference to data stored in adjacent rows. And you may actually lose the data because you've actually interfered or you actually depleted the charge in some of the vulnerable cells. I will not go into this in detail that much. There may be some talks today. I don't know. But tomorrow we'll have a DRAM security workshop that talks about Rowhammer quite a bit. There are actually a lot of Rowhammer papers. I'll give a keynote in that workshop. So if you're interested, if you're still not bored of hearing me, I'll talk about Rowhammer in that workshop a lot. Okay. So we wanted to study the technology scaling impact of this. And over the years, we did a lot of studies using the DRAM Bender infrastructure. And as cells become smaller and close to each other, the vulnerability to Rowhammer and similar read disturbance issues becomes much worse. And you can study all of these things with this infrastructure. You'll see some of these talks. You can see that the number of activations to induce a bit flip has reduced by more than 100x in the course of only 10 years. The question is, how do you design DRAM if you're faced with such difficulties, right? Okay, this is our original Rowhammer paper that used our infrastructure, and a lot of work built on this, on security as well as some other domains, but security folks took Rowhammer a lot, and basically they built real attacks that took these bit flips that you can induce quite reliably and consistently, and figure out how to take over a system, read data that you don't have access to, break out of virtual machine sandboxes, or corrupt some important data like ML model weights that are important for your inference workload. As a result, your ML inference may be useless. So this becomes a safety problem as well, under conditions where you're using DRAM for inference, for example, in the field. Or you can steal secret data like cryptographic keys and ML model parameters. So this sort of infrastructure can enable research in other domains also, as you can see. And in fact, some security folks are using this sort of infrastructure and publishing this sort of things in security conferences like ACM, CCS, etc. Okay, so that's not the only issue. There are more issues. This is a work that we published at ISCA. Haocong is the first author. And there are other read disturbance problems in DRAM, basically. One of them is row press. And row press is very different from Rowhammer, it turns out. Instead of activating a row, opening and closing it repeatedly, as frequently as possible as allowed by the standards, you keep the row open for a longer time and activate it less. It turns out this induces a lot more disturbance, a different kind of read disturbance. And this enables you to activate rows much fewer times before you induce a bit flip. which means that the attacks or the solutions that you designed for rowhammer, which we didn't talk about, may not work if they assume some sort of activation count. And most solutions assume some sort of activation count. So discovering new things like this enables the attacker to be strong, but it also enables the defender to defend. And publishing this actually helps everyone in the end, I think, because if an attacker knows and doesn't publish it, as a defender, you're in trouble, right? It's good to know, think about these things. We're going to talk about these things at DRAMsec tomorrow, actually, DRAM security. Okay, row press amplifies read disturbance in DRAM quite a bit, and we've shown that in some cases, fascinatingly. I think one of the things that I should tell you that when we built this infrastructure, we didn't envision any of this, right? We're talking about 2011 when we built the infrastructure, and I keep getting fascinated by some of the results that we find today. Like one of the results is you activate a DRAM row once, keep it open for 30 milliseconds, and you get bit flips in adjacent rows. This is fascinating to me. I mean, there are reasons for it, of course, and people have published device level works after we published our paper. So it's good to discover these things. This also requires, or this also enables us to think what kind of memory controllers or systems should we design to avoid such issues, right? These days, there's huge talks about space data centers, right? Going to space, which is good. We should be doing all of that. Robotics. If you actually put DRAM, cutting edge technology, into space, is it going to work as it is? How do you make it work? Or do you keep putting DDR1 or SDR into space as we do today and get low performance and low capacity, right? That's basically, these are good questions to think about. And I think in space or on this Earth, we need intelligent controllers to solve these problems. And we have actually written a lot of papers on this topic. This is one of our papers before rowhammer. And this is a more recent version that we wrote with Ataberk and Ismail, who are sitting over here. And the good news is, if you show data persistently, and again, enabled by these infrastructures, industry may not want to listen initially, but eventually they do listen because they have to solve this problem. This is real data coming out of real DRAM chips. There are real problems here. And this is the first paper that a major DRAM manufacturers wrote, SK Hynix, in a major circuits conference that acknowledged the rowhammer problem. And they basically said, we solve it using some methods that build on several things that we have proposed in the past. But one of the things that they have introduced is something that is expensive, I would say. It's a solution that actually we kind of dismissed in our original ISCA paper, saying that this is an expensive solution. And the idea is to modify the DRAM chip. Inside the DRAM chip, you have an activation counter per each row. And whenever you activate a row, you increment the counter. There's some control logic. Essentially, there's some intelligence. There's some computation capability inside the DRAM chip to track how many activations you get for each row. And if the number of activations is greater than some threshold, that should be very, very carefully determined, depending on what conditions you're operating on, then the DRAM chip takes some mitigating action. Mitigating action may be refreshing adjacent rows, for example, or something else. They don't talk a whole lot about exactly what they do. But the key is, this is a step in the right direction, which is memory chip incorporating something intelligent to fix an important problem. If you went to the DRAM manufacturers 10 years ago and tell them, I want some computation capability inside your DRAM for this, they would kick you out of the room. Maybe they would be a little bit more polite, you know. they would wine and dine you, but they would not take your solution. But today, they are the ones actually that are adopting the solution. Okay, so this was standardized in JEDEC, and I think some version of it will be in all DRAM chips going into the future. The question we should always ask as researchers is, are solutions good? Right? This is a solution to a problem, probably not a good solution to the problem it intends to solve. So how do you actually evaluate solutions, whether or not they're good? Now you resort to simulation, because these things don't exist yet. And none of us here, I think, unless someone is a DRAM manufacturer over here, can build DRAM chips. So what we do is basically we need to simulate these solutions. That's where actually simulation of these systems in an accurate way comes in. And this is our Ramulator simulator that we released originally in 2015. I can tell you a lot of stories about it also. We were working on memory, like DRAM, for a really long time. When I was at Microsoft Research, the first thing we did was really looking at memory controller designs. And I started the simulator. It was not called Ramulator at that time. It was written in C#. Microsoft, C#. It's a good language. I'm not taking sides. I think it has good characteristics. But we wrote it in C#, and eventually my students at CMU inherited it and made it much, much better than what we did. And we decided to open source it in C++. Although we always had a version of C# in our group, there was this discrepancy to outside and inside. But eventually we killed the C# version, and we have the Ramulator 2 and Ramulator 2.1 used in the group today. Okay, but that's how you can evaluate these ideas that are proposed, or you can propose new ideas. This is what we're going to talk about later on. And this is the Ramulator 2.1, which we've also already released, actually, which I'd recommend everyone to use as opposed to the other ones. Okay, so we evaluated industries solutions. This is called per row activation counter that I mentioned in SK Hynix and also DRAM standards. And we found out that these are not good in terms of performance, basically. And we propose solutions to it. I'm not going to talk about it. Cronus is one solution that I think is actually quite nice, that takes advantage of the parallelism and sub-area level parallelism inside DRAM. But there could be other solutions. How do you evaluate them? Essentially, using simulation infrastructures. Okay, so we should always ask the right question, I think. Can we do better? And again, if you ask this question, then you're really stretching the limits, and you need better and better simulation infrastructures. This is an idea that I like. We published this at Micro in 2024. The idea of self-managing DRAM. I will talk about it very quickly, but basically, you have a memory controller and you have a DRAM chip. Today, if you want to do something big in the DRAM chip, some optimization, for example, you need to change the memory controller and you need to change the interface to the DRAM chip. This makes it very difficult to adopt innovative ideas in DRAM because no one agrees to change all of these at the same time. The question is, can we actually enable innovation in a much better way without requiring some changes to happen to the memory controller and the interface? And the idea is basically, if you need to change the interface a little bit so that it can be flexible. Today, the interface is such that memory controller tells the DRAM chip to do some things, and DRAM chip cannot do anything on its own. That's very sad, I think. For example, my phone over here right now, or this laptop is refreshing itself in memory, but the memory itself is not refreshing itself. What's happening is that a memory controller on the CPU side is telling memory, refresh yourself, refresh yourself, refresh yourself, refresh yourself, refresh yourself every 7.8 microseconds. That sounds terrible, right? We are autonomous agents as human beings, right? We don't want to have someone asking us, take a shower or wash your face, right? It's basically the same analogy, I think. So basically, I think we need to enable DRAM chip to become autonomous. And the idea over here is to enable the DRAM chip to be able to say no to the memory controller. If you want to keep the existing interface as much as possible, at least give some breathing room to the DRAM chip such that the DRAM chip, if it wants to do something internally, it can do something internally. And if it's busy doing something internally when the memory controller is trying to access that part that the DRAM chip is busy with, the DRAM chip should be able to say no to the memory controller. No, memory controller, I am as important as you. So try again, sorry. And if you do this, it's very little cost, and it enables a lot of optimizations without requiring the interface and memory controller changes. The memory controller needs to change once to ensure that it can deal with the negative acknowledgements, of course, but it doesn't require changes afterwards. Okay, so we've shown that in this paper, you can actually optimize DRAM refresh, retention times, row hammer protection, memory scrubbing mechanisms. And if you're interested, you can watch Hassan's talk, or Ataberk can tell you more about self-managing DRAM a lot. They're co-first authors in this paper. Okay, so why am I telling you all of this? Because I think this sort of ideas are really, really important to examine today, especially. Today, we're building systems, but I think our systems are very broken because they're extremely processor-centric. And you can see that the memory cannot do anything by itself. If you have an interface like that, memory can do operations also more easily. We're going to talk about memory, in-memory computation. So I think we need to change the interface, but this sort of ideas are almost impossible to examine without simulation, basically. That's why we have these simulators that are out there, and all of these papers have open source code building on Ramulator that you can use and build on. If you want more stories, I have a keynote talk at Micro that talks about some of these things, and it's online, so you can take a look at it. Okay, so the question is, what else can we do here? I think it's good to, since you're attending this workshop, maybe you have an interest in doing something better. And I would like to talk about what is possible to do. I think there's still a whole lot we don't know about DRAM, for example. DRAM is a technology that's been around for 60 years or so. And I'm fascinated that we're discovering things that no one has documented or even discovered today. Granted, technology has scaled to very small node sizes. So it's a different kind of DRAM than 1960s DRAM, what Denard built. But still, it's the same technology with the same fundamental principles in the end. So for example, I think I'll give you some thoughts over here. Aging is something that worries me. If you take this DRAM chip, put it to the space or anywhere where it will age, how does its characteristics change? This is something that bothers me a lot. Yet we have some evidence that rowhammer becomes worse with aging, but there needs to be more in this area. Spatial variation is something that we have analyzed. That's part of the aging studies that we have done. There are also some other things that we have discovered very recently. These are all from 2025, 2026. One is variable read disturbance. This is Ataberk's paper. You can talk to him about it. But the idea is there's some unpredictable characteristics, random characteristics, in which the number of activations to induce a bit flip changes in an unpredictable way. So when you test DRAM right now, you may get a number of activations that's like 1,000. When you test DRAM 10 days later, you may get number of activations to induce a bit flip 10. So you need to keep testing DRAM while it's in operation as much as possible so that you can accurately identify the read disturbance threshold that you need to protect for. This is a very dangerous thing, I think. That's why we need even more intelligent controllers. So that was published at HPCA 2025. This is another work Ismail led, which is column disturb. We talked about rowhammer. A single row activation can actually flip bits across 3 DRAM subarrays because you disturb all of the columns when you actually activate one row. We may talk about that. Tomorrow, we're going to definitely talk about that at DRAM Sec. And when you do processing operations inside DRAM, this hammering becomes much worse. Again, I'm not going to talk about these, but these are all recent discoveries that have been enabled by the DRAM Bender infrastructure. And there's more. Since you're at ISCA, I will not go into this detail. There are 2 papers that we're publishing over here. In one of them, which we call PUD Ghost, the idea is that data in non-activated rows. So you're operating on some rows, but some rows you don't activate, and you want to do computation on the rows that you activate. Unfortunately, the computation that you do on the rows that you activate get affected and sometimes get corrupted by the rows that you do not activate. So if you're building or if you're trying to build new systems that can do processing using memory, processing in memory, you need to be very careful about what you do. And then there's probably the thing that surprised me the most, which is deja vu that Haocong is going to present at ISCA. And here we show that data previously written to a row affects the row's read disturbance vulnerability. And it can make the read disturbance vulnerability better or worse. The problem is you need to be very careful about how do you test DRAM and how do you figure out the vulnerability to read disturbance. This also affects processing using DRAM operations. So if you're interested, come to Haocong's talk, or you can read the paper online. OK, so there's also more to think about over here. I think emerging memories also are important. We have not adapted DRAM Bender to emerging memories, but if there are people who are interested in doing that, it'd be good, and we can try to help. The downside over here is there are not that many emerging memory technologies that are easily adaptable to an FPGA-based infrastructure, but we're happy to talk over here. But we've done simulation-based work in emerging memories for many years. And in the end, you need intelligent controllers to manage these memories also. This is one of the early works that we did in ISCA 2009. And the idea over here is if you replace phase change memory, if you replace DRAM with phase change memory, you have some characteristics that you need to deal with. And one of the characteristics is whenever you write to a phase change memory cell, it wears out. And you'll need to have an intelligent controller to manage wear leveling and wear out, just like we do in flash memory. OK, that's why we keep building this infrastructure so that we can figure out more. I'm giving you a lot of references here, but this is Giray, who recently graduated from my group. He wrote a thesis that covers a lot of things done in DRAM Bender. He built, for example, voltage measurement infrastructure to measure the effect of word line voltage on the vulnerability to read disturbance. I think it's very important also going into the future. These infrastructures should deal with voltage in a better way. But if you're interested, he has both. This is a thesis that combines DRAM Bender and Ramulator in a really nice way. Okay, let me quickly go over existing DRAM chips. These are some of the other results that I didn't talk about. I was focused more on read disturbance, but we've also, using our infrastructure, found out that existing DRAM chips can do operations. This is a summary. For example, these are DRAM chips that you haven't modified at all. You just modify, use DRAM Bender type, essentially DRAM Bender, and violate the timing parameters to DRAM chips. For example, we've shown that you can copy one row up into up to 31 other rows with almost perfect reliability. You can perform NOT operation and NAND, OR, and NOR operation. So if you can actually perform NAND, for example, NOR, then you have a functionally complete system. You can build a processor out of DRAM. I think that's fascinating. And this is existing DRAM chips. We're not talking about changing DRAM. We're just talking about abusing DRAM such that you violate the timing parameters. I'll give you the key ideas relatively quickly. These were published in 2 papers, functionally complete DRAM and simultaneous many row activation. And the PUD Ghost paper, as well as Deja Vu papers that are going to appear at ISCA, actually build on both of these. So in DRAM multiple row copy, very quickly, you can actually copy one row to another row in DRAM. This is based on a paper that we published in 2013. You activate the source row, which brings the data into the sense amplifiers, and then you activate the destination row, and the data gets copied to the destination row. So you can do this in from not one. You can do this in real DRAM chips by violating the activate to activate timing parameter carefully. Yeah. Okay, I'm going to skip the NOT operation because we don't have a lot of time. Let's talk about how you can do NAND or NOR. So this is what a DRAM chip looks like: 2 subarrays, A and B over here, in one subarray, X and Y in another subarray. Let's assume that if you could concurrently activate all these 4 rows, multiple row activation. In theory, what you would get is the sense amplifier in the middle comparing the average voltage of A and B to the average voltage of X and Y. And if the average voltage of A and B is greater, then you would get a VDD on top and 0 at the bottom, otherwise vice versa. Right. So this is circuit theory. And we have shown in real DRAM chips that if you carefully violate, activate, precharge, activate timing parameters, you can activate 4 rows at once, or some more also. And we can get these functions. The question is, what kind of functions do you get? For example, you need if you set the reference subarray values to VDD and VDD over 2, and you can do both of those reliably in DRAM. There's a nice paper at Micro 2022 called FRAC DRAM. The values that you compute, the result that you compute on X and Y is essentially an AND function, because the average voltage over here will be greater than the average voltage over here, 3 VDD over 4, only if and only if X and Y are both VDD, which is 1. Right? And that's essentially an AND function in the compute subarray. You're really computing the AND over here. And by definition, because it's an inverter over here, you're computing the NAND over here. So you get AND and NAND by carefully placing data values in the reference subarray. So this is actually a computational substrate that you can build relatively reliably. There have been works that have, for example, ported machine learning inference on top of this. Of course, you need to have low bit widths to begin with. How do you scale to high bit widths becomes interesting. Okay. I think I'll leave the NOR as an exercise for everyone, but not that hard. Okay, so this is enabled by the DRAM testing infrastructure that we built. And you can see that this is how robust multi-row copy is, almost 100%. And I think we have ways of making it 100% right now. Ismail has ways. If we can convince the reviewers, he can publish it. That's another thing that we can talk about, but I don't have time to talk about right now. And or NAND and NOR are less reliable, but quite reasonably reliable or surprisingly reliable, given that DRAM chips are not designed for this purpose, right? Nobody advertised DRAM to actually do these operations. We are abusing the DRAM chips. And even memory companies came to us saying that, oh, you discovered some things that we didn't really think about in our DRAM chips. So it's good to have this sort of interest from a wide spectrum of, let's say, industry. Okay. So there's more that I don't talk about, but you can talk to people who've done this work, and also there will be some talks. How much time do we have? Minus 20 minutes. Wow. Okay. We started minus 10 though. Okay. I'll go through these relatively quickly. This is a prototype that Ataberk built, PyDRAM. Essentially, it's an end-to-end prototype to perform row clone and true random number generation in DRAM chips. You can actually look at the effect of these operations and done in DRAM chips on a real application. And you can see real results. So this sort of prototype is really important to build, I think, and we're building better prototypes going into the future. Now I get to simulation. But since I have minus 20 minutes, I'm going to speed up quite a bit. Maybe we can eat into the break a little bit, you know, if people are okay with it, or we can adjust. Okay, I like the simulation. I give this lecture. Maybe I should just point you to my lecture online so that we save time. But this is an area that has been going on for a while. Essentially, an architect, if you're an architect, you need to dream, right? You need to create the future. If you talk only about the past, that's a very boring world. Right? And simulation is really a key tool that we have. It really allows the evaluation and understanding of non-existing systems. It enables many things, the exploration of many dreams concurrently, a reality check of the dreams if you're careful about what you're doing, deciding which dream is better. That's good. It also enables the ability to fool yourself with false dreams or wrong ways of doing things. So you need to really know what you're doing with your simulator. You need to understand. And this I cannot emphasize enough, because some people think they can use the simulator off the bat and not make mistakes. Simulator will automatically figure out what kind of mistakes I make. That's a false dream. That cannot happen. This has happened in the past in architecture, where people who do not understand simulators generated garbage results. So if you're building simulation, you need to understand it. And people who are actually doing physics simulation, et cetera, they do actually understand. They do try to figure out what they're doing, right? And we should be doing that in our community also. Okay, so there are trade-offs in simulation. There are 3 metrics to evaluate a simulator: speed, flexibility, accuracy. There are 2 other metrics that I'll introduce later on, but essentially, you cannot get all of them. That's a bit unfortunate. This is one of those cases where you get 2 out of 3. If you happen to get 3 out of 3, let me know. And speed is how fast the simulator runs. Flexibility is how quickly can you make modifications so that you can evaluate different things. Accuracy is how accurate is the performance energy numbers the simulator generates versus a real design. And you need to be careful what is a real design here, because if you're evaluating the future, you don't have a real design, right? You may calibrate your simulation to a real design today. That doesn't mean that it's calibrated for something 10 years down the road. So that's why I think we need to be very careful. If you calibrate it for today, does it? Okay, that means something, sure. But what does it mean about the future? Maybe it means nothing. Okay. So the relative importance of these metrics varies, depends on where you're in the design process and what your goal is, clearly. So you can trade off these things clearly. Speed and flexibility affect how quickly you can make design decisions. Trade-offs. Accuracy affects how good your design decisions might end up being. And how fast you can also build your simulator. So there's another metric here, simulator design time, that I introduced. Flexibility also affects how much human effort you need to spend modifying the simulator. And you can, again, trade off between these 3 metrics to achieve design exploration and decision goals. So I think making the best of architecture as an architect, this is what I tell my students also, you should be comfortable at all levels of refinement, basically, including the extremes. And knowing when to use what type of simulation for prototyping or analytical modeling is really important. And in the end, we have a variety of evaluation methods available, right? At some point, you go and implement a real chip, but the question is when, right? It's good to think about that too. Okay, I think this is what I should have done. You can listen to more of this in my simulation lecture. There's more trade-offs that we cover, etc. So we're going to talk about Ramulator here. I gave you a story of it, so I'll go through this relatively quickly. We believe that actually memory is really important, and we need to have a simulator for it. And we were not satisfied with the existing simulators because they were not flexible enough at the time. And we introduced Ramulator because we believe that the landscape was going to change, and you needed a simulator that's good at exploring many different standards, new and upcoming, and also academic designs, and it should be fast and easy to extend. That were the goals of Ramulator, and this is from the original Ramulator paper. You can see that there are a lot of standards over here. And we open sourced this. At the time, it was faster than the prior simulators. It was modular and extensible. And you could do studies like this that were not possible with any other simulator at that time. And the idea is, for example, you could look at different memory interfaces, memory chips, and you could run workloads that you're interested in, and you could see how these different memory designs would give you performance. And you could couple this with DRAM power or some sort of power measurement infrastructure such that you can get power numbers also. So here you can see, for example, we're running 22 spec workloads and comparing the performance of DDR4 over DDR3. You get some performance with DDR4, but HBM at the time, we were talking about 2015, is much, much better, you can see, right? Because there are some workloads that do very nice streaming. LPDDR is a little bit worse in terms of performance, but not too bad, basically. So you can do this sort of studies that's very interesting, I think. And that was the reason we actually wanted to open source it, to enable the community to actually do this kind of studies and extend it, right? Okay, I'm going to skip these. Basically, you can integrate it with many other simulators, but and you can also do interesting studies like, again, what workload works better with what kind of DRAM type. And this is a paper that we published at Sigmetrics that I will not go into. And you can propose new Rowhammer solutions. Blockhammer is one of them over here. Okay, we have a project course on Ramulator if you're interested, but this is the old version of Ramulator. We should probably do another course, but that's the purpose of this workshop and tutorial, actually. Ramulator 2.0, which we introduced recently, Haocong drove the design of it, is much better. It's much easier to use. When we introduced Ramulator, industry picked it up a lot. Some major companies actually have teams that are using Ramulator, and they gave us a lot of feedback. One of the things that they didn't like was how hard it was to modify, etc. I think Ramulator 2.0 fixes it in a nice way. I'm not going to go through this because there will be talks about this. And you can do things like this. Cronus, for example, was evaluated using Ramulator 2.0. But I think Ramulator 2.1, which Haocong will talk about, is probably the one to use going into the future. And we encourage the community to help us make this better, because memory is going to be important. And we want more and more that could be done as a whole research community so that we can explore other ideas that are not easy to explore. Okay, there's more to come, basically. I'm going to skip a lot of these. These are some of the works that are here for some reason. I'll just put a pitch for DRAMsec tomorrow, which has a bunch of papers on Rowhammer. A lot of them are evaluated using Ramulator and some sort of simulator. So it's going to be interesting. Actually, one of them is actually using DRAM Bender also, if you're interested in looking at. And ISCA is actually, I think, a bunch of papers on read disturbance also. I didn't count the memory-centric things. Okay, I'm not going to talk about this, but Ramulator has been extended for processing in memory. This is something that we want to do for Ramulator 2.1 also. So if people are interested in extending things for PIM, we are happy to get help. We have a bunch of papers for the old Ramulator. And if you want to learn more about this, tomorrow, Ismail is leading another workshop on memory-centric computing systems. This is the right one over here. And if you missed that one, there's another one that's coming up at ICS. Okay. I will also put a pitch for Virtuoso here, because I think some of the things that we have done with Ramulator is a very, let's say, memory controller and DRAM-centric simulator. It doesn't do virtual memory translation, for example, right? It can hook up with CPU models, it has a very basic CPU model that you should use carefully. You should understand the upsides and downsides of that CPU model, but you can integrate it with any other CPU model you like, right? You can integrate it with ChampSim, you can integrate it with Sniper, etc., with some levels of difficulty, ZSIM, Gem5, and we have integrated with it. So Virtuoso fills a gap in virtual memory research, and there are also other simulators that I skip over here. Virtuoso fills a gap, and it enables really virtual memory research. I guess before I go into Virtuoso, there's also MQSIM that we do in SSDs, but if you're interested, you can talk to Rakesh about it. Okay, Virtuoso. Essentially, the idea here is if you want to actually simulate both hardware and software together, it's an even more challenging task than what we have been talking about with simulating memory, right? Because you need to simulate the hardware side modifications that you do. You need to simulate the software side modifications you can do. And your simulator becomes extremely slow And people have attempted designing simulators that are full system, they're extremely slow. They may be more accurate. Again, accuracy is something that you need to be very careful about. In existing systems, they may be very accurate, but in future systems, you don't exactly know. And then people have designed also emulation-based simulators that are fast, but not necessarily very accurate. Right? Our goal was to actually get to that place. And with some trade-offs, we achieved that place, and you can read the paper about it. And essentially, it's a new simulation framework that provides fast and accurate prototyping and evaluation of software and hardware components. It actually provides a lot of tools, a lot of different mechanisms that people have proposed in the community. So if you're interested, you can take a look at it. You can add your new things. Our goal with Virtuoso is to really make it something that a lot of virtual memory research can compare a lot of different ideas in, right? And if you're interested in virtual memory, this is an area that I would recommend. And the good news is Virtuoso is already integrated with the Ramulator, MQSIM, and a bunch of other simulators that are widely used in the community, processor simulators also. So it can actually have an ecosystem that spans across the stack. It's not there yet fully, but it is possible. Okay, I'll let you read the Virtuoso paper and talk to Konstantinos if he's here later on. He's the one who developed this. Okay, I have the something wrong over here. I'm done. I'm happy to take any questions. I took more time than expected, but hopefully this was a good introduction. Any thoughts, questions, comments? No? People are still waking up? Normally I hammer people with row hammer talk, but this was not a row hammer talk. Anyway, okay, let's start with the next talk then.
Okay. So I'll continue with some, let's say, more detailed introduction of DRAM Bender and what DRAM Bender is and what you can do with it. Onur already covered many of the things I had liked to cover for this presentation, but I'm hoping I can get you more interested in DRAM Bender so that you stick till the end of this workshop and participate in the hands-on session that I think many people have prepared for and worked very hard for. But this is going to be about DRAM Bender. So as Onur already mentioned, there are many things, many factors that affect DRAM reliability and latency and performance in general. And we want to be able to evaluate the effects of these in real systems. And for that purpose, we need to perform experimental studies of real DRAM chips. And there are DRAM testing infrastructure that allows us to do these sort of studies. The open source ones, particularly the FPGA-based open source infrastructures, are good in the sense that they're publicly available, so we can start using them today. And they're relatively low cost because you just need an FPGA board and a bunch of DRAM modules to get started with your experiments. But there were limitations with these existing infrastructures that we identified in our journal publication we wrote about DRAM Bender. So they imposed some restrictions on the DRAM interfaces they were supporting that would limit you from conducting all types of experiments you would want to conduct. And they were difficult to set up. Some of them were based on discontinued hardware software stacks. It would be very hard for you to get started with these infrastructures. Or they would, one thing I didn't mention here is an important barrier for entry is if you need hardware design expertise or something like Verilog design expertise to get into working with these setups, that's something we wanted to avoid. And yeah, some of them are monolithic in the sense that you cannot really easily extend these infrastructures to support new DRAM types. So for DRAM Bender, we had 3 key design goals: flexibility. So we wanted people to be able to design or test any DRAM operation with any combination of delays between your DRAM commands. We wanted it to be easy to use, as I mentioned in the earlier slide, and we wanted it to be very extensible. So if you wanted to support, let's say, or add support for a new FPGA board, we wanted to enable you to do that very fast. And we developed DRAM Bender. It was I think it is the first publicly available FPGA-based DDR4, 3, and HBM2 characterization infrastructure. This is one of the pictures that you've seen earlier. This is a DDR4 tester setup that we have with a temperature controller and a voltage controller as well. And this is easily programmable using the C++ and Python APIs. So we're going to be talking about the Python API more today towards the end of the workshop. It comes with 6 different FPGA-based prototypes out of the box. So if you go to our open source GitHub repository, which I will link to in the later slides, you can already get started working on one of these boards and do rowhammer or other sort of DRAM Bender experiments. And we have some new support for new features coming up soon. So the first one is we're going to add support for the U55C HBM2 board. This basically what's special about this board is it enables you to do power measurement studies in high bandwidth memory. And we also have a power measurement and voltage control setup via this custom riser board coming for the DDR4 testing setup as well. So we will test them internally and then release them as we validate all these, the functionality of these new exciting features. Onur already showed you a bunch of pictures. So this is the laboratory we have with 120 plus, that's what he quoted, the number he quoted, plus setups. And we're expanding, and it's very good to see that it's getting bigger and enabling more research. This is the paper that we wrote. Anyways, Onur talked about these things, but this paper talks about what we're going to introduce in more detail in the upcoming days or weeks, to be more realistic about the timeline. And yeah, I refer you to this paper if you want to learn, read one paper about DRAM Bender. I think this one is the good paper, the right paper to read. There's also people that are doing a lot of work in our laboratory that I'd like to acknowledge here. So there's Konstantinos, Ismail, and Umut. And there are many faces here I'd like to highlight. Haocong, Jikun, Spiros, and Orhun were helping a lot with the workshop organization and also doing a lot of DRAM Bender experiments and research using DRAM Bender. So I'll talk a bit more about DRAM Bender's ease of use. And I'll show you one example of a rowhammer program that you can write using only 12 lines of C code, basically. This is using the C++ API. What this code is doing here is basically adding a bunch of instructions to a list. So you're creating a program that will repeatedly activate, in this case, 2 aggressor rows surrounding a victim row. And we will learn more about this towards the end of the slide. So you don't need to understand what any of this means. But DRAM Bender, as you can see, is a programmable core that is easy to program. And therefore, it enables you to do or design new experiments without going through the trouble of creating new hardware for each type of experiment. In the original paper we released about DRAM Bender, we showcased this ease of use and flexibility using 3 case studies. I'll refer you to that paper for more details on this. And there are even more details in that paper. And this is a link to it. We will publish all of these slides as part of the workshop, so it's fine if you missed this. And I'd like to mention there's like a lot of research that DRAM Bender enabled, and these are the publications those works led to. This list grows, and I am very proud to see what or where DRAM Bender ended up. And this is like a lot of research papers that I'd like to just quickly flash. These are all the links that you can, references basically, that take you to various DRAM Bender sources, either tutorials or videos and the source code of it. And to summarize, this is the first publicly available DDR4 and 3 and now HBM2 characterization infrastructure. and we think it's very easy to use. And I hope you get to experience that today. And it enables many studies, ideas, and methodologies in the design of future memory systems, and I hope it will continue to do so. Now, that was the overview. I'll continue with a few research highlights. I'll go into details of one of the few works that Onur mentioned in the earlier presentation, after I give you a brief overview of what DRAM Bender can be used for. So this is, or what it's already used for. DRAM Bender is widely used for 3 types of major, let's say, characterization studies. The first one is understanding DRAM robustness problems. The second one, we classify it as uncovering new DRAM functionality. This is the fancy processing using memory operations that you've seen in the earlier slide. And to learn DRAM internals. So these are very interesting studies, and we're going to have one of the authors of one of these works as an invited speaker today, Professor Jungo An. It's very interesting because these infrastructure also allows you to gain insight into, maybe I'll use the word trade secrets of DRAM manufacturers, but hopefully that will become more clear as I present you the slides. So for understanding DRAM robustness problems, this is my collection of work or research papers that fall under this category. And I'm going to highlight a bunch of these. I'm going to talk about them in a little bit more detail. For uncovering new DRAM functionality and for learning proprietary DRAM details. There are also other, I think, noteworthy use cases for infrastructures like these. That is to understand DRAM voltage and latency sensitivity, or exactly, so how DRAM operation latencies affect your robustness and how voltage affects your robustness of your DRAM. DRAM power characterization and parts of DRAM Bender, the hardware design, can be used in developing new FPGA-based infrastructure for other purposes. So I'll give you a better idea of how you can use DRAM Bender to understand robustness problems. And I'll highlight variable read disturbance. This was published in HPCA last year. So I'll give you some background first. And this is a typical computing system with a CPU and a DRAM module. We have many chips on a module. And inside the chip, we have many DRAM banks, subarrays inside each bank. And the cells are laid out onto a 2-dimensional array of rows or word lines and columns or bit lines. And we have this row buffer here where data needs to basically be copied to before you're able to access it. And you've already seen read disturbance or row hammer. So I'm not going to talk about this, but if you repeatedly activate a DRAM row, you will induce bit flips in neighboring rows. And there's also row press. By keeping that aggressor row open, instead of repeatedly activating many times, you can induce these bit flips as well. Now let's look at how DRAM charge leakage or DRAM cells store data to understand how DRAM read disturbance breaks some robustness characteristics of our DRAM chips. So each cell will encode data in fundamentally leaky capacitors. This is showing you a diagram of a DRAM cell with an access transistor that gates access to this data. And the word line and the bit line in the previous picture, we've seen these two structures. There are many paths by which the charge can leak from. And if too much charge leaks, or this is the abstraction level we will use to understand DRAM read disturbance effects, if too much charge leaks, we can consider the stored data to become corrupted. Now, to avoid that, we need to periodically refresh our DRAM cells. So this is showing you the capacitor voltage over the y-axis and time over the x-axis. We see that the capacitor voltage decays over time. And to keep it above this threshold, under which we can no longer reliably read the data from the cell, we need to refresh the cell periodically. And this period is typically referred to as the refresh window. If a row hammer attack is ongoing, or if a neighboring row is being repeatedly activated, this will cause the cell's charge to go below Vmin before the refresh window ends. So that's one way to think about how redisturbance leads to bit flips in DRAM chips. So if you refresh the cell at this point in time, you will see the incorrect value, and you will restore that incorrect value back to the cell. There are many ways to prevent these bit flips from happening. And they each come with a different, let's say, point, and they each end up and land you in a different point in the area, performance, energy, security, even trade-off space. But many of these defenses have a key property, which is they take a preventive action before a bit flip manifests in a victim row. And they must accurately quantify the amount of redisturbance a row can withstand before a bit flip manifests in that row to be able to do this correctly. And this is typically done by basically testing, because the manufacturers will not release or will not tell you how many activations, let's say, you can perform to an aggressor row before a bit flip manifests in a victim row. You won't get this data, so you can only learn this via experimental characterization. And this metric we use to quantify let's say the amount of redisturbance a row can receive is called the redisturbance threshold, and it can be thought of as the number of aggressor row activations you need to induce the first bit flip. Now I'll talk about why it's important to accurately identify that redisturbance threshold value. So on the x-axis here, we see the configured redisturbance threshold for the mitigation technique. So as we go high up, we have a larger value that we configured for. So that roughly means that our mitigation technique will take preventive actions less frequently if we have, let's say, an ongoing row hammer attack. And if we're to the left side on this x-axis, that means we're repeatedly doing these preventive refresh operations, and we're inducing a lot of overhead. And on the y-axis, we see the performance and energy overhead. And again, these are not for scale. This is like a toy example. So you would expect to see a curve like this. If, let's say, your ground truth redisturbance threshold value, that is the real value exhibited by your victim cells, is 1000, and you have configured your defenses with a value that's much higher than that, you're basically created an insecure system. This will get you low overhead, but you will also get bit flips. You don't want this. And if you set it to a much smaller value than the ground truth value, you have underestimated the redisturbance threshold. You won't get bit flips, so it's going to be secure, but you're going to end up with a lot of overhead from all those preventive mitigative actions. That's what I was saying earlier in this slide. So given that we want to identify this ground truth value, the question is, can we do that? Prior works assume that the ground truth redisturbance threshold value can be identified, but we want to understand if that can be done. So does redisturbance threshold change over time, and how reliably and efficiently can we measure it? And we want to analyze the implications of the answers to these questions for redisturbance solutions. And for that, we use DRAM Bender, and we test many chips, 160 DDR4 and 4 HBM2 chips from back then, all three major manufacturers. And the key takeaway that I'll like to leave you with is that the redisturbance threshold of a DRAM row will change randomly and unpredictably over time. And that makes the accurate identification of the redisturbance threshold very challenging. So let's see how that variation looks like. So this is going to be 5 repeated measurements of the redisturbance threshold in a single victim row. Y-axis shows you the threshold values, x-axis shows you the measurements we did. So this starts off at 37,000-ish hammers. That's the number of activations you need to induce the bit flip. And it looks like this if you do 5 measurements. This is what it looks like over 1,000 measurements. And then we will measure more. So just to make sense out of this plot, we summarize those points as those 1,000 points as the maximum, minimum, and the average, as you can see here. And this is what the values look like if you do 100,000 measurements for a single row. And I think this particular measurement study took like a week or so for a single row. Anyway, so from here you can see that we see the, well, maybe you can't see that, but I labeled it. The minimum read disturbance threshold, you see it at the 16,926th measurement. And from that, we conclude that the read disturbance threshold of a row varies over time. And this is how it looks like across many chips. Again, this is data from a single row, but from every one of the chips we've tested. And this is consistent across the chips we tested. And you can find more details in the paper. And we also have done some statistical studies to find that this variation is very likely unpredictable. And you can find what we did in the paper to back that statement up. We also did an in-depth analysis. So we cannot measure every single row for 100,000 times, but we can measure them fewer times and explore more parameters, a larger parameter space. And these are the major takeaways from the in-depth analysis we did. We find that all of the rows we've tested, that's 150 DRAM rows in each tested chip in our study, they exhibit variable read disturbance, so that we didn't identify any DRAM row that was not subject to this phenomenon. And if you use relatively few, let's say that less than 500 read disturbance measurements, and then you take the minimum out of those 500 measurements, and then you consider that to be your minimum across time, that will that's not going to yield the absolute minimum across time. So that's what the second takeaway is saying. And then we found that with data patterns that you use to initialize your DRAM rows, with temperature and the aggressor row on time, so that's the effect of row press, the profiles of your rows, the variable read disturbance profiles will differ. So you have to be careful about what temperature, what data patterns you initialize your DRAM rows with, if you're considering finding the minimum read disturbance threshold value. This has key implications for the security guarantees of our mitigation techniques. And we discussed this in greater detail in the paper. But if the read disturbance threshold changes unpredictably over time, then you would like to use some sort of guard bands and some error correction capability in your system to mitigate these errors. And we find that doing so may prevent VRD-induced failures, but it comes with the overhead of, again, so the large guard bands you apply to mitigate these errors will induce performance overheads. And these are quantified in the paper. I'm not going to go into a lot of detail in the interest of time. One more thing I'd like to mention is we have this paper building on variable read disturbance. It's called Discord. The preprint is available on arXiv, and we're trying to deal with the question, so how can we reliably identify the read disturbance threshold in a relatively short amount of time, right? Not with 100,000 measurements, given that variable read disturbance exists. And that paper explores that, but it's still not published yet, so it's on arXiv. I'm not going to talk about row press. Onur already talked about this, but if you instead of repeatedly activating the aggressor row many times, you keep the row open for longer, you can induce these bits flips with fewer activations. And I'll mention that we also have a real system demonstration of row press. If you use this module and that CPU on the left side, you can run a C++ program and you can see the effects. So basically the hypothesis here is that if you repeatedly access the same, let's say the different cache lines in the same physical DRAM row, the hypothesis is that the memory controller will keep that row open for longer than if you access only a single cache block in that row. So using that, we see that row press gets you bit flips where row hammer cannot. And that's also in the row press paper. I will not talk about column disturb, except maybe I'll emphasize this question here. What if there's a much worse read disturbance phenomenon that affects thousands of DRAM rows through the bit lines? And that will be answered in greater detail today as part of Ismail's talk on column disturb. And I'll quickly go over a different class of, let's say, research that DRAM Bender enables. That's to uncover new DRAM functionality. And I'm going to highlight Quark TRNG. This was presented virtually by me in ISCA 2021 because of COVID. It wasn't held in person. And this is my first ISCA. I'm so happy to be here. So it's like almost as if I'm presenting Quark TRNG in the right way. I'll give you a little bit more background. So this is, here you're seeing the structure that we've seen earlier. This is a DRAM cell that stores data. It's charging a capacitor. This is the access transistor that gates access to the data. And then you have the sense amplifier that will sense the perturbations caused by the charge sharing process that takes place when you access the cell. So if you enable the word line, you will connect this capacitor to the bit line, basically circuit theory. And that will cause the capacitor to share its charge with the bit line. And then when the sense amplifier kicks in, it will understand that the bit line voltage deviated in one direction, and it will amplify it that way. And this will back to the capacitor. So if you look at DRAM operation, this operation in a coarser granularity, you will see that we access DRAM cells in the granularity of cache lines, and you will see some DRAM command sequence on the bottom here that shows the commands we execute as we access this one DRAM cell in that highlighted DRAM row. So first we need to issue an activate command to row 0. That will carry the data, or copy the data, let's say, from this row to the set of sense amplifiers on the bottom. Then you can send read commands to read data out in cache line granularity. That's typical 512 bits in today's systems. If you want to access a different row, you have to pre-charge this bank or subarray in this picture. And then you can activate another row, and you can read from that row again. And there are some timing parameters that you need to obey to guarantee that these operations succeed as DRAM manufacturers or DRAM vendors design them to. That one important parameter is TRAS, that's the activation latency. It's the time you need to wait between an activate command and the next pre-charge command. And the other one is TRP, that's the pre-charge latency. It's between the pre-charge command and the next activate command to the same subarray. Now, why I talked about this in this much detail is because if you violate those timing parameters, meaning by default, you have to wait for around 35 nanoseconds for TRAS and around 14 nanoseconds for TRP. If you greatly violate those and you only have a delay of less than 3 nanoseconds between these commands, what happens is you activate 4 rows simultaneously in the DRAM chip. And with that 4-row activation, and we have in the paper detailed explanations of what circuit level details might be causing this, but I'm not going to talk about them in detail. If you do that 4-row activation, you can actually generate high quality true random numbers, which are useful for many applications. And you can do this inside your DRAM chips. So it has a nice synergy with processing in memory, the processing in memory paradigm, if you think about it. You can securely generate true random numbers inside your DRAM chips without going to some outside source. So I'll show you how that works over this pictorial example. Here we have 4 different cells or 4 rows on a bit line. And we initialize these rows with conflicting data patterns. So half of them will get logic 0, half of them will get logic 1, in a way that each cell will cause the bit line voltage to deviate towards its own direction. Right? So if you have logic 0, they will try to take the charge level on the bit line down. Logic 1 will try to take them up, and you will end up in a metastable region. And basically, that's what this figure is showing you. If you send the activate pre-charge activate command sequence with violated timing parameters, you will activate all 4 of these rows at once, and the bit line will end up at a metastable state. So what you end up seeing in the sense amplifier is caused completely by random perturbations. So if you build on this idea to develop a DRAM-based true random number generator, we've seen that this gets you higher throughput than prior best DRAM true random number generators. And all of this is explained in more detail in our paper. But we also have new ideas building on this. Simra TRNG showed that you can activate even more rows or fewer rows, actually 2 rows simultaneously, but up to 32 rows. And you can get higher throughput than Quark TRNG. This was published in ICCD. And with Simra, you can also do, like with multiple row activation, you can also generate physical unclonable functions. I won't go into the details of this, but this was presented in Dependable Systems and Networks just last week in Charlotte. So another set of, I think, ideas that we've developed that Ismail led builds on this key primitive, like activate, precharge, activate command sequence with violated timing parameters. If you open multiple rows, you can do, you can realize not and NAND or and NOR operations in real DRAM chips. And he's going to talk about this in more detail tomorrow in the MCCSys workshop. So I'm going to skip these. And also Onur gave you some good ideas on how this works. So it's kind of redundant. And I'll talk a little bit about the last, the final class of work I want to highlight as like DRAM Bender enables learning DRAM internals. And I'll talk about uncovering in DRAM row hammer protection mechanisms. We talked about row hammer. I'm going to eat like 2 or 3 minutes into your break, if that's fine. But feel free to leave, if, of course. I cannot keep you here. Target row refresh is a mechanism that was adopted by DRAM manufacturers in their DRAM chips. It's a proprietary row hammer defense mechanism. The key idea is there's some sort of sampling logic inside your DRAM chip that will determine if a row is an aggressor row, and it will also decide to take an action or not. It's completely up to the implementation of the TRR mechanisms. And before this paper, these mechanisms, the way they operated, were largely unknown. But the basic idea is some sort of sampling is happening inside your DRAM chip to determine which row is an aggressor row. In this work, we studied the in-DRAM TRR mechanisms to understand how they operate and then evaluate their security guarantees, and also propose ways to completely secure them against redisturbance bit flips. That's the paper. The key idea of the experimental methodology we used in that paper was to use data retention failures as a side channel to detect if the TRR mechanism refreshes a victim row. So I'll explain how that works. We have a 7-step or 6-step methodology here that I'm going to go through. And this is a high throughput slide, so I need my notes for perfect delivery here. We find a DRAM row R with a retention time of T. And this means that the row will harbor a retention failure, retention error, if we do not refresh it for T units of time. And on the bottom, we have a timeline of actions taken by us, the experimenter, and the hypothetical TRR mechanism inside the DRAM chip. So initially, the row is refreshed, so it can retain data correctly until time hits T on this diagram over there. And we're going to advance time. We wait for half T. What we're going to do now is we hammer the aggressor row right next to this row only once. So we activate it once. And at this point, we'll see what the hypothetical on-DRAM die mitigation mechanism would do. If it exists, it will, or it may or may not, but we'll consider it will sample this activation as an aggressor row. And then we issue a periodic refresh command. And one thing I didn't talk about earlier is that TRR mechanisms will take their preventive actions at the time of a periodic refresh command. So there's some slack that the DRAM chip can use to perform additional refresh operations during a periodic refresh operation. Our goal with the 4th step is to trigger this DRAM mitigation, the on-DRAM die mitigation technique to perform some action. In fact, if it exists, if it had sampled this as the aggressor row, then it will refresh the victim row. Now we wait for another half T, and then we read out row R and check for bit flips. The key here is that this row, victim row R, will experience no bit flips only if the on-DRAM die mitigation mechanism exists and it refreshed row R at the right time. And if it doesn't exist, the on-DRAM die mitigation mechanism doesn't exist, then row R will experience a bit flip because T units of time has passed, and there's now going to be a retention error in that row. There are a lot of details and things you have to consider, like variable retention time. This retention time of the row will keep changing and so on. So you have to account for a lot of, let's say, drawbacks of real world testing. But this mechanism works, this methodology works. And using that methodology in the UTRI paper, we've uncovered a lot of details about how these proprietary mechanisms work. So there are no published details about these mechanisms, but using this sort of an infrastructure, you can understand how they work. And we crafted new attack patterns, access patterns that bypass, that try to bypass these mitigation mechanisms. And here you see the effectiveness of these attacks. I'm not going to be able to talk about this in detail, but the qualitative takeaway is that now you can, if you understand how these sampling mechanisms work, you can bypass them also. And for a lot more details on this, I'd like to refer you to the UTRR paper. I think we have also a very nice paper, DRAM scope, that's gonna maybe be talked about today as part of one of our invited speakers' talks. But that actually concludes my presentation. So I'll just have a final slide here that just to summarize, I think DRAM Bender enabled many studies, ideas, and methodologies in the design of future memory systems. And I've covered a few of those in greater detail. We attribute the success of DRAM Bender to its flexibility and ease of use. And today, I hope you will get to experience that. And I think with more research, or with more researchers actively participating and from our community in DRAM Bender related research, let's say, it drives us to develop new features for it as well. So over time, Onur talked about the story of how we had an earlier framework that supported DDR3. And then we had this DRAM Bender infrastructure that supported DDR4. Now it also has support for HBM2, and maybe moving forward for HBM3 as well, if Google and Meta and NVIDIA lets us get any of those. But it already supports 6 FPGA boards out of the box, and the number of FPGA boards supported is increasing year over year. So I hope you will be able to easily use this if you really want to. That concludes my presentation. I think I'm 4 minutes into the break. If you have any questions, I'll be happy to take them. Otherwise, thank you for your attention. And I'll see you after the coffee break. No questions. Okay. 10:30. Yeah, we'll start at 10:30. We'll have an invited speaker, a very cool talk. It's going to be about cryogenic temperatures and DRAM.
Hello. How are you? Good. Oh, no.
What happened? Oh.
Okay. Nisa here. Okay. Very good. Yeah, nice to meet you. Yes. Yes. This should be exciting. Yeah. No, who's on the panel? Well,
I'll get some food.
I'm kind of curious.
I'll get some food. Zoom audience.
I know. Well, and then right, we had the various Samsung guys. Oh, that's right. Well, they vanished. And then all the information. Allegedly, someone has around. Okay. Very interesting. Of course. Well, it's fun to say. It's good. Yeah. We're trying to get Microsoft. Yeah. That's Dell. See, that's what makes comments for the views. DRAM manufacturers. No, but actually, I was yeah, absolutely, absolutely. Yeah, yeah, yeah. Maybe you guys. Well, in the range. Yes. Okay. 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 Yeah. 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 No. It's jetic. So. Software supply chain. Yeah. Goal of the system. All these other things. Floating around. I do a lot of times. Our team focuses on got it on this, let's just put it on this. Yep. That's very interesting. I was like, really? They're like, yeah. Yeah. It's not the label. There's an end there. Are we going to play it 9 really? No, that's not our part.
They sell you am I being censored? Am I?
No.
Oh, this is the wrong one.
Yes.
Oh, this is the wrong one. Okay.
I can also unmute that.
Sure.
Okay. Maybe I'll give you this and then I'll give you this one.
Okay. Problem with that was we cannot buy boards from. That's the main problem. They want to sell you a service, not the product.
I see.
The product comes as a service. Do you want to like? Where would you like to stand? Here, there.
Yeah, I'll stand there.
Okay.
Sure.
Let's start with you.
Okay, sure.
I'll introduce you. And then
Sure. Okay.
introduce you from here. So we're continuing our workshop with an invited talk from Dr. Haocong. I hope that's correct. He is a senior research manager at Beijing Superstring Academy of Memory Technology, and he works on advanced memory pathfinding, including 3D DRAM, cryogenic DRAM, and non-volatile memory technologies. His research interests include advanced memory materials and device modeling, and the reliability and characterization of memories under extreme environments. And Dr. Bai received his PhD in physics from the National University of Singapore. He also holds a MS in electrical engineering from Stanford University. He has published more than 30 research papers and filed more than 20 patent applications. We're very happy to have you here. Please go ahead with your presentation.
All right. Thank you for the introduction. Good morning, everyone. My name is Haocong Bai. I'm from this SAMT in Beijing. If you don't know us, we are a research institute focusing on advanced memory technology research and pathfinding. So I would like to thank the organizer invite me over here to present our recent work on cryogenic DRAM. And much of the essential part of this work was actually carried out using DRAM Bender. So it's my pleasure actually to share our user experience and testimony with the community. So I would like to acknowledge collaboration with Professor Kim's group in Korea, and also my local collaborators from Tsinghua University and also CXMT. So the original work was published in International Memory Workshop this year. So if you are interested in this work, you can refer to the paper there. I don't have a disclaimer page, but I'm still in jet lag, so bear with me if I'm slow. And also, I'm not a system person, so I come from a completely different background. So if I made any mistake, just point it out. We'll appreciate that. So here's the outline of my talk. So I believe this cryogenic electronics is a less visited topic. So I will spend the first few slides to walk you through the background and motivation, why cryogenic electronics and cryogenic DRAM are interesting topic. And then the real technical work, I will talk about our study on cryogenic DRAM. We tried to be holistic, so we studied this problem from different perspectives, from like a device level, from circuit level, and also from DIMM level. And for this DIMM level research, we use DRAM Bender as a programmable test platform. We call it a behavior study because we didn't redesign anything. We just put existing DRAM, commodity DRAMs into like cryogenic environment, test them and study their behavior. So I hope that clarified the scope of this work. Background. So cryogenic electronics is no longer a niche field. It actually attracts like research interest from multiple communities. For quantum computing, people there try to put this control and readout circuitry into very low temperature so that they can have a better control of the qubit and also prevent thermal leakage, promote integration. And for deep space electronics, actually, the electronics are naturally working in a complicated environment which combine like cosmic radiation and wide temperature range. But this work actually was in the context of high performance computing, where people talk a lot about performance and energy efficiency. And there's lots of problems you're all familiar with, like Moore's law slows, Denier scaling breaks, and AI era drives soaring energy costs. And for the memory side, there's widening process memory performance gap, and many of actually today's AI workloads are increasingly memory limited. Of course, I mean, we should continue with the technology scaling, but for cryogenic electronics, we look at this problem from a slightly different angle. We ask the question, if we put existing technology in cryogenic environment, would this electronics work as intended? And if they do, how much benefit in terms of performance and energy efficiency we can get? If you look at existing literature, actually the answer is pretty positive. So if you put like if you don't change anything, you just put off-the-shelf CPU and DRAM into like a low temperature environment of like 77K, you will have a huge boost in the peak frequency and also the I/O bandwidth. But this improvement are not just, I mean, are achieved without cryogenic specific redesign. Low temperature itself already provides substantial performance headroom, which can be either traded for higher speed or converted into lower operating voltage and improved energy efficiency. And more importantly, cryogenic operation is not just a cooling solution. It has, there is actually a much richer physics behind it. If we intentionally design devices and circuits architecture from a cryogenic aware perspective, the achievable gains can become even more substantial. One particular inspiring example is this work from Georgia Tech, which showed that cryogenic aware gate level design can achieve delay improvement even beyond what is typically obtained from conventional technology node scaling. By leveraging the enhanced device characteristic at low temperature, they demonstrated substantial faster circuit operation together with lower energy consumption. And more importantly, these benefits also propagate to processor level. Their work shows significant improvements in both overall processor performance and performance per watt, highlighting that cryogenic operation is not just a device level phenomenon. It actually offers a system level opportunity for continued performance and energy efficiency scaling. And for DRAM, specifically, cryogenic temperature also dramatically suppress the leakage current and leading to much longer retention time. This means refresh operation can be significantly reduced or potentially even eliminated in some operating region, which not only lowers the refresh power overhead, but also improve effective memory availability and overall system efficiency. Then you may naturally ask the question, where do this benefit come from? To answer that, we now move one level deeper and look at the underlying physical mechanism behind this improvement. I will first focus on, so this is basically a typical transfer curve of a transistor. So I will first focus on the substrate swing in more detail because it is one of the most important mechanisms. At lower temperature, the thermal energy of carrier is reduced. So the transistor can actually switch much more sharply. So this is actually the room temperature transfer curve, and this is the low T transfer curve. So this gives us a steeper SS, restores voltage headroom, and enable lower VDD operation for better energy efficiency. And besides SS, there are also several other beneficial factors at cryogenic temperature. Leakage current becomes automatically smaller, dramatically smaller, which help reduce static power and for memory, improve retention. Carrier mobility increases, which improve drive current and transistor speed. At the same time, the wear conductivity can improve by several times at cryogenic temperature, reducing interconnect resistance and RC delay. Together, this mechanism contribute to a higher speed, lower power consumption, and potentially improved reliability for cryogenic CMOS and DRAM systems. After discussing the broader opportunity of cryogenic like electronics, we now focus specifically on DRAM. In this work, we actually asked two key questions. First, can commodity DRAM operate reliably at 77K? And second, what performance, power, and reliability benefits can emerge from cryogenic operation? To answer these questions, we actually perform a full stack evaluation spanning from from device physics to DIMM level behavior. This include device level characterization and circuit level simulation and direct and also direct evaluation of commodity DDR4 DIMMs under cryogenic environment, where we use this DRAM Bender as our test platform. So let us start with the device level. Since the device physics ultimately drive the circuit and DIMM level behavior that we observe later. So there are many different like DRAM devices in a modern DRAM chip. And here we just show 6 representative ones. In this slide, we focus on like cell devices, the 1T, 1C, access transistor, and storage capacitor. And in the next slide, we move to the peripheral CMOS devices, including high and low VT NMOS and PMOS devices. So these are the real device that from like commercialized DRAM from our industrial collaborator. And for the cell device, we mainly care about leakage since it directly impacts retention. As the temperature goes down, both the transistor and capacitor leakage decrease significantly, but to a different extents. For the access transistor, the leakage almost completely vanishes at cryogenic temperature. And for the storage capacitor, the reduction is much smaller, only around 1 to 2 orders of magnitude. The reason is that once the semionic emission leakage is suppressed, the remaining leakage is mainly trapezoidal tunneling in the high K dielectric, which is much less temperature dependent and therefore set the floor for the leakage. And so overall, we actually observed 2 different leakage regimes across temperature. Near room temperature, especially when the cells is storing a logic 1, the leakage is mainly transistor dominated. But at lower temperature, the dominant leakage mechanism shifts to a storage capacitor. Now we move to the peripheral CMOS devices, including both NMOS and PMOS transistors with high and low VT options. Overall, the trend are very consistent across all devices, all device types, as temperature decreases from 300 K down to cryogenic temperature. We observe steeper subthreshold swing and dramatically reduce leakage current and improve drive current, which are all beneficial for DRAM peripheral circuits, such as like a sense amplifier, decoder, driver, and control logic. This observation are also broadly consistent with what has been reported for advanced logic CMOS devices, suggesting that many of the cryogenic benefits are fairly general across modern transistor platform. One important caveat, however, is that the threshold voltage also increase at lower temperature, which can partially offset the energy efficiency benefit. So to fully employ cryogenic operation, cryogenic aware like VT and VDD scaling is likely needed rather than simply cooling conventional room temperature designs. With the measured device data, the next step is actually to enable circuit level simulation, which requires compact device models. So in our work, instead of relying on the conventional BSIM style modeling, which usually requires extensive parameter calibration extraction work across temperature, we will adopt a different approach in this research by using an artificial neural network-based model. Here, the neural network takes the terminal biases and temperature as input and predict the device current as output. We then benchmark this artificial neural network model against established compact models such as EKV. And as shown here, the artificial neural network model is able to reproduce both the transfer and output characteristic very accurately across a very wide temperature range from 77K to 300K with the prediction error below around 0.5%. With the cryogenic models in hand, we then move to a circuit level simulation to evaluate both the power performance benefits and functionality of DRAM-related circuits under cryogenic operation. So here we basically study 3 representative circuits and each with a different focus. So first, we talk about this ring oscillator. We mainly focus on the power performance trade-off. At 77K, we observe substantial performance improvement together with large power reduction. Under ISCA leakage condition, the frequency improved by around 1.5x, while the power can be reduced by more than 80%. So this shows that cryogenic operation creates significant design headroom for either higher speed or lower power operation. And second, for the row and column decoder, we are particularly interested in standby power, since standby power is critical for large memory array. And here we observe that the static power becomes nearly negligible at cryogenic temperature due to the dramatic suppression of leakage current, while maintaining comparable latency of performance. And finally, the third circuit we evaluate is a level shifter. So the main focus here is functionality. A level shifter is basically a voltage amplifier. If we feed in a low voltage square wave, ideally we should get the same square wave at the output with the same frequency, but a much larger voltage swing. However, at cryogenic temperature, the original room temperature design no longer works correctly because the large VT shift and device imbalance. In this case, the output gets stuck at high state instead of switching properly. To fix this issue, we actually redesigned the circuit by stringing the pull-down paths using a wider NMOS devices, which helps rebalance the circuit under cryogenic operation. After redesign, the functionality is successfully recovered, which still achieve around 50% latency reduction and around 70% power reduction. What is worth mentioning is that we simply cool down the original room temperature design, and the dynamic energy improvement itself is actually relatively limited. To fully maximize the cryogenic energy efficiency gain, cryogenic aware VT and VDD scaling is likely necessary rather than relying on temperature reduction alone. So overall, this circuit simulation basically show both opportunity and challenges of cryogenic electronics. Significant power performance benefit are achieved, but some circuits may require cryogenic aware redesign to fully exploit them. So far, we've mainly been looking at cryogenic behavior from device and circuit side. But the real question is, can these benefits and some of these challenges actually can be carried over to the real commodity DRAM system? To look into that, we now move to a DIMM level evaluation, which we directly test commercial DDR4 modules at cryogenic temperature and study things like functionality, retention, reliability, bandwidth, and power. So in order to carry out the DIMM level tests, we build a custom experimental platform, which consists of both an electrical part and the cooling part. For the electrical side, we use, DRAM Bender, which is FPGA-based DRAM test platform, original open source by these organizers at ETH Zurich. It provides a low-level programmable DRAM control, which is very important for our study for detailed like characterization and reliability study. For the cooling side, we actually build an air-sealed cryostat to cool the DIMMs down to a cryogenic temperature. A key requirement of this setup is that the DIMM need to be cooled down while the FPGA and surrounding board electronics remain near room temperature. So this basically took a lot of like thermal engineering. We need to add a good thermal isolation between the DIMM and the board. And also we design a water pipe, circulating water pipe to just warm up the board. And in the end, I mean, this actually design actually works, and we are able to carry out the low temperature study as what we want. So first we talk about with the platform ready, we first move on to the functionality characterization of commodity DRAM under cryogenic temperature. The testing procedure is actually fairly straightforward. We just repeatedly perform a bunch of write, retention, and read operation. And more specifically, we first write a data pattern into the array and let DRAM retain the data for a certain number of normal refresh intervals, and finally read the data back out. Ideally, we should observe exactly the same data as we originally wrote in. If not, we record the failure location together with the corresponding temperature. So this figure, I mean, on the bottom left, actually summarize the functional behavior across different vendors. The black marker indicate the temperature we observe at which we observe the first bit flip, and the blue ones denote the temperature where we see bit error rate of 1e-7. Overall, we actually observe a very notable vendor-to-vendor variation. Some DIMMs can operate reliably all the way down to our measurement limit, which is actually not 77K, but 90K, because this DIMM, when they work, they actually is actually a heater of some certain power, like a 5 volt or something like that. So yeah, while others begin to fail at a substantially like higher temperature, they suggest that the cryogenic robustness is actually strongly influenced by vendor-specific design and process choices. And we also try to understand the data or understand the source of the failure. So to do that, we actually map the spatial distribution of failures inside the DIMM array. In this plots, actually, the darker blue means fewer failures, and brighter regions actually means more failures. And interestingly, we observe this column-like failure patterns. So if the failure were purely caused by individual cell devices, we would expect them to appear as a random distribution across this cell array. But now they show this strong column correlation. It suggests that many of the failures are likely circuit related. For example, originated from sense amplifier or related peripheral circuitry. And this is actually quite interesting because if you still remember my previous slide, actually, because the sense amplifier also contains this cross-coupled inverter structure, somewhat similar to the level shifter we discussed earlier, which may also become sensitive to device imbalance and VT shift under this cryogenic temperature. So they might originate from the same failure source. And then next, this is actually the the way we use DRAM Bender, this API to program our test procedure. So I won't go into details because as the expert just sitting here. So, but this, very easy to use. We are actually not system level person, but this interface is very, very approachable for us. Actually, it's very flexible, and we just can use this because they have very good abstraction of the underlying operations into this high-level programming language. So we can just call these functions and easily define the variables and also this the test procedure or experiment. Then we move on of retention, which is one of the most important aspects for cryogenic DRAM. Here we test the retention by completely disabling refresh operation. After writing data into the memory, we simply let the DRAM retain those data for a certain period of time, and then read the data back. Once we observe the very first fill bit, we define that time as the retention time. This is actually a pretty conservative definition, but even with this strict criterion, we still observe a very strong and fairly universal trend across different vendors. From 300K down to around 120K, the retention improved by roughly 1,000 times. We also extract the activation energy associated with the bit flip from the temperature dependence of this retention behavior. And interestingly, we again observe these two distinct temperature region. At a higher temperature, the activation energy is relatively large, which suggests that the thermionic activated leakage mechanism dominate the retention loss. But at lower temperature, the activation energy become much smaller, indicating a transition to a weaker temperature-dependent leakage mechanism. This behavior actually interestingly matches very well with the device-level leakage result we discussed in an earlier slide. Near room temperature, the retention loss is mainly dominated by excess transistor leakage, while at cryogenic temperature, the remaining limitation increasingly come from storage capacitor leakage, especially those trap-assisted tunneling. If you understand the device physics, this tunneling mechanism are independent, almost independent with temperature. Well, so this is basically the retention test flow. So while the greatly extended retention time is very beneficial for reducing refresh power, it also naturally raises another important question regarding reliability and data security. If the refresh interval become much longer, then DRAM rows remain vulnerable for a longer period of time, which could potentially enlarge the attack window for disturbance-based failures such as row hammer. So after study retention, we'll next move on to investigate how cryogenic temperature impact row hammer behavior. What is particularly worth mentioning is that we can roughly characterize our test data pattern into two groups, and they show very different temperature dependence. One group exhibits strong temperature sensitivity, while so the top row, and while the other remains almost temperature insensitive, even at a cryogenic temperature. We are semiconductor device person, so this behavior is actually interests us because it doesn't actually fully align with some of the conventional understanding of roll hammer mechanism at the semiconductor device level. Because the understanding was, so this mechanism actually based on, so the conventional, understanding of the mechanism is that this roll hammer thing is based on electron migration or trap-assisted charge transport. And those physical process actually is strongly depends on temperature. So this trap capture or emission of a stored charge is actually very sensitive to temperature. If you lower the temperature to a very like a cryogenic region, those mechanisms should be frozen, and you would ideally observe a very strong or very like strong improvement in roll hammer behavior. But this is not the case for some of the data pattern. So so this may suggest the existence of a different disturbance mechanism that is much less temperature dependent, and we are currently still investigating them. So we did actually some like device level TCAD simulation and actually find some probably new mechanism. And we think this is important because if we want to, of course, you can mitigate roll hammer effect from like a system level, from different level. But you can, but if you want to improve it also from the process, semiconductor process perspective, then you're better to understand this this mechanism fully instead of relying on like a partial understanding of roll hammer. And then last slide. So this is basically, we also test the DIMM power and bandwidth. At low temperature, actually, we find that low temperature enables stable overclocking of the DIMM with pretty remarkable improvement of the I/O bandwidth. And for the power, because our test workload is basically dynamic workload dominated, so we don't see very, like we do see actually an increase of power at lower temperature, but this is understandable because this DIMM is actually not experience cryogenic redesign. So so the dynamic power is basically determined by like a CV squared times F. We didn't scale like the voltage, but we ramp up the frequencies. So of course, you will see a larger temperature, this power consumption at lower temperature. So conclusion. So I will give some takeaways. Cryogenic operation actually unlocks some major power performance scaling opportunity for DRAM. Benefits arise from reduced leakage, enhanced driving current, steeper subthreshold swing, and lower wire resistance. And commodity DRAM actually demonstrate feasibility, but not the full potential. The full benefits actually require cryogenic aware DRAM redesign across device circuit system level. Cryogenic DRAM must still address reliability and security challenges. The roll hammer doesn't automatically become better at cryogenic temperature. So here's some ongoing work. We are collaborating with our like local like collaborators to develop test function for DDR5 DRAM, and we want to extend this cryogenic study to HBM and GPU, etc. And recently, I mean, you also see I believe you all have seen these headlines of moon shooting, whatever this electronics to the space. And so it's actually, so this is actually pretty interesting, a diagram from economists. Actually, some people are, I mean, some people are pretty optimistic, well, some of them are pessimistic. So this is actually reflected from this cost estimation of how much it will cost if you shoot a 1 gigawatt data center to the space. And so this line is basically the cost of building a 1 gigawatt data center on the Earth. And with some of them actually estimate this cost to shooting this on space is much higher. But with the roadmap broadcast by this Star Cloud and SpaceX, whatever, with reduced this satellite costs, launch costs, and other costs, you basically, I mean, have a possibility to build a data center with even lower cost than what you do on the Earth. So we also hope to study, plan to study this cryogenic plus radiation conditions to simulate what this electronics will experience in the space. So we do build up some test structure in this National Institute of Atomic Energy in Beijing. So this is actually 100 mega electron volt proton cyclotron, and we mount this DRAM Bender test platform probably here, and then we actually do some redesign of this test platform, because the original slot that we can test the DIMM is probably this one, but we want to face this this chip directly to the radiation source. So we did some modification to the lower level, like the language you guys shared on the GitHub, and we shift that slot to here. And then so this is the radiation source, and then we do some radiation protection to the rest of the board, so that, I mean, we just shine on the DIMM, but not damage anything on the board. So this is we are still carrying out this study, and we will show the result in the near future. So finally, I will give a big thanks to the Safari group at ETH3 for both open sourcing this amazing DRAM research platform. Actually, when we were assigned this research task, we were scratching our head on how to testing a real DRAM DIMM, because none of us are of like a system background. We are like a semiconductor material device person. And then we came across this this amazing research platform, which opened the door actually for our research. So with all this, much of the actually research result I shared just now wouldn't be even possible. And I also appreciate personally you guys publishing these YouTube courses on computer system architecture, because years back, actually, I was taking this EE282 class in Stanford, and it's really hard for me to catch back. So I really learned a lot from this video, and I gave you lots of give your video lots of likes. and that's it. I mean, I'm happy to take any questions. Thank you.
Any questions from the audience? I think I.
Now too. You gotta shout a little bit, maybe.
Yeah. No, it's fine. Go ahead. This is for Zoom.
Yeah, first, thanks for the awesome presentation. So if if it's possible, would you mind like elaborating more on the device level mechanisms of Rowhammer that you find, let's say, existing device level works does not at lower temperature level? Yeah.
I see. So the conventional understanding of the mechanism is basically through electron migration, which is mediated by, like traps. Because I mean, this transistor in silicon have lots of this defects or traps, and then so basically you have this stored capacitor, and then these traps will capture the stored electron or charge, and then throw it away. And some of them, these charges doesn't go back to the capacitor. It's just a loss. But that mechanism actually doesn't fully explain what we observe here, because I mean, for certain test patterns, actually you don't see this. By the way, this capture emission process is actually strongly temperature dependent. It should be frozen out at low temperature, because the capture emission rate, if you look at those functions or equations, they are strongly dependent on temperature. So at lower temperature, it should be frozen out. But the observation is not in that way, at least for some of this test pattern. And we did find some mechanism which caused by capacitance coupling from like a capacitance coupling, and then those coupling actually is insensitive to temperature. So it's actually a fighting between these two different mechanisms. And for some of the data pattern, attacking pattern, actually this capacitive coupling mechanism actually dominant. That gives you this temperature insensitive behavior. I hope that answers your question. Yeah. Yeah. Thank you.
Because we're also looking into how we can expand this testing platform. And one challenge we face is that like for all the, let's say, commercial FPGAs, we don't seem to find a commercially available combination of a hard DDR5 PHY combined with a soft controller that allows.
That is where the problem is. But, I can refer you to some of those are not actually perfect solutions, but I can refer to you some like open source platform called Phoenix. I'm not sure whether you're aware of that.
Phoenix?
Phoenix, right. So they actually did something about DDR5. And they also have some like open source GitHub repository. But well, we just try to modify it, but it's still in the process. As I agree with you, it's very, very, very challenging.
I see. Yeah, thank you.
Thank you very much, Dr. Bai. I think we have many more questions for you. In the interest of time, I'm not going to ask them yet.
Yeah. And thanks for the nice talk. I think it's very interesting. It's great that I think device level folks like you are looking into system level issues. I think we need a lot more communication between these communities. It's hard to actually break these barriers sometimes because you submit a paper to ISCA that has some device level results. These ISCA people sometimes say basically, oh, you gave me a paper that I cannot understand, reject. But I think we need to change that, you know?
Yeah,
like we've changed that.
That's why I appreciate you invite you over here.
Yeah,
this is the first time actually I speak to this community.
Yeah, I think this community needs to be more open and hearing from other lower levels also of the stack, because that's how you can, going forward, that's how you can really solve the very challenging scaling problems. You cannot solve them by being an ISCA person only. Anyway, after making that statement, I have a question about your radiation testing environment.
Okay.
You said you have some results on that. Were you completely able to protect the rest of the board? And what kind of measures did you take other than just radiation protection?
I think I think the board actually works as it pretty normally. We just did this like a copper. We actually designed like a copper box. Okay. And then put it just on the cover. I mean the rest of this board, and actually it works pretty fine. We didn't find any problem with the FPGA board because but the copper has to be sufficiently thick. Because otherwise it will, the radiation can still go through.
Okay. So you didn't need to actually build a separate extension to separate the DIMM?
No, we didn't.
Okay. Okay, looking forward to your results.
Thank you.
Thank you.
Yeah, thank you very much.
Thank you.
I have many more questions, but I think we'll take it.
Sure, afterward.
Yeah.
Sure. Thank you.
Thank you very much again.
Okay, then let's move on to the Ramulator side of the tutorial for now. We will have more invited talks talking about both tools, but now I will talk about Ramulator, but starting with a brief introduction. Okay. We already covered this. I'm Nisa, happy to be here and happy to see you guys. Let's start with Ramulator, the first version. A fast and extendable DRAM simulator, as it was published in Computer Architecture Letters in 2015. And the motivation behind Ramulator was covered by Onur a bit, but I will reiterate it a bit more. So DRAM and memory controller landscape was changing with many new and upcoming standards, some of which you see in this slide here on the table, from DDR3, DDR4 to HBM and so on. And there were also many new controller designs that we wanted to study and see what they offer in our memory systems. So to study these systems, these architectures, these new standards, a fast and easy to extend simulator was very much needed. To address this need, Ramulator was developed, and Ramulator is a fast and extensible memory simulator which provides out-of-the-box support for many DRAM standards, again from DDR3 to HBM to emerging memory technologies at the time, such as PCM, STT, RAM, and so on. And it also supported new proposals from sub-array level parallelism, which changes the architecture, or more like processing in memory architecture techniques such as row clone. And at the time of the study, it was faster than the fastest open source DRAM simulator. And you can see some comparison numbers here. What's more important to us that it enabled unique case studies. So this was one of the case studies that we covered in the first paper, which was a comparison of DRAM standards. Again, you see in this table different DRAM standards with different characteristics, DDR3, DDR4, HBM, and so on. And all of these have different benefits when you consider the memory system, when you consider your workloads, and so on. And it was not possible to compare them directly because at the time, none of the existing DRAM simulators supported all of these DRAM standards. And with Ramulator, we were able to look into the performance comparison of these DRAM standards across a wide range of applications using a simple CPU model and plotting these results and looking at the trade-offs in the system design. And again, this is the link to the paper. And if you're interested, you can find much more details about it in the paper. And Ramulator is free and open source. Again, this is the first version. And there are also some steps to get into using Ramulator with some reproducibility steps from the paper itself. And it was also possible to integrate this tool with other simulators, other system simulators like DRAM5, which we included some steps to do this integration with. And Ramulator was used by many works. It enabled a lot of works, it was used both from like groups in academia, in industry, as Onur also covered. And we were also using it a lot for our internal use, right? We were using it for our research works and so on. And we kept developing it and maintaining it for a long time. But we wanted to also improve it and make it even more modern, even more modular and extensible. And this is why we developed Ramulator 2.0. And the motivation behind Ramulator 2 did not change. DRAM and memory control landscape is still changing. But we were interested in looking into two different directions in our research. First, we wanted to look into robustness issues in DRAM, from data retention to read disturbance, like raw hammer, raw press, column disturb, which we will cover today. And there are even more issues that we wanted to study in DRAM in memory systems in general. And we were also interested in looking into performance issues in main memory systems and alleviating them with architectures like processing in memory architectures by simulating those new architectures, future systems. Or we wanted to look into emerging memory technologies to see what trade-offs we can see by adopting them in our systems. And we wanted to especially incorporate both of these directions and look into the performance overhead analysis of future systems that might adopt these read disturbance mitigation techniques. And we see that these techniques are today being introduced into the standards and being prepared to be available in a lot of DRAM modules. So we wanted to look into, well, we didn't know the standard part, but we wanted to look into different designs and see the performance overhead analysis. And because of these reasons, particularly for us, DRAM simulation infrastructures were needed and are still needed to understand, characterize, and evaluate the robustness and performance of DRAM. So we developed Ramulator 2, modern, modular, and extensible DRAM and memory system simulator. Ramulator 2 still models a wide range of DRAM standards and memory controller functionalities. It has a modular and extensible software architecture, which I will describe a bit in a little bit. And Ramulator 2 models DRAM operation at a cycle level, adopting a fine-grained modeling approach. And it is used in a wide range of research work since it's been released. I will give the highlights of our design and features, and Haocong will follow up with a more detailed description of latest changes that we have done, introducing Ramulator 2.1. So we talked about this modular and extensible software architecture. What we mean by that is we introduced two main concepts to model all components in the memory system. First, we have interfaces. An example of an interface could be the front end, and another example could be the memory controller. And this interface concept defines how these modules, how these components communicate with each other. So front end sends a memory request to the memory controller side, which will be served from the memory device itself, and it receives the request callback when the request is served. And the interface defines this communication between these components. And the implementation concept is a separate concept. It decouples this communication from the actual implementation of these components. For example, the front end could be implemented as a simple out-of-order core, or it could be an in-order core, but this does not change the communication, so we decouple them. And here, memory controller is a generic DRAM controller. So I will explain this with an example. The memory controller can include many things, from address mapper, request scheduler, refresh manager, raw policy, and so on. And this is how the system looks like in Ramulator 2.0. So here you can see a lot of interfaces from front end, memory system, address mapper, DRAM controller, or the DRAM device itself. And what we do is, having these interfaces, Ramulator 2 defines how these all come together and communicate with each other. And all of these components can be independently implemented with different design features. So this enables us in a unique way that we can flexibly change each component without hard coding the other parts of the system design. So for example, let's say that I want to change the request scheduler. I don't need to hard code any other part in the controller or in the front end. I can just change the request scheduler and compile, and then I'm good to go. Another key design point that we introduced in Ramulator 2 is the memory controller plugins, which is highlighted in here. As you can see, the plugin is a component that communicates directly with the DRAM controller, and it is actually decoupled from the rest of the system. You can define different communication channels, but this is how it's by default implemented. So what is this plugin? We made the key observation that many memory controller functions and utilities are triggered and updated by the currently scheduled command. So they don't really care about anything else. Let me give you an example of this. So using this plugin and using just the currently scheduled command, we can implement a lot of functionalities like DRAM command sequence validation or access pattern profiling. If you want to check an application, like where an application accesses in DRAM and so on, we can just add a plugin and basically track these at the controller level. And we use this mainly for the raw hair mitigation techniques that we implement with Ramulator 2. Now I will show you in a bit more detail, taking the raw hair mitigations as an example. Here again, we have our DRAM controller interface and our DRAM device model interface, and they communicate with each other. So this communication is defined. And we have, as an addition, we have this plugin interface, which implements a lot of these raw hair mitigation techniques. Here we see a lot of like different designs, from probabilistic designs to deterministic designs. All of these mitigation techniques have their own definition, and they basically can do different preventive actions as well. So what we do is memory controller updates the memory controller plugins when a new DRAM command is issued. And after that, the plugin can then implement the design-specific tracking methods or probabilistic schemes to perform preventive actions. So it can enqueue victim refresh operations back to the DRAM controller device by this communication path, or it can trigger different actions such as row migration and so on. So all of these details, design-specific details, are within the plugins, and we can just change them, keeping the rest of the system mostly the same. And we can implement a lot of these mitigation techniques. Now, let me talk about the DRAM modeling side of Ramulator 2. So the DRAM device interface supports implementations of many main memory standards similar to Ramulator, the original version of Ramulator. And you can see it highlighted in here, and we can change the DRAM device independently from the rest of the system. How we actually model DRAM is like this. We have a hierarchical state machine-based modeling of DRAM. Here you see a graph, and each node in this graph is an organizational level of DRAM. So for example, we have channels, and under channels we have ranks, and under that we have bank groups, and all of these nodes are connected to each other by their organizational relationships. And each of these nodes also have this information of the state of that DRAM node, which could be the current state of the node, sorry, such as open, close, activating, and so on. Or it could have timing constraints like the earliest time in the future that each DRAM command is allowed to be issued to that node. And we also have some information about the energy and power modeling, which then can be moved to the DRAM power model, and then we can make estimations based on that. And these could include like time spent on each state for these DRAM nodes, or the number of commands that are served. And this can be extended for other information. If you want to keep track of other things, you can do using the state of a DRAM node. DRAM commands are implemented as lambda functions that hierarchically traverses this graph that I showed you before and updates the states of these nodes. And I will not go into too much detail here, but basically we go one by one for each DRAM command based on their definition and update the states. For that, we use template library of generalized DRAM command lambda functions that allows reusing the command implementations across different DRAM standards. As you can imagine, a lot of these functionalities are common across different DRAM standards. Here you see an example of a function that is named require all banks closed, which just checks the state of the DRAM banks and sees if they're closed, and if they're not, it just precharges the bank. And this keeps the code clean, and then we can reuse a lot of these functions that are already defined, already tested, and also it helps us quickly create new DRAM standard models. There are more details in the paper, and we will cover some of them also, but you can check it out from the paper here. And we have, so Ramulator 2 is open source, of course, and we have a more detailed user guide and documentation available on our GitHub repository. So we validated Ramulator 2 in 2 ways. First, we validated the DRAM command traces against Micron's DDR4 Verilog model across streaming and random access patterns with varying memory intensities, and we found no timing or state violations. And the second validation came a bit later, which was a bit unexpected. But we basically, I will talk about this a bit more in detail in the next session. So a micro-based paper runner-up publication titled A Mess of Memory System Benchmarking, Simulation and Application Profiling proposes a new benchmark to evaluate the real and simulated memory system performance. And while doing so, it also made some strong negative claims about 2 of our simulation infrastructures, including Ramulator 2, and showed unexpected results, contending that they poorly resemble the actual system performance. And in one of our recent works that was published in ISCA this year, we demonstrated that these claims and results are incorrect, and they were due to configurations and simulator usage errors made in the MES paper. We then described 4 best practices, which we will cover to aid users and developers of simulation tools. And we open sourced everything to enable reproducing. And these were the key results. So as you can see here, which I will go into too much more detail later, when correctly configured, Ramulators simulated memory system performance resembles real system characteristics. And there are more information about that in the paper. Again, we will cover them in the next session. Moving on to the integration with other simulators. So it is because of this modular and extensible software architecture of Ramulator 2, it is possible to pack Ramulator 2 into a library, and we can change the front end from, for example, our simple O3 front end to Gen 5 front end, or have your favorite simulator, for example, ChampSim. And this enables easy integration into other simulators to support detailed memory system simulation coupled with detailed system simulation or core model simulation. And we used a couple of these integrations in our recent research works, and also some other works from other groups also use these integrations. One of them is this micro paper that was published last year, which combined a more detailed core model with Ramulator 2's detailed memory system simulator using Gen 5 and Ramulator 2 integration. I will again hopefully cover this later, but in this work, we integrated Ramulator 2 with Gen 5, and we studied the side and cover channels, leveraging the 2 latest industry solutions to Rowhammer. So introducing these mitigations into the system also opens up some vulnerabilities when we think about timing side channels. And this is the infrastructures that we used for studying this. It is also possible to integrate Ramulator 2 with Virtuoso to enable simulation of virtual memory functionalities. And the paper from Aswells also uses this to show some nice results. And we also had a workshop that we showed the use case enabling swap space studies with Ramulator 2 coupled with Virtuoso. And you can watch it from this link. And there are even more integrations that are coming from the community. So for example, this ISCA 2025 paper integrated Ramulator 2 with ChampSim as a core model, and also used it as a memory system security infrastructure. So let me talk about the impact of Ramulator 2, future work, and conclusion. And Ramulator 2 has already enabled many works, and even this slide is a bit outdated. I need to update it. But we are happy to see that people have used it a lot and liked it. And we have been working on a lot of new functionalities for Ramulator 2, which ended up creating this new version, Ramulator 2.1, which we will cover in a second. So this version fixes almost all bugs that are identified by GitHub issues and by our internal use. And it adds a lot of nice functionalities. And we are happy to get contributions from the community, especially we are interested in getting like more integrations with other simulators. and adding more DRAM standards and emerging memory technologies, more timing, DRAM timing presets. For example, for HBM, this is very difficult to get. And we would love to support who wants to use it and help if there are any issues and so on. And this concludes this part of the talk. For now, I will leave it at that, but I would be happy to take any questions. Maybe not this time, but yeah, I would be around, so I would have to chat. Yes. Yeah.
Yes. Try what? I cannot try it. I can turn it off and on again. Do you know which mic it was?
Maybe I can just speak.
Oh yeah, I think it's this one.
Okay. Can Zoom hear us? I think so, yeah. It's good to go?
Yeah.
Okay. Yeah, hello, everyone. Thanks for waiting. I'm here to introduce Ramulator 2.1, a major overhaul of Ramulator 2. In this version, we fixed a lot of bugs identified by prior GitHub issues. We thank all the contributors and our internal testing. And we provide more comprehensive support for newer DRAM standard and controller features. And we introduce a more comprehensive set of tests and validations. And we significantly improve the ease of use, configuration, and extension. And we also improve the overall code quality and the documentation coverage. So the GitHub main branch of Ramulator 2 is already updated to match v2.1.0. And we also configure it to be one-click ready with code space and dev containers. So you can just like one-click and try in your browser. And we also archived the existing v2.0 as the legacy / v2.0 for archival purposes. And of course, we welcome your use, contribution, and feedback. You can use the issues and discussion features on GitHub and OpenPRs. So now let's take a quick look at what are the key bug fixes and new features. So currently, Ramulator 2.1 models a wide range of DRAM standards, DDR345, LPDDR5.6, GDDR6.7, and HBM1234. And the current modeling scope and the prioritized implemented features, they focus on the timing and functional simulation of DRAM commands. And we focus on the commands that matters for implementing load stores, refresh, and redisturbance mitigation. So currently for those like self-refresh, power down, they are not on our prioritized list. And of course, for the newer DRAM standards, because they show like a split between high frequency and low frequency operation in terms of commands, timings, and organization. And for now, we choose to prioritize those high frequency ones. And we also fixed a lot of bugs identified from GitHub issues, like the HBM organization time and throughput, and some LPDDR5 timing. And together we have better support for newer DRAM standard and controller features. We have the HBM controllers that supports pseudo channels, row column commands, parallel issue, and the clock edge constraints for HBM3+. For LPDDR5.6, we properly support the WCK sync commands that with explicit expiry state tracking, and of course the split of activation into ACT 1 and 2 with the deadline aware scheduling. And for GDDR7, it's basically a combination of some of the LP5.6 features plus the row column commands dual issue. And also, all of these are powered by an improvement to the scheduler implementation, where we allow adding customized filtering logic in the form of lambdas to, let's say, baseline generic FRFCFS that significantly simplifies the implementation of many of these controller features. And we also enhanced the memory controller plugins protocol. So now it's a standardized and modular interface that allows very flexible extension of the functionalities of existing memory controllers. So the contract looks like this. You can specify how your plugin will work before the scheduling of the a request, what it will do upon an issue of a DRAM command, and what it will do when, let's say, everything has finished. So this enables very easy plug and play implementation of utilities, like you can use it to dump DRAM command trays that you may feed into DRAM power, etc. And we implement a wide range of row hammer mitigations, all in the form of very flexible memory control plugins. And for the test validation, we formalize 3 automated test and validation workflows. First, we have some quick tests to see if your recent changes break anything. We also have a low-level verification of DRAM timings and controller scheduling. And also, as a high-level validation of memory system performance, you can just generate latency and throughput plots very easily for the DRAM standards that are modeled. So here's an example of how you can write your customized low-level test for DRAM commands and testing. You initialize a DRAM under test, then you can probe it with specific command, address, and timings, and then you can check whether the timings are ready, whether the prerequisite command has been met, etc., and you can assert them to form a test. And of course, you can write longer traces that test more complicated combinations of the commands at different timings. All of these are under the GitHub repo. You can check for examples and some more advanced test cases that we have. And for the latency throughput plots, so we have a set of scripts that can automatically sweep different, let's say, memory system load by sending streaming requests with different intervals between them, and probe the memory access latency with a random access probes. And altogether, this provides a very easy high-level way of eyeballing or validating some key memory system performance metrics, like whether you can achieve the maximum throughput or is your unloaded latency reasonable. And here we show that for all the DRAM standards that we model, the shape of these latency throughput curves, I mean the shape of the knees, they match what we expect from like such systems, and we can reach the maximum throughput, and the smallest unloaded latency also makes sense. Next, we have some quality of life improvements. Now, Ramulator is a Python package. It's essentially still your C++ code, but we have Python bindings for them. And this enables very simple, flexible Python-driven configurations. You can configure your simulation, execute your simulation, parse the results, plot all of them in one single script. And because it's Python, you can just flexibly sweep all the parameters, override whatever timings, just a for loop. And it's also Gem 5 friendly, like it's just like drop in for Gem 5. And we also provided a tested integration wrapper that we verify that both SC and FX works out of the box, and it's also compatible with the Gem 5 board features, which we tested with like the very recent version of Gen 5. And all of these comes at no extra burden of the user. So still, we have a single source of truth implementation. You don't manually write this wrapper code, but they are automatically generated by our software framework and the build system. So you don't have to worry about how to write the Python wrapper, how you bind your code to Python. All of these are handled by us. And of course, if you want to integrate Ramulator 2 with your own simulator and you don't want to introduce the Python dependencies, we also provide a utility that you can just export the Python-based configuration to a 100% equivalent YAML file that Ramulator can also accept. By doing that, you can still benefit from the same Python configuration without introducing Python dependencies in your own project. And so the overflow of adding new components with Python bindings is very simple. You still write your code in C++, and you just have to register your interface implementation and the parameters that you want to be recognized by Python with our macros like register interface, register implementation, parse certain parameters, specify the hierarchy of your components, which objects are the children of others, etc. And our software framework and the build system will automatically pick everything up, and it understands, registers, and build the object hierarchy of your interfaces and implementations, and also create Python wrappers or proxy objects with the specified parameters as being the class members. So all of this happens automatically. And also with Python, we implemented a very flexible and easy way to author the DRAM standards directly. So this replaces the still relatively verbose and hacky C++ DRAM specifications in 2.0. Now it's much cleaner and much more readable, much shorter with the Python scripts. So this enables very flexible authoring of DRAM organization, commands, timings, because we have this scriptability of Python. And our code generation utility automatically converts these user-friendly Python scripts into the low-level, relatively verbose and contains a lot of hacks C++ implementation that fits the Ramulator 2's internal modeling and simulation engine. So here's what the Python-based specification of DDR5 looks like. Essentially, you just write a bunch of Python lists and dictionaries. And here's a very user-readable way of specifying timing constraints. So you just specify first at which level is the timing constraint, what are the preceding commands, and what are the following commands, and what are the name of these latencies. And it will automatically generate the Cartesian product of the timings constraints between the preceding and the following commands. And of course, with Python, we can just parse these, let's say, expressions like plus, minus, etc. And by doing these things, we significantly reduce the lines of source code needed to model DRAM standards. So this table compares the standards that exist both in 2.0 and 2.0, and we can find that with this flexible Python layer, we can save about like 66% of the lines of source code. And this also enables a very easy extension of DRAM standards. Let's say if you just want to add a new DRAM command, which has a little bit of extra timings that comes with it. So in 2.0, you have to just manually duplicate the entire standards. It's like you just increase your risk surface. You have more duplicate code to maintain. But now with Python, what you do is you inherently just inherit the base DRAM standard, and you just append the new commands and timings to the base DRAM standard. Let's say here you want to add a new command foo to DDR3, then you essentially just create a new Python class, DDR3 foo, that inherits from DDR3. You give it a name, and then you just append the command foo to the supported command list of your base class, and you also append only the new timings that you need. So this also significantly simplifies a common use case in research where you want to add some new DRAM commands. Yeah, and also we introduced a web-based interactive DRAM trace visualizer to help you do performance reasoning, debugging, or analyze the memory system bottleneck of your workload. It supports both offline visualization. You can finish your simulation, dump the command trace file, and view it offline. It also supports online visualization, so you can just see the commands being real-time visualized as your simulation runs, which is very helpful for debugging. And you can use this to inspect both the memory request. You can see how long has the request been queued in your memory controller, as well as individual DRAM commands, address, and timings. And we optimize the performance that you can view like several hundred megabytes of trace interactively on like an Apple M1 laptop. And it looks something like this. If you're interested, the last section of our README in the GitHub repository contains the tutorial on how to use it. And we welcome your contribution to Ramulator 2.1. So now it's already released on GitHub as which replaces the old 2.0 on the main branch. And we, for now, for the ease of integration with other simulators, we will also be tagging our major updates. And please check it out. And if you have any issues, please let us know through issues and PRs. We will be regularly checking and addressing them. And of course, the earlier 2.0 version is archived as the legacy/2.0 branch. And you can use it, report issues, add new features, add more tests. These are all very welcome, and check our detailed README and rich in-source documentations on how you can use, extend, and integrate Ramulator 2.0 with your other simulators. And here are some example directions that you can contribute to Ramulator 2.1. So first, if you have better sources of timing standards, we are very welcome that, because some of the more recent DRAM timings, the manufacturers, they don't publicly release the timing constraints. So we do our best to provide guesstimates for them. So if you have better sources without breaking NDA, please contribute. And we welcome more DRAM request scheduling techniques, redisturbance mitigation techniques. All of them should be relatively easily implemented with our new controller plugin and scheduler filter features. And of course, the next step would be implementing more intelligent scheduling of refresh, as some recent works reverse engineer the real DRAM controller. Real DRAM controllers, they may have dynamic choice between all bank refresh and finer grained refresh that targets individual banks based on the current load of the system. So that this can be a very useful addition to further, let's say, match what we get from simulator to, let's say, specific real chip. And of course, to the mid and longer term, processing using DRAM and processing near memory support is something that we definitely want to have. And of course, if you want to integrate it with your own simulator, we are very welcome. And of course, if you want to work on any of these, please first open an issue or a discussion thread so that we can coordinate and avoid potential overlapping or conflicts with our ongoing internal development. And here's the end of my talk, and I thank all the current contributors, and we hope you will join the list. Yeah, thank you very much. I'm happy to take any questions. Yeah, please. Maybe you can say again with the mic. What of the visualizer? Effectiveness. We don't have like a very concrete specific case yet, but let's say one use case would be that. So our visualizer supports a feature that you can visualize the command bus and data bus utilization in a line chart. So you can immediately spot where am I being bottlenecked by maybe data bus, command bus contention. And when you see like a drop in data bus utilization, you can go there, zoom in, inspect. Am I having a lot of row conflicts? Am I correctly distributing my request across different band groups? Or you can also use that to visualize how different refresh scheduling mechanisms may collide with your normal access streams. So these are the very concrete use cases that we can think of now. We haven't done like a concrete study yet. Yeah. Yeah, thank you. Yeah, of course, yeah. Yeah. Yeah, yeah. Yes, because it's not like a relatively old standard, so it may not be on our like priority list, but we can talk like if you have some need for it, we can see if we can implement that. Yeah, so as of now, because I think maybe we can see that we have some ongoing work on power characterization. So maybe in the future, you will see like an updated power model compared to DRAM power from us. But as of right now, you can use the memory controller plugin feature to write a plugin that dumps the memory command trace in the DRAM power format that you can just feed into DRAM power. Yeah, in the future, power modeling is definitely like one of the major midterm goals, I would say. And we aim to have better power modeling backed by real device characterizations. Thermal, yeah, I haven't fully thought about thermal yet, but I agree it can be a very good addition, especially when people are talking about stacking DRAM over logic. That can be a very good addition. Yeah, and of course we welcome your contribution if you have any contributions. Yeah, thank you. Yeah.
Things about emulation in general.
Okay.
So the question says, does this support dynamic address mapping? Suppose someone wants to use different address mapping for pin versus non-pin mapping, but emulate model that.
Yeah, of course. So because everything is modular, you can implement whatever dynamic address mapping scheme you have. And we already have like a row hammer mitigation, like randomized row swap, that somehow has similar features that you have to reserve part of the rows. So like, yeah, like it's implemented by in the address mapper that for some of the requests, it gets mapped to this group of rows, some of the other requests gets mapped to other group of rows. So if you look at the RIT mapper in the current address mapper directory, that should be a very good inspiration and example on how you can implement that.
I'll ask one question also. How is the performance of Ramulator 2.1 and 2.0?
So I haven't fully benchmarked it yet. But I can say confidently that the Python thing does not add overhead because all the simulation still happens in C++. And we have plans to optimize the performance of Ramulator 2.1 from two directions. The first is more like software engineering and modeling methodology side. Let's say for now, for some of the more modern DRAM standards like HBM3, they can send requests on both the rising and falling edge of the clock. And there are also some like command pairing rules with respect to row and column slots, and also the rising and falling edges. So for now, for maximum flexibility, we essentially model like half clock, like we treat every falling or rising edge as a clock unit. But maybe there can be optimizations that we can just co-design the command coupling rows together with this row and column bus, so that we can go back to like one TCK modeling that should immediately cut all these simulation cycles by half, but we're still actively investigating it. And the second is to, maybe it's a more longer term goal. Like we should, as many people are talking, should rethink about how we do memory system simulation. So maybe there can be a, let's say, combination between accurate fine-grained cycle level modeling and the, let's call it, real-time-ishness of like the immediate response latency model. So these are the directions that we are looking into.
That's very good. I think one last thing is it may be good to have, maybe you already have this, but maybe you have a wish list of items that people can contribute to.
Yeah,
maybe if you can point people.
Yeah, I think probably this is like our current wish list.
Can people find this on GitHub?
Not yet, but I can just paste this on GitHub.
Maybe useful to do that, because some people may want to contribute.
Yeah,
who knows? Maybe even some DRAM manufacturers will help us. I have to pick on them, you know. Who knows? Yes. They may be inspired if they see your list, you know.
Okay.
No, actually, in all honesty, we would like to.
Yeah, you can also contribute to the list, you know. That's also fine. Yeah. Okay, I'm done. Thank you.
Yeah, thanks. Just maybe
so we're done for the morning sessions. We'll continue in the afternoon with more invited speakers, more me falling down, and I think more Ramulator, exciting content about Ramulator. Put it that way. So I'll see you in the afternoon, I hope. And even after then, the last afternoon session, we will have both DRAM Bender and Ramulator hands-on tutorials planned for you. So we hope to see you there. Enjoy your lunch.
Oh. Me too. Me. Yes. Okay. I think the microphone is also working. Hello? Yes. Yes. Ah, thank you. Thanks. Okay. Okay. Maybe we can get started. I hope you enjoyed the lunch, and now we're back with more research highlights about on Ramulator, and also we will have very interesting talks from invited speakers. Okay. So the first work that I will talk about, I highlighted a bit during the introduction. It is called Cleaning Up the Mess, Reevaluating the Real System Model and Accuracy of Ramulator 2.0. This was a work that we had done with like great efforts from all the authors that you see here, Haocong, Ataberk, Maria, and we led this work in order to show a great comparison of Ramulator's memory system modeling accuracy compared to real systems. Okay, so cycle-level DRAM simulators provide accurate and flexible models for DRAM and memory controller operations, and they enable research on current and future memory systems, as we covered so far. If you want to study, for example, DRAM performance and latency or solutions for robustness issues and emerging architectures, these simulators are very important and critical to enable these works. So it is critical to have these tools for improving the performance, efficiency, and robustness of memory systems. A Micro 2024 best paper runner-up publication with all 3 artifact badges titled A Mess of Memory System Benchmarking, Simulation, and Application Profiling, which we call the MESS paper, proposes a new benchmark to evaluate the real and simulated memory system performance. While doing so, it also makes some strong negative claims about 2 of our simulation infrastructures, Ramulator 2 and DAMU, and shows unexpected results, concluding that these tools poorly resemble the actual system performance. In this work, we demonstrate that these claims and results are incorrect and are due to configuration and simulator usage errors made in the MESS paper. We describe 4 best practices to aid users and developers of simulation tools to avoid such issues in the future. To facilitate transparency and reproducibility, we open source all our code and results in this GitHub repository, and you can check it out and reproduce all the results. To demonstrate that these results and claims in the MESS paper are incorrect, we first analyze the evaluation of Ramulator 2 and DAMU in the MESS paper, and then describe these best practices for these tools to avoid such issues. Now let's talk about our analysis of the evaluation of Ramulator 2 in the MESS paper. Ramulator 2 is again, we covered this, a modern and modular extensible DRAM simulator. It models a wide range of DRAM works, and it is open source and freely available on GitHub. The MESS paper evaluates memory system performance by proposing the MESS benchmark. The MESS benchmark aims to characterize a memory system using a set of latency throughput or used bandwidth curves. These curves are plotted as a line figure, where each data point is an experiment that performs 2 types of memory accesses concurrently, streaming and pointer chasing patterns, and plots the measured average memory access latency and the used memory bandwidth. The MESS benchmark then varies the memory intensity by adding knobs between subsequent memory requests, which creates a single curve, and evaluating a sweep of read to write operation intensities from 50% to 100% reads creates different curves. The MESS paper comments on the accuracy of the Ramulator 2 by first evaluating a real DDR5 memory system with the MESS benchmark, and these are the results. Then compares these curves in this figure against the Ramulator 2 curves that they obtain. The MESS paper observes that Ramulator 2's curves show first a smaller used memory bandwidth and 2, smaller memory access latency compared to the real system measurements, and contends that Ramulator 2 poorly resembles the actual system performance. However, Ramulator 2 results in the MESS paper are incorrect, and at the time of the publication, they were also irreproducible. We analyze the MESS paper and its open source artifact and identify various issues categorized into 3 classes. First, it was not possible to reproduce any of the Ramulator 2 results from the MESS paper's artifacts available at the time due to the missing source codes. The missing source codes were uploaded only after our contact, and this was after 10 months after the artifact evaluation has concluded and awarded them the badges. Second, we identified Ramulator 2's evaluation suffers from fundamental configuration errors, as the MESS paper compares an 8-channel memory system in Ramulator 2 against a 16-channel real memory system, and configures the system to have unrealistically low cache latency configurations that lead to a low memory access latency. Lastly, we also identified scholarship issues, as the paper does not disclose these modifications to the source code of Ramulator 2 and differences in the evaluation methodologies of real and simulated memory systems that we will not cover in this presentation, but they are explained in detail in our paper. The MESS paper's configuration errors result in incorrect claims about Ramulator 2. Now I will describe how they lead to smaller bandwidth and smaller latency. First, the smaller used bandwidth results are caused by the difference in numbers of channels available in simulation and in real system evaluations. The MESS paper's Ramulator 2 configuration specifies 8 channels with something like this line that you see here, and the paper specifies the real system configuration as 8x DDR5. This leads to Ramulator 2 instantiating 8 independent DDR5 channels, whereas the real system configuration has 8 DDR5 DIMMs, each of which containing 2 channels, meaning that there are actually 16 independent DDR5 channels in the MESS paper's real system configuration. And because of this mismatch, Ramulator 2 results in the MESS paper show around half the used bandwidth of a real system measurement, as it has half the number of channels. We identify that this is because the MESS paper incorrectly assumes a DDR5 channel in Ramulator 2 as 64 bits wide, whereas the implementation clearly states the channel as 32 bits wide, which is the consistent value with the JEDEC DDR5 standards. Because of this configuration error, the MES paper configures Ramulator 2 with half the channels of a real system, and thus results in smaller used bandwidth. The second issue, smaller memory access latency, is due to the unrealistic cache latency configurations. The MES paper's artifact hardcodes the cache latency as 0 cycles and instantiates a high number of misstatus holding registers. And this configuration leads to significantly smaller DRAM round-trip latency and queuing delays, thus a low memory access latency compared to a real system. So the MES paper uses this unrealistically low cache latency configurations, resulting in the low memory access latency that it attributes to Ramulator 2. To this end, we independently evaluate the MES benchmark by executing the same access pattern and configure Ramulator 2 correctly. And we instantiate a 16-channel DDR5 memory system and measure the memory access latency from the memory controller. I will now show you our key results. On the x-axis here, we see the used memory bandwidth, and on the x-axis, we see the used memory bandwidth, and on the y-axis, we see the memory access latency. We show the maximum theoretical bandwidth as the yellow line here, and since this does not account for periodic refreshes, we draw a second line to show the maximum achievable bandwidth that accounts for periodic refreshes. And these are the results. We make two key observations. First, Ramulator 2's memory model achieves a high used memory bandwidth, close to the achievable bandwidth value as opposed to the claims in the MES paper. Second, the memory access latency of Ramulator 2's DRAM model increases as the used memory bandwidth and the write ratio increases. We conclude that when correctly configured, Ramulator 2's simulated memory system performance resembles real system characteristics. Now let's look at the analysis of the evaluation of the move in the MES paper. So we did not talk about the move, but the move is another tool that we developed, which integrates ZSIM with Ramulator, the first version of Ramulator, which enables evaluating emerging processing in memory architectures. The MES paper evaluates a real DDR4 system as shown on the left side here. And for the move, the MES paper's results are on the right, which shows a constant memory access latency. We identify that the move results in the MES paper use wrong simulation statistics that are unrelated to the simulated DRAM performance. We analyze the MES paper and its artifacts and identify two key issues. First, we could not reproduce any of the demo results in the MES paper due to the missing source code and configurations in their artifact. Second, we identify that MES paper scripts use statistics from ZSIM and ZSIM to calculate the memory latency, but these stats are not related to the DRAM latency modeled by the Ramulator side. So due to these issues, we independently evaluate the move by executing the MES benchmark and by adding missing resources in a best guess manner. And here are our results. This plot is again similar to the ones I showed you before, and we observe that when correct statistics are used, the move's memory access latency is not constant, in contrast to the claims in the MES paper. There are even more details and analysis in the extended version of our paper on arXiv, and you can access it from this link. And cleaning up the MES is open sourced and artifact evaluated, and you can check it out from here. Lastly, based on these analyses, we identify best practices for Ramulator 2 and the move. To avoid such configuration and usage errors, first, the users should be familiarized with JEDEC standard documents. Second, they should understand the simulator's memory organization and configurations. And these two best practices would help avoiding the Ramulator 2 configuration error in the MES paper. Third, the users should understand simulation methodology and simulator implementations sufficiently to use the correct statistics. And this would help avoiding the statistics usage error that we see in the MES paper regarding the demo results. Lastly, the users should communicate with the simulator developers or the user community when unexpected results are observed to ensure correct simulator usage. And this best practice would help avoid all errors in the MES paper. Now, let me conclude this part of the talk. A recent paper from Micro 2024, a mess of memory system benchmarking, simulation, and application profiling makes strong negative claims about Ramulator 2 and DOMU and shows unexpected results. We demonstrate in this work that these claims and results are incorrect and are due to the configuration and simulator usage errors made in the MES paper. We strongly encourage the computer architecture community to consider our corrections to these results regarding Ramulator 2 and DAMO in the MES paper, and to prevent the propagation of inaccurate and misleading results. To facilitate transparency and reproducibility, we open source all our code and results in this GitHub repository. And this concludes this part of the talk. I would be happy to take any questions.
I'll ask a question.
Sure. Go ahead.
Okay. Okay, thanks for clearly I know what happened in this area, but when the normal practice in scientific community, when something wrong is found in someone's paper, is for the author to correct the results using errata or some other way.
Mm-hmm.
Did the MES authors correct their results?
No, and to our knowledge, there's no plan that we know of to correct these results apart from the paper that we submitted, and it is published in the SPAS.
Okay. I think scientific community should really be careful about ensuring that results that are proven to be incorrect should be corrected. And I will say that this paper comes from two institutions. One of them is a DRAM manufacturer. And I think that DRAM manufacturers should be more careful in putting their names on such papers. If they want to collaborate on good papers, good scientific work, there are other people to collaborate with. Sorry. Part of the scientific record.
Okay, then I'll move on to the other research highlights that we want to talk about today. So one of the use cases that we see that is being one of the use cases that we see for Ramulator 2 is the raw hammer mitigation evaluation papers. So we already talked about supporting a lot of mitigation techniques as plugins. And the use case actually starts with the Ramulator 2.0 paper. So in this paper, we look into the performance overhead evaluation of different raw hammer mitigation techniques. And we evaluate 6 different raw hammer mitigation techniques, all implement these plugins to the same memory controller implementation. And what we show is that as DRAM becomes more vulnerable to raw hammer, evaluated raw hammer mitigations incur higher performance overheads, directly motivating more research to be done in this area. And after this paper was published, there was a very exciting improvement in the DDR5 standards that we see. So this was the introduction of a mitigation technique, a mitigation framework to the DDR5 standard. There were many before also, not many, but TRR and RFM namely. But this time, the standard included some per-row activation counters in DRAM. And we were very excited to see, test it, and see like the performance overheads, security implications, and so on. So we did this study. Basically, in here, in understanding the security benefits and overheads of emerging industry solutions to DRAM read disturbance work, which was published in DRAM Sec in ISCA in 2024, we looked into the different designs of this framework, different implementations of this framework, and we evaluated the performance. So here you can see the results of state-of-the-art, at the time, state-of-the-art mitigation techniques, and also per-row activation counting as we implemented as described in the standard. So we extended the memory controller implementation with the support for per-row activation count tracking and the backup signal, which is a way for DRAM to request time to do preventive refreshes. And we compared this mitigation implementation against the state-of-the-art mitigations. And we show that PRAC introduces non-negligible performance overheads due to increased DRAM timing constraints. And after that, we wanted to even go further and improve this baseline that we had. Based on that, based on our analysis, we developed Cronus, understanding and securing the cutting-edge industry solutions to DRAM read disturbance. And here we analyzed the 2 major drawbacks of PRAC. First, the increased critical DRAM timing parameters, which results in large performance overheads, even at high read disturbance thresholds. And then the second drawback was the wave attack vulnerability that requires aggressive configurations to prevent. And we show that this leads to poor scaling to low read disturbance thresholds. And Cron's key idea was to first concurrently update counters while serving DRAM accesses. This would then lead to no increase in critical DRAM timing parameters. And the second key idea was to prevent wave attacks by providing DRAM chip with more control over backups and preventive refreshes. And then this leads to better scaling to low read disturbance thresholds. We evaluated the Cronus with Ramulator 2 by again extending the plugins and implementing Cronus. And we show that Cronus reduces the performance and energy overheads of Prague and outperforms at the time the state-of-the-art solutions. And this is the paper, and you can check it out from here. And again, like in this line of work, another recent work that we did, which I talked about a bit, is called Understanding and Mitigating Covered Channel and Side Channel Vulnerabilities Introduced by Rowhammer Defenses, which was published in Micro 2025. I will quickly go over these, but in the interest of time, I will be very quick. But I would love to hear your thoughts and answer any questions if there's time or offline and so on. So modern computing systems are vulnerable to security attacks such as covered channel and side channel attacks, where an attacker uses the shared computing system to communicate with another attack process or to leak security critical data of concurrently running applications. And a set of these attacks exploit shared hardware structures that result in different execution time for executing a type of operation based on the input or the current state of the shared structure. This means that timing differences leak information. Now let's take a closer look at these computing systems. Here is our typical DRAM-based computing system with a CPU and a DRAM module connected with an off-chip link called the DRAM channel. We talked about read disturbance. Unfortunately, DRAM is vulnerable to read disturbance, which breaks memory isolation. And a prime example of this is Rowhammer, where repeatedly opening and closing a DRAM row causes Rowhammer bit flips in nearby cells. Unfortunately, as with technology node scaling, DRAM cells get smaller in size and get closer to each other, such that we observe significant reductions in the minimum memory count in this first bit flip in the last decade. So DRAM cells become increasingly more vulnerable to read disturbance, requiring low-cost defenses. To address this need, to mitigate these bit flips, recent DDR5 specifications introduced two new defense frameworks to mitigate Rowhammer bit flips. The first one is what we talked about, per-row activation counters, or PRAC, which introduces per-row activation counters inside DRAM to track aggressive rows activation counts. And the second one is called refresh management, or RFM, which is a command to provide DRAM with the time to perform preventive actions. The industry has already standardized multiple Rowhammer defenses to mitigate read disturbance bit flips. However, their full security implications are not known. This brings us to the question, do industrial and academic Rowhammer defenses introduce new covered and side channel vulnerabilities? And in this work, we show that the answer is yes. We make the key observation that Rowhammer preventive actions have two fundamental features that enable covered channels and side channels. First, these actions often result in high memory access latencies for regular memory requests, such that when DRAM is doing these preventive actions, it becomes unavailable, and all other requests needs to wait for a long time, which they experience higher memory access latencies. And the second feature is that a user can leverage memory access patterns to intentionally trigger a preventive action and make DRAM unavailable, such that, again, all other requests experience higher memory access latencies. So based on this key observation, we introduced leakhammer, which is a new class of attacks that exploit Rowhammer defense-induced memory latency differences. And the key idea of leakhammer is to first deterministically and intentionally impose observable large latency overheads on requests with preventive actions, and second, accurately infer victims' memory access patterns that result in preventive actions by just observing the memory system. We demonstrate three different attacks as case studies of leakhammer. We first established PRAC and RFM-based covered communication channels. Again, these are the two state-of-the-art industry solutions. And then we demonstrate a website fingerprinting attack that leaks which website is accessed by a victim user by observing the preventive actions that are caused by the victim. I will not, again, go into too much detail, but let me quickly recap the first case study. I will talk about proof of activation counting at a high level. So what proof of activation counting, or PRAC, introduces is the proof of activation counters inside memory that accurately tracks activation counts of each row. This means that when we activate a row, that counter is incremented, and until it reaches a threshold that is called the backoff threshold. When the counter reaches that threshold, the DRAM identifies this row as an aggressor row, and this means that it requires a preventive action and sends a backoff signal back to the memory controller side. And after that, after receiving the signal, the memory controller sends an RFM command, which allocates a fixed time for preventive refreshes to happen. And at this time, DRAM becomes unavailable, performs preventive actions, and then it becomes available again after this time ends, and the memory controller can send regular requests again. To exploit this for an attack, we first need to verify if we can observe these latencies from user space applications. So we test if an application can intentionally trigger this and observe PRAC-induced higher memory access latencies. And to do so, we construct a routine, which I will not go into too much detail, but we activate two rows in an interleaved manner, and hopefully increment their activation counts. We measure the memory access latencies of this routine, and here on the x-axis we see the memory request, and on the y-axis we see the latency values measured, and here we see the latency values. So we empirically divided the values that we see for the latency from PRAC backoffs to periodic refreshes and to row buffer conflicts as shown here. What we see is that we can identify these preventive actions or backoffs because they introduce a high latency in this graph. And the observed backoff latency is consistent with the specification and can be distinguished from regular memory operations such as periodic refreshes or regular accesses. And this means that we can exploit it for an attack. Based on that, we construct a covered channel where a sender and receiver exchange messages using the shared DRAM bank. They start by allocating different rows. They do not share actual data, and they agree on a transmission window length. And during that, they know only one bit will be transmitted. They also agree on an encoding for this message such that a logic 1 value will be transmitted with a backoff. And after that, the receiver can start measuring access latencies within a loop to get a trace of this latencies during a transmission window, and can use this trace to determine the bit value transmitted by the sender. To send a message, the sender needs to, if it's a logic 1 value, the sender needs to create a backoff based on the encoding. And to do so, the sender accesses on DRAM row, which creates conflicts with the receiver, and both of their activation counts increase. And this leads to one of the activation counters to reach the threshold value. At that point, the DRAM sends a backoff signal, creating a high latency overhead for all other requests. And after this, by measuring this high latency, the receiver can detect the backoff and say that, okay, I received a logic 1 value. And to send a logic 0 value, it is very simple. The sender does not need to do anything and just sleeps throughout the transmission window. And the receiver's activation counter is not increased due to lack of conflicts. And the receiver does not measure any backoff, and therefore can understand that the bit value was logic 0. And they continue these steps to send the full message. We evaluated this proof of concept attack and measured the channel capacity. Here you see a proof of concept that transmits the micro message. And what we observe is that the receiver can successfully decode the sender's message, and this attack achieves 39 kilobits per second raw bit rate. And then we evaluate how it performs with system level noise by introducing more noise in the backoffs that we see in the system. We also do another study with real-world workloads running in the background, and we see that this covered channel attack maintains its capacity until very high noise intensity values. I will skip through the other attack, but it is very similar, but the underlying mitigation is RFM-based instead, and you can find more details about it. And for this side channel attack, we did a website fingerprinting attack where an attacker can detect which website is loaded by the victim by just observing the latencies in the same channel. And to do so, the attacker first needs to create a fingerprinting approach. And to do so, it measures the memory access latencies throughout an execution time and creates a trace similar to the receiver's trace. And then we create fingerprints using backhoes for many websites. And for each website, we get many fingerprints to build a database. And based on that, we can launch the attack. And whenever the victim loads a website, we can correlate that fingerprint and compare it to our database and understand which website is accessed. So we evaluated this with 40 most visited websites, and we used machine learning approaches to classify these websites. And we only use simple and lightweight machine learning models at this step. We showed that it's possible to classify websites with up to 75% accuracy. And next, we discussed and proposed and evaluated 3 countermeasures, which I will not go into too much detail here, but you can find them in the paper. And Leakhammer is also open source and artifact evaluated, and you can check it out from this link. And this concludes this part of the talk, my part of the talk for this session. Thank you so much for listening. I would be happy to take any questions. Okay, so let me switch. Question?
Thank you for the presentation. I think that's pretty.
Not for. It's just for recording. Can you?
Oh,
please-
okay. Okay. I'm curious what you think about this for the. I don't know if that's working. For PRAC in particular, when you're looking at the alert backoffs. I understand your perspective on this because you're basically pushing a meltdown respector into DRAM. It's effectively what you're doing. So you have some data dependency where you have a time varied access delay and you're able to arbitrarily filter data. One thing that is interesting is, have you looked at conditions where you can do that possibly without triggering the alert pin? Because if I'm a system integrator, what I'm going to do, once I see the alert pin go up, I mean, I don't know what the companies will do, but they might blacklist, the user, whoever is accessing, whatever process ID is accessing that one, and just kick it off. Mm-hmm. And if that's the case, then it may be harder to pull off an attack like this because you get blacklisted every time you trigger it, which you can still do. It just would take longer. Have you considered that at all?
Yeah, so in the paper as well, we actually evaluated or analyzed a lot of different mitigation techniques that do not require backhaul, for example. So the underlying timing leakage comes from the latency itself first. Basically, if you're doing a preventive action, which could be a refresh or a migration or something, if the DRAM becomes unavailable, and if it's observable from user space application, there's some timing leakage coming from that. There are some mitigations that, for example, overlap the latency of preventive actions with, for example, periodic refreshes like TRR. So if that's enough, meaning I will explain it. If that's enough, if the user cannot observe the latency, then there's no leakage and the attack cannot be successful. That is difficult because what prior work showed is that because of the vulnerability level that we see today, we cannot be bounded by the periodic refreshes. So we cannot overlap all of them, all of the preventive actions with periodic refreshes. So that sort of mitigation that is reacting to the user's memory access pattern will leak some information. But as you mentioned, if we are blocking some users, if they cause, for example, a backoff in the system, I see that's also challenging because as DRAM technology node size scales, benign applications can also trigger this. So benign applications without any malicious intent can have locality in the row level and hammer that row and cause these. And for reliability, we need to also, like the mitigation needs to also consider that. I can imagine like if there's a blacklisting method, like throttling method, which there are some works on that. I did not look into it, but I think it's very interesting to see. But my intuition is that if there is a reactive method that reacts to the memory access pattern that results in a higher latency, then it's possible to probably correlate it with some behavior at the system level.
Any of the telemetry, particularly some clocks are spinning it.
Yeah.
So you can see 100 nanoseconds will flow your counters at a time.
I see. Yeah, that would, I guess, relate to the leakage throughput more so if you're seeing a delay and so on. But yeah, so another thing that I would like to quickly add, another way to mitigate this sort of attack is to eliminate the timing channel itself by decoupling preventive actions from memory access patterns. So what that means is we make it periodic, right? But what we show is that at very low row hammer thresholds, meaning that your DRAM is very vulnerable to row hammer, you need to do these with high frequency, and it's very bad for the performance. So there's a trade-off between security and performance at that point.
Do you know how many cars
so you mean like in real systems? What is the value that we see, or?
Right. Well, mainly so, because how we would construct something like this, right, is we would have a constant timer that would just periodically fire our events.
Yeah.
And then decouple any of the
Mm-hmm.
The consequence would be, okay, that constant firing of our events is gonna clog up your.
Yeah, exactly. This is exactly what we see at, for example, row Hermit threshold of 64. And here we need to configure that so frequent that we actually can do a couple of activations before triggering or like before having preventive actions. So that's why the performance is actually like the highlighted part is very low.
So if your threshold is say like 2,000 or 1,000,
then it's doable, probably.
That's more doable.
Yeah. Okay, thank you for the question.
Thank you.
Can you help me?
This PDF.
Yes. That's why I need help.
Yeah.
Okay, maybe I can do this.
Oh, should I just wear this?
Yeah, or if you keep it on the table, that's also okay.
Probably not. Okay, sure. Thanks. Okay.
Or if you'd like to say that.
No, it's okay.
So the next speaker is Professor Prashant Jain. He is an associate professor. I believe many of us know him. He's an associate professor at the University of British Columbia and also the lead architect of the 3D memory architecture at Limetrix. So he asked me to cut this bio short
I'm gonna stop there and I'll invite him to deliver this beautiful presentation.
Thank you. Thank you. Can everyone hear me? Oh, okay. Thanks. Yeah. Yeah. It's nice to see most of you, and thank you for attending this talk. When I was asked to prepare a presentation for something like this, the natural thing I did as a professor was to just ask my students as to what they need in Ramulator. So this talk is mostly inputs from my students and mostly Junghyun and a few others. And feel free to sort of point out if there are problems in this talk, in the sense that this was a version of Ramulator that's 2.0. I think right now it's at 2.1. So it's possible that some of the things that I'm proposing here would already be there. So that, without further ado, I'm just going to talk about how we can think about extending Ramulator going forward. And some of the inspirations that for this talk come from my teaching motivations as well, because we use tools like Ramulator and ChamSim in teaching, and some of these inputs come from there. Okay, so what's Ramulator 2.0 today? It's a fast, cycle-accurate, open-source DRAM simulator, right? It's very modular. It's extensible and it's broadly standard compliant. You can drive it by using CPU traces, or you can just use a front-end simulator, right? So you have the front-end sim that's feeding the controller, that's feeding the DRAM device, and you sort of get statistics and data from that. And you can model all sorts of DRAM standards. Now, you might think this is all good, and it's modular, right? You have interfaces versus implementations that sort of you can sort of configure. It's fast and it's quite validated, right? It's cycle accurate and it's quite fast, right? I can give my students an assignment due in 2 weeks. They can start 2 days before the due date, and they can still finish the assignment. So that's great, right? It's compared to other simulators, and it's easy to extend. We can give them README files, and they sort of extend it very easily. So then, why extend it now, right? While this is my sort of also my opinion, while Ramulator is fast and modular, we would like to observe certain additional effects that dominate modern DRAM behavior, right? And this kind of thing would unlock more research, right, or new research. Right now, this is done at a group by group level. For instance, in my group, if we have to model some behavior, sort of Junghyun or some other student sort of does this at their end. I'm sure that other groups also have the same mechanism. And what I thought was, if there's a central forum where I can recommend some of these, it'll be great. Right. So for instance, right, this is very high level. One of the things that you can try to focus on is much higher accuracy in terms of modeling real world mapping, page policies, refresh, and scheduling, right? Right now, we can feed in maybe FRFCFS, FCFS, and any other complex policies. But if we can take input from industry and a few others on how AMD or Intel schedules the requests, and have that as a config file in Ramulator, that would be great. In terms of security and reliability, most of us have used Rowhammer as an example to prove that DRAM are inherently insecure, and we have used ECC to fix bits, right? And these are first-class concerns. And right now, it's a bit hard to evaluate this end-to-end. I mean, we can implement Rowhammer mitigations in Ramulator, but can we model things like charge leakage and bit flips and all that sort of end-to-end? That's a bit hard. It's a hard problem, and maybe the simulator is not for that. But if it's packaged in that way, it's in my vested interest to sort of give this to my students and sort of give them this black box. They can implement mitigations, and we can see if that actually works. Right, and we prefer like a shared platform, right? We want something that's sort of packaged in this way, and then all of us sort of develop ideas on the simulator. So that's my goal here, and let me sort of maybe put it in a single sentence. It's to make Ramulator a high fidelity, security aware, energy aware platform, right? That the whole community can build on. Okay, I think you need to click this. This one. Oh, this work? Or does, oh, I just go up, that's fine. So I've thought about this, and Junghyun gave me a few pointers. I've also spoken to a few other students and some other students that I've taught. So these kinds of recommendations come from research and a bit more on the teaching side of things. So there are 4 areas I think that we could broadly improve on, and each of these area extensions sort of is a missing model that's sort of coarse grained, and you can make it configurable, right? So the first area is modeling fidelity, right? So for instance, how do you think about page mapping in the Ramulator framework, page policy and refresh scheduling, more from a industry standpoint? Can you integrate this this DRAM simulator with some popular front ends, right? So there is GemFi, there's ChamSim, and can we have maintained wrappers that integrate it? Right now, as far as I know, maybe things have changed. Even to integrate this with GemFi, it's a little bit of a manual process, and the same thing is true for ChamSim. If there's a more seamless way to sort of integrate that, that'd be great. Like I mentioned, for Rowhammer, there are bit flips and ECC and errors, and how do we sort of do an end-to-end evaluation of that? That part could be useful. And power and energy, right? So this fourth thing comes from the DRAM power tool, right? So there's a tooling for measuring DRAM power. But is there some way we can sort of get inspiration from there, but use all of the features of the Ramulator to model power and energy more in a more fine-grained manner, right? So this is how this talk is going to be structured. I'm going to talk about the area 1 and 3 first, right? Which is the memory controller-based recommendations, and then the area 2, which is the front-end driver. Essentially, how are you going to feed in traces? How do you sort of wrap around different frameworks? And then area 4 is basically the DRAM device model for energy and timing. Okay. So essentially, what I want, hopefully, all of us work towards is one code base, right? Wherein you have one area that focuses on the controller and device. You have one area that focuses on the front end, another area that focuses on the plugins, and then fourth area that enriches this model, right? We can, from like focus groups, if that helps, to sort of have pull requests into some of these areas and expand the simulator, right? And sorry to make this only a simulator-only talk. I thought this is the Ramulator talk, so I have a bunch of slides on Rowhammer, but I think it's better to sort of talk about some of the challenges that we faced while working with Ramulator. And maybe Junghyun fixed it at his end, but it's better if you talk about it more from a community perspective, right? So what I essentially want the controller to do is to make the controller and the device model what the industry products do, right? So for instance, right, if you look at DRAM organization in Ramulator, every model timing starts with the same hierarchy, right? You have channels, you have ranks, you have bank groups, banks, rows and columns, and then cells, right? And these parameters in Ramulator's DRAMs are standard classes, right? And the aim is to encode them into sort of industry products, right? So if you have access latencies like TRCD, TRP, TRC, right, and you have spacing constraints, right, like TFAW and TCCD and all that, right? Can we sort of use all of those while also looking at how address mapping works, right? So there have been some papers in Usenix and several papers in Usenix security and CCS that have actually broken real industry products, and we know how these mappings are, right? Instead of having a few fixed linear mappings, right, and not the reverse engineered mappings, maybe we can actually have some vendor maps in the Ramulator framework, right? So if the students can, to address reviewer C's concerns, instead of running things on a Zen real device, we use the validated vendor maps in Ramulator and say, okay, we've picked this configuration that actually AMD or Intel has, and we've evaluated on that configuration, right? It could be different scheduling policies or mappings that, it's sort of an open sort of question, right? The same thing, right? Why does the mapping matter? Because it could be one that some reviewer asked for this. The other one would be like, okay, with this mapping, what happens, right? Like, is there going to be a serialization at the bank level, or are there going to be like some optimizations that you can think of, right? But now you can claim that you've used the mappings that some of these products actually use, right? So it's pre-validated, it's packaged in Ramulator, and we can sort of give students and sort of pick those configs out, right? I'm sure you know all this about this already. So if you have a poor mapping that sort of sends a hot stream to one bank, and if you have bank level parallelism that's unlocked, then you can actually sort of send requests to multiple banks. Right now, it's a configurable parameter, right? It's not like you can't do the other one, but if you can sort of point us to some industry or product related mappings, it's much easier than to sort of work on the real problem and sort of configure the simulator. The same thing sort of applies to row buffer policy, right? Now, whether the controller keeps the row buffer open after an access sort of has an impact on performance and latency, essentially. And you can only pay like a column access latency if the row is already open. So whether you do open page or closed page or some combination or hybrid of that is important. It will be useful, and there are some papers already, right? This is an old paper from ISCA 2000, but there are some papers in a few other communities that have looked at what the scheduling looks like for these different products, right? So if you can sort of integrate that into Ramulator, then you sort of abstract that away. So you have a configuration that's pre-validated, and then you can just focus on the problem at hand. This is basically to sort of speed up research, and it's also for my undergrad students to focus on some other problems, right? Not try to sort of work with Ramulator and try to configure it in a certain way. So currently, and this is again 2.0, so maybe 2.1 has changed things. We have, as far as I know, there's open page, there's closed page, there's FRF, CFS, and you can choose this statically, right? What we could think of would be some industry-driven adaptive policies that switch between open and closed pages, right? As modern servers do, right? So that then sort of becomes a file that you can read from and then configure your simulator. And then you can actually say, okay, this is pre-validated, this is compared against these servers, this is the config file we are using, and then all of these results hold, right? So that's another sort of pointer. The third is refresh management, right? We all know that refresh reduces the bandwidth, the effective bandwidth, and how the granularity of refresh decides how much bandwidth is lost. And JDEC is also adding RFM, which is the refresh management command, to effectively throttle activations to bound row hammer, right? You can have all bank refresh or per bank refresh, right? And depending on whether it's all bank or per bank, you can have different types of stalling, right? And then right now there is REF-AB, right? Where each device pauses and and there's no RFM, right? Or as maybe there is, this probably is older, but what we could add is a per bank and a fine-grained refresh management command, right? That sort of would unlock more bandwidth effectively and also sort of reflect the JDEC RFM config. And the fourth, this is a little bit more higher level. Right now, we've been looking at these kinds of DRAM simulators more from a processor or a CPU perspective. But if you're looking at a system of chip, right, like an SoC, you could have multiple cores through a shared LLC talking to a memory controller, but you could also have IODMA come in. And I know there is already some research on this, but if you can develop the memory controller to be more cognizant of this kind of configuration, right? And think about ways in which you can have quality of service priority, aging, the weighted round robin, and all those kinds of scheduling mechanisms, just because the SoCs have become more complex now, right? And you can have multiple devices talking to the between the DDR, DRAM, and maybe the HBM and all that, right? So, and there's unified memory now, right? So, so I think these kinds of enhancements will go a long way in sort of helping researchers and students try to model real systems without them trying to configure those files by reading these sort of parameters online, right? So the goal here is to make it simpler for researchers so that it's pre-validated, and then you sort of just focus on the idea, right? So if you're thinking about an idea that improves, mitigates row hammer in the DRAM channels, then you can just pre-configure the setup, right? Have inputs between cores and the IODMA, and just focus on the row hammer problem then, right? So that's sort of the goal. And to be fair, like I'm fairly certain that a lot of groups here have done this independently in their versions of Ramulators. The goal here is to sort of centralize it and sort of make sure that everyone has access to it, right? The fourth, area 2 out of 4. So this is going to be like a long talk. I'm going to keep like very specific pointers. So, well, I'll try to hurry up. So the front-end simulator, right? So, typically you have a core that's, doing some branch prediction, out-of-order processing. You send accesses to the caches, and then those misses go to the DRAM. So if you do use a trace-based simulation, then it sort of hides the wrong path, prefetch, and all that, right? All of the filtering effects, of the real front end are lost, right? So one of the things that I thought we should try to get, maybe this is not a Ramulator specific thing, but more a broader sort of question, would be to get branch prediction and wrong path information in some of these traces. It will lead to maybe more cache pollution, and more second order effects could be shown. These could also lead, going in the wrong path could also lead to prefetching, interesting prefetching papers, right? That we can actually use Ramulator as a way to study these prefetching techniques, and also optimize the L1 and L2 and L3 LLC hierarchy, right? Because now your LLC might have some lines that are from the wrong path, and then they probably sort of pollute the LLC and L1 and L2 caches, right? So, so in terms of tracing, this could be one thing, right? So this is the front-end fidelity essentially, right? Instead of just using sim points or so getting traces from any of these kinds of tracing techniques, maybe we can get traces from Gem5, which includes the wrong path information, and get those traces out and feed that to the Ramulator. So speaking of Gem5, right? Now Gem5 is an alternate model for out-of-order cores, caches, and prefetchers. I would say alternate because, well, people say it's cycle accurate. Some people it's accurate. I just say that this is one other way to evaluate performance, right? But right now, wiring into Ramulator is very hard. Okay, at least the 2.0 was very hard. The student, this was pre-ChatGPT Claude days. Maybe it's easier now, but it was a bit hard at that point in time, and we had to write some things manually, and these things drift out of date. You make updates in Ramulator, and then sort of the wrapper sort of breaks and all that, right? So if we can get some support here, because Gem5 has a big community, so this integration becomes easier, and then you can sort of cater to a much larger community then, right? So if you can keep it in tandem with Gem5, right? So the coupling sort of lives in the README file right now, and you have to manually patch it. And that patch sort of drifts out of date after each release, and it becomes very hard to integrate, right? If you can have a maintained wrapper with both match timing and merge statistics, right? Essentially, statistics is the harder problem. Across both tools, that'll be great. And now ChampSim, right? So one of the things that I've, at least at UBC, but we've sort of switched over to ChampSim as a way to teach prefetching and branch prediction assigned. Like, we don't teach them using ChampSim, but at least they evaluate their policies using ChampSim. And one of the things that I really want them to do is to integrate a good memory model with ChampSim. And again, we need a wrapper, right? And we didn't have any bridge into sort of building it with ChampSim, right? For Ramulator with ChampSim. So it is a hard problem. So this is another wrapper that I think for a fast simulator, if we could maintain as a community, that'll be great, right? So right now there is no built-in coupling, right? Every group has their own sort of wired up bridge. I have some hacky wired up bridge in my labs, and I think Tor taught the course after I went on a sabbatical. I'm sure he has something there. It's better that we sort of develop this bridge and sort of help making students sort of learn the real things, right? Essentially scheduling policies and other things, and you abstract some of these tracing and other things out of the students' assignments, right? So maybe if you can have a maintained wrapper here, right, that sort of verified and works with multi-channels and all that, that'll be great. In terms of security and reliability, so this is somewhat personal to me, right? So rowhammer, we've been working on a few papers in the recent years. It's an important problem. DRAM chips are vulnerable to rowhammer, and you can have single-sided, double-sided rowhammer, and you can have mitigations, right? So today, Ramulator can model the cost of a mitigation. So you can tell it like, okay, these are the rows that gets maybe refreshed or mitigated. But it's very hard for it to test it, right? You can't test it because you don't have a physical model of these cells in Ramulator, right? There's no model that says, if I access a row 4,000 times, right? Some amount of charge leakage has already sort of happened. That thing is not there. So we have to sort of develop a different model, and then sort of, it becomes a hard problem to solve, right? So I mean, maybe this requires a little bit more thought, right? But you have mitigations like Para, TRR, Hydra, right, where you sort of have plugins to Ramulator, and there's no mechanism to test its security. What you could think of adding is a bit flip model. It could be like a first order bit flip model, which people can sort of improve on. I think some of the work that Onur and a few others have done have characterized these bit flips to a point at which we can actually model these very effectively, right? You can have first, second order, or third order, very, very detailed models of these bit flips. And then every axis also sort of encodes these charge losses and physical effects, right? So then you can actually test your mitigations much more effectively, in my opinion, instead of using a separate tool for doing that. So one of the things that we can sort of, at least at a first order test, is our probabilistic mitigations like PARA or PRA, right? Wherein you have charge leakage happening, but the moment you refresh, the model sort of refreshes the bit, the charge on these cells. You can have in-DRAM TRR or counter-based techniques that can be tested. But in all of these tests, right, you can, because you've actually modeled the charge and leakage and physical effects, even sort of blast radius effects and other things can be captured now in a more sort of nuanced manner, right? So that's the simulator jobs, right? So you can then have this one sort of resource you go to, right? It does defense, it stops all the bit flips, it can model the timing, but it can also model performance, energy, and costs, right? And all that together, and security. And the other point here is ECC and error modeling, right? So right now we have different error sources. There's random errors, retention errors, rowhammer errors. We have on-die ECC, rank level ECC. We have correctable, uncorrectable errors. So Ramulator models performance very well, right? So let's say you have to do a read modify write, it can model that, but it does not do the resilience simulations on the side as to what happens when you actually get these errors, right? So if you can inject errors in Ramulator and model ECC latencies, cup cost, and track all of these, that'll be great, right? And this is probably an easier thing to do because you can sort of say that, oh, I've injected 4 errors randomly and I run a scrubbing engine. Is your ECC technique really working? And even when you're actually developing ECC, instead of just modeling the correction probability or correction chance, you can actually model the ECC technique and pass the data through. If you're assuming random data, you randomly flipped a bit, maybe you can test. So it makes the simulator more robust. I'm sure a lot of industry people would be interested in doing something like this, right? If this happens. Okay, so the last point is power and energy analysis. Right now, the energy depends on each command and the rank's idle power, right? So there's like the activate, pre-charge, you have self-refresh power and all that, right? But there's this tool called DRAM power, right, which sort of does this power modeling. So instead of having a single coarse-grained power estimate, if there's a per command per state energy breakdown, that'll be really useful. In fact, I think power modeling is something that I really found useful when I was looking for ways to model power in 3D DRAM accelerators, for instance, right? Because their power becomes very important, and how you model per token cost sort of directly is dependent on the power, and you sort of want to have a very fine grained model of power at that point. I could not use Ramulator at that point because it didn't have that, but it would have been nice if there was a very good power model inside it, and people can then start using it even in the industry. So you can have a per command power, per state energy, and a detailed model, right? Very similar to DRAM power. In fact, I would, this is an open source project. You can actually clone this, sort of try to merge it in Ramulator if that's easier, in my opinion. Okay, so that's about the 4 things that I wanted to talk about. These are the references. I mean, this is obviously a lot of work. These are only a few of the references. A lot of people have worked in this space, and a lot of people have used Ramulator. I'm just citing a few papers that could sort of back whatever I've proposed. And if your paper is not here, it's not on purpose. So thank you, and I'm open to questions. Yes.
Yes. Thanks a lot, Prashant. I really appreciate all the directions of improvements, and actually we have the same vision as you said. We want to make Ramulator we consolidate the efforts from different groups, different versions, and we maintain them. We try our best to validate them, and in the end, we have a shared pool of resources that everyone can just be comfortable to get started with, and it will simplify a lot of stuff. And also, as you said, many of the or some of the improvements are already landed in 2.1. Let's say for Gen 5, we already have validated wrapper that works for both SE and FS, and it also works with the, let's say, the more recent Gen 5 board organization. So that's already done. And I strongly agree with all the other, let's say, improvement directions you mentioned, especially different address mapping, different scheduling policies, and can we make them more aligned, more validated to what some of the representative real products are using? That would be a very good direction on that. And I think the modular structure of Ramulator 2 should enable this, because these are relatively more self-contained components. So yeah, maybe we can also maybe talk afterwards, maybe also with your students. So if you already have some contributions, we are very welcome to.
I think we've been guilty of this as well. So we've made changes into the local copy of the Ramulator. We didn't have any pull requests, for instance, right? But I think if we can set up a mechanism to, as a community, right? If most people working in memory space sort of does this, we can develop this simulator to be much more sort of broader, in my opinion. Thank you.
Thank you. And also, I also have some other comments on the other directions.
Sure.
So for the Rowhammer stuff, as you mentioned, the exact error modeling, that's something that we are very actively working on, and we actually collaborate with device level research groups, try to come up with a so first step, we try to have a more comprehensive, more updated TCAD modeling that explains all the first order device real chip observations, and then we can try to build a system level error modeling and injection model into Ramulator, which is backed by both the real chip observations and TCAD simulations. And if you or your students have any ideas in this, we were also very open.
Yeah, for sure. Yeah. In fact, I think your group has access to real chips data. So I think you should fully leverage that and sort of incorporate that into the simulator. That's because I got all of you all here. I thought I'll say this, and it's much easier now, right? So yeah.
And for the power energy thing, that's also something that we strongly feel will be the next important let's say, go or update to
Yeah.
Ramulator?
So right now the DRAM power is already becoming a large fraction of the total power in a data center. But if you're going for like any sort of exotic accelerators, those memory powers sort of becomes a significant dominant factor. So modeling that more accurately helps give people more directions. More than accurately getting the right split of where the power is spent can then drive research in certain directions, right? So that'll be great if you can add that. Yeah.
Yes. Yeah. That's all from my side. Thank you very much for all these suggestions. And yeah, our two groups can definitely talk more about these.
Thank you. Thanks.
Hi, Prashant. Nice talk and summarization of problems. It looks like many things have not changed since 10-15 years.
No. I think this is, I mean, we are at a much better state now, for sure. But like, yeah, I mean, you always want more, so that's why. But yes.
I'm more thinking like this is the vanilla system where you're seeing CPU, LLC, but most of the systems where DRAMs are deployed, whether you're GPUs or memory compute inline or memory in compute PIM. So all those things which are or in the inference or LLMs, how those in the accelerators DRAMs are used.
Yeah.
So I have talked to startups. They start with Ramulator and then see what do we do, because they have to redo everything. So it's good for the research or where the vanilla CPU and this thing is, you can hook up this thing, but or whether it's a DRAM sim or emulator, doesn't matter. But in the industry, who wants to model their system, they have to do much more than what's there, as fun as I understand.
Yeah,
so
that's true.
Especially in these things, how do you incorporate those different systems like memory and compute or GPUs, for instance?
Yeah. So I think as a memory simulator, this is quite modular, to be fair. So you don't actually have to break things a lot to integrate them, in my opinion. But it's still, I mean, there are some things that we really prefer. Like that's the way I sort of see it. I mean, I've used this in some of my studies, and it was like you can sort of modularize it and break things over and sort of model things. But it's, yeah, some things were lacking essentially. So if you could add more, that'll be great. Yeah. Okay, thank you. Yeah. So if you want me to talk about Rowhammer, I can talk as well, but I don't think you want to know that. Okay, thanks, guys. Thank you. Yeah. Hello. Should I give it to him?
Yeah, it's my turn. Take your time. Oh, it's not there? I sent you.
Yeah.
Oh, yep. Maybe desktop. I will make it quick. Take your time. Take time. Yeah. It's not technical talk, so. Awesome. Cool. Oh,
we should extend it because I had to mirror the screen for the previous talk.
I think this is.
I have the screen overlay.
I think this one means it's shared.
Yes, but I'm worried that it's not sharing the whole screen.
Yep.
Sorry.
Okay.
Okay, now we're moving on to the next invited speaker, Professor John Wang. Professor Yang is a professor at Seoul National University. He received his PhD in electrical engineering from Stanford University in 2007. Prior to joining SNU, he was a senior research scientist at HP Labs, and he later completed a sabbatical at Google and Samsung Electronics. His research focused on bridging the gap between the performance and efficiency demands of emerging applications and the potential of modern massive parallel systems, with a specific emphasis on memory subsystems. Thank you for joining us.
Thank you for the nice introduction, Nisa. And also, thank you very much for inviting me to this excellent tutorial and some sort of workshop thing, Onur and all the organizers. So let me talk about something non-technical stuff. As I briefly mentioned, I will not speak too long. So basically, I will talk about why I moved, not entirely, but to move from my in-house, my own simulator into the Ramulator plus DRAM Bender combo. And that's combined with the lessons and implications I have. So first is the disclaimer. I'm not a native speaker, and this one maybe there will be subtle things here and there. So please kind of understand that part. Second, I do not intend to offend anyone, but maybe I do so indirectly. This is my brief career, so I call it, but I graduated 2007, and it's kind of not as old, kind of similar age with Onur, I think. So this is, I got my bachelor degree at Seoul National University, moved to Stanford, spent a year at Stream Processing Incorporated, which is now, it's gone, and the people there basically merged into NVIDIA, so they are wealthy and happy, not me. And then after graduate, I went to HP Labs, spent 2.5 years, and then came back to South Korea. Why I talk about this one? Kind of it's regarding the DRAM simulators. If you take a look, DRAM Sim 1, it was first 2005. So about the time we started to write papers regarding DRAM. DRAM Sim 2 is 2011, DRAM Sim 3 is 2020. But as you know, that DRAM Sim 3 is not that much actively maintained compared to Ramulator. That's my understanding. The another thing was from the Rajiv's group at University of Utah. That's the USIM, which was the kind of become public 2012, but there's no USIM version 2 or things like that. There are some papers which claim to use USIM from time to time, but it's not that much active either. So now we are talking about the Ramulator. Ramulator 1 was the 2015. It's published at IEEE Computer Architecture Letter. And about 9 years later, it was kind of the version 2. Now it's 2.1. That is the main topic of this tutorial, I think. Around that time, I kind of developed my own and called it as a Maximate Plus. Even though it was published at ISCA 2013, I started to develop that at my time when I was at HP Labs. So it has more about kind of less than 20 years of history. So before I joined the HP Labs, when I was at Stanford, by the way, Bill Daly had a kind of stream processor. Somebody called it as a kind of predecessor of GPU. But, believe it or not, it has some similarity. It has kernels, it has stream C kernels, it was kind of infrastructure. Not just that, the first paper I kind of published at ISCA was in 2004. It's evaluating the image stream processor. I did not fabricate, or I did not basically made Imagine chip, but I was a part of the Imagine development board part. So they spent quite a bit of time spending on the FPGA part. That is something I want to emphasize. I know the value, I know how hard to play with FPGA, especially on the memory system. Even at that time, I was very kind of pleasantly surprised that my little, very basic memory controller worked, even though its performance sucked. It has nothing, no cool features like out of order scheduling, things like that. It took me a lot of time just simply make it store a bit and retrieve it. So that's something I want to emphasize, and I will give big hands to the older people in the DRAM Bender team. And then when I was at HP, there was a paper I was the part of it is the how to simulate 1,000 cores, even though it is the totally different simulator infrastructure called COSIM. I spent some time there. Then I have caused some of the tool papers, not just the simulator part, but also the Cacti. I participated in the Cacti 5.1 and the MacPad part. Some people still use it. And now let's talk about the Maximini Plus, which I use in my research lab for a while. So this is the kind of DRAM tools I have been using while writing papers for my group. So the blue one basically is the My Simulator, which is not just DRAM, but also the many core processor, which is I call it the application plus, because it's a kind of the decoupled simulation, which is kind of trace driven, but not entirely. It has some more features than that. I modeled the cache coherency, not necessarily memory consistency too much, but I use the Intel pin instrumentation tool and let it generate the traces dynamically based on the execution path, and then let's plug it into the memory hierarchy simulator, including L1, L2, and left cyber cache, so on, including the DRAM timing. For example, I was able to model whether it's open policy close or the adaptive open those are the part. When Onur started to write papers regarding, for example, parallelism aware batch scheduling, PABS, and Blaze, those kind of things, I kind of reproduce in my lab, in my group to see how, where it's good or bad. I mean, typically it's good, even though it's some complicated. So as time goes on, around the time right after kind of COVID started, some of my students actually go against me and just adopted Ramulator. So that's a yellow one. And as time goes on, more and more papers from my group are kind of based, it depends on the Ramulator. There are some kind of remaining kind of residue. Even this year, I think there was a paper, probably just this ISCA paper is based on my tool. Also, I have 5 papers so far by utilizing SoftMC and DRAM Bender. I briefly talk about this kind of stuff, not technically. So why have I been developing my own simulator? That's training and education. DRAM and memory scheduler basics, load of memory, main memory. What I mean by that, I want to kind of talk to my students about how DRAM works, how memory scheduler works, and then let them kind of make their hands dirty, let them kind of make mistakes and fixed. That means that they understand what's good, what's bad, what's going on, how dirty it is about the nitty-gritty detail about this, especially regarding basically the which one? The that, how can I say that, the fairness, that's the most important stuff. And it's basically a black box versus white box approaches. If you just kind of, in some sense, buy Ramulator and then assume the Ramulator is correct, then you spend actually even more time by on this if you encounter some unknown behavior, so kind of which is not right to their brain, they spend more and more time. If you just kind of read the kind of simulator code line by line and try to understand what's going on, then you kind of understand the result, even if it may not be the perfect, not modeling all the nitty-gritty detail. So I want, in other words, if there's any problem, so that's related to the fact that all the simulator have some kind of bugs. Bugs are kind of unavoidable. It's not the fault of anyone. It's all the voluntary effort, and bug happens. And in that case, if it's a student or even me approach a simulator as a black box, they are out of nowhere. But if it's a white box, then it saves a lot of effort. It saves their life, not life, but the graduate student life. That is the customization. It's again the hands-on experience. Say that we have new features, then in that case, it takes less time if you are really used to the tool itself. I think that is part of the primary reason why Onur's group still working on the Ramulator, and they kind of made a step further of kind of community service-wise, try to open source it and let others use and let others share their experiences. That's related one is the time to market. We are all kind of have to write a paper and show time, right? We cannot let our student to kind of spend 3 years of thinking about, for example, there's a PROC. And the students say that, oh, I want to kind of develop my own simulator and spend on building that for 3 years. That, okay, maybe just PROC 3.0 at that time, that you have to start from scratch. We need, in our kind of time processing market, or not market, but the field of kind of computer architecture, we need speed. And that, again, debugging, I will not repeat too much. The last one is the fun. I actually learned a lot out of developing my own simulator. Even though it's not perfect, I understand what's going on. And I experienced a lot of deadlocks. And then I had good experience as a kind of assistant professor, as a researcher. I spent lots of time to see what kind of mistake I made. And then I learned a lot out of it. And I want my students, some of my students, to repeat the process, learn from failure. Then, why do I embrace Ramulator right now? It's again, training and education, especially for the tutorial, unit test, documentation, ease of use. Ramulator is well more kind of structured, well executed simulator. I did it by myself as a kind of researcher and an assistant professor, but I didn't have time and effort to write it down. Write a great documentation, great tutorial, write a great kind of unit test, but relatively, Ramulator is kind of better as a starting point to a new graduate student. Code maintenance and community. We can ask some questions to the people out there. So people, not just kind of owners group, but to the other kind of people there. So this again, brand power, sorry. So my paper has been kind of cited a little bit less than 200 times. So I'm proud of it, and some of my friends and my colleagues use it still. But compared to the Ramulator 1 and 2, it's kind of already cited more than 1,000 times, and even Ramulator 2 is cited a little bit less than kind of 200 times. So it's a kind of safe bet for my students to investigate. And this is the kind of one of the critical parts. It's hard to motivate students because they want to write a paper. They don't want to spend 3 years to develop a new simulator. So again, I think it's as a long run, it's important for them to have exposure and have their own experiences in developing simulator, but practically, they want to just use a kind of relatively reliable tool and write paper. And I'm getting older. It's hard to kind of repeat the process of educating my students one by one. Say that, oh, you made this mistake, that mistake. How about the DRAM Bender and soft MC? Again, I spent some time, some good time. I saw some spark right on top of my head, right behind my eyes when I was developing that the dual imagine development code. So I kind of, not entirely, but understand how hard it is. So brave guinea pig in my group. I appreciate that Dr. Jayon Park, who's at Samsung right now, Haocong, Seungmin, and Jumin. They spent about 2 and 3 years to make themselves used to. Now, after that, kind of now they do the sanity check and things like that. They ended up with writing papers. I think I'm very proud of these kind of papers, try to understand without very kind of destructive or intrusive kind of surgery kind of thing. I understand what's going on within the DRAM, like DRAM scope, or based on that, the knowledge we got out of the ISCA 2024 paper, we had marionette row hammer tech row coupling. That's what my group was able to, with essentially the help of kind of open sourcing their efforts into through the GitHub. So the thoughts and lessons, what I learned regarding architecture simulation in general. A simulator is a modeling tool. Modeling is an abstract. You cannot model everything. That's impossible. all the modeling tools have intended usage scopes and so limitations. For example, so when I graduated from Stanford and joined HP Labs, so the Noam Jupi actually was keep putting his cacti into the web. There's a cacti.hp.com or something like that. People use it, but actually people abuse it more than use it. It's because the cacti has some assumption, and people started to use cacti out of the intended scope of the simulator. So I saw that kind of every day. I try to kind of educate or explain what was the range of the cacti, but still now in 2026, a lot of people abuse it because they do not understand the intended usage of the right scope of it. Verification is a must, but rigorous verification is tough. We are all kind of volunteers. We did our best, but we have some unknown bugs here and there. And research is really about exploring the unknown territory. So if existing code from academia, if it has no bug at all, when you are exploring a new area, and you made some mistake. That cannot be the case. So also, one thing I really want to emphasize is that simulation is not for generating absolute numbers, because there are a lot of, for example, say that the clock crossing issues and some analog related issues and here and there, or even the which a refresh can be kind of adjusted in timing, delayed, or just kind of postponed the other way. Those kind of things are not modeled in any of the simulator. You cannot make a 100% accuracy. So it's not about the absolute number. It's really about the trends or the relative numbers. So verifying a simulator, memory simulator, anything, or a combination of those against real hardware is very important but complicated. For example, prefetch, as Prashant and the others, Nisa or others also mentioned, or the Haocong also kind of mentioned about the vision of the Ramulator 2.1. There are complicated stuff, address entropy, qubit per size, structures, robot per management policy, on-core latency, including wiring stuff, which is really hard to model, clock domain crossing, asynchronous pipe, and network on chips. These kinds of things are really hard to model. So I want to emphasize that the devil is in the detail. So what I want to follow, kind of saying is that reporting timing discrepancy is one thing, but performance debugging is another. Adjusting unloaded latency through minor modification on the code or machine description file. In that case, say that you saw 30 nanoseconds of zero root latency, but actually a chip has an 80 nanosecond zero root latency. I measured the chip here and there. Somebody here already mentioned that where is the address interleaving, but you can actually change the address interleaving by modifying the bias. But you cannot, depending on the bias, depending on whether you use the desktop chip or server chip, you cannot actually control those. Even if the memory controller of the AMD and Intel actually have them implemented, we do not know the detail because those people do not disclose everything. So that's very tough. And kind of depending on the number of cores, so a zero root latency change from 70 nanometer to 80 or 85 nanometer, those kind of things are normal. There are a lot of nitty-gritty detail we do not know. And in that case, if you saw there's some mistake in the machine description file, why not just directly reporting the issue to the simulator developer and let them fix? That's, I think, the most important thing we have to do. How can we do code-fitting when we do not know the internal microarchitecture of memory controller and the parts around those? Again, the band conflict, those kind of fairness-related issues. I will skip that for the sake of the time. So again, aforementioned open source, the main memory simulators are voluntary efforts, even DRAM sim, Ramulator, and USIM. We must appreciate the hard labors of the developing and maintaining or even using those kind of simulator. What would be the implication of LRMs on the laboring? I think it may help. We had some discussion with Haocong and Nisa when back a couple of months back at Seoul National University. It will definitely help people, but still, it's kind of based. My understanding, or so far, my understanding is that those kind of LLM helps a lot, but it helps making FusionJump unit tests and things like that, but it does not replace what is in your head. So you have to design first and then get some help from the LLM. Debugging is known for the simulator, not a compensation or the sole topic of the research paper. I think that debugging itself is really important, but just reporting the debugging into a conference, I think that's okay in some sense, but I would say that if you are 100% sure if it has some insight which the previous people did not have, then maybe good. But if it is based on the kind of common knowledge we all have as a community in mind, but did not into a written paper, there are a lot of things, not but some of things like that. Again, for example, the relative performance, not the absolute. Those kind of things, it's, if you kind of thought it into a paper, then I'm not sure whether it's best idea. So you, last but not least, your dedication should be rewarded. However, not necessarily to ISCA, HPCA, micro, HPIS plus papers. I think we have to value IEEE computer architecture letter or the ISPAS as good as ISCA, HPCA, micro, and S plus papers for the good kind of hometown of the simulator papers. So I really appreciate all the efforts the people in this room have made. So just 2 more minutes. Do you know are you familiar with this figure? Do you know where this one is coming from? It's from the textbook. Looks like the processor. There are MSHR, there are kind of TSHR, bank control, memory banks, 1 to n minus 1. Any idea where is this book coming from? Yes, you're right. Hey, you're cheating. So actually, this is the book of the day of the principles and practices of interconnection network. What I emphasize is that the book is about the interconnection network, but it talks really good things about memory subsystem as well. My hunch is that the difference between the interconnection network and memory scheduling or main memory system, it's almost nothing. You can apply all the good things from there into here, from here into there. For example, this is the figure Nisa and others show. This is the load latency graph, which we are all kind of agree with you, but these are kind of the textbook, there's the figure from the textbook. And this is the figure you can see from the paper, from a paper. And this is basically says that the caption says that an incorrect method of presenting latency and accepted traffic. So if it is not monotonically increasing, there's something weird going on, then you have to double check. It's a kind of mistake we make, and this is the one kind of repeating, even if it's on the paper. And some related one is the fairness. If you make some mistake in the fairness, until the network is saturated, you cannot see that. But once the network is saturated, and if you make a mistake, say that, just keep fixed priority to some of the decision you make, you will see something funky going on. And that is these two figures or the graphs are somewhat related. So with that, thank you. I'm happy to take any question. Thank you. So. Great. Sure.
Thanks for the nice talk. Thanks for the insightful talk. I enjoyed it. I think you talked about very interesting things. Definitely, I think all of these are volunteer efforts for sure. One thing that you did not talk about is how these simulators interface with other simulators, because they don't exist in isolation. Do you have any thoughts on how to bridge that gap? Because today's systems are very complicated, right?
You're talking about things like Gem5 and Ramulator.
Or Chamson. What are your thoughts on that? You said you were using Ramulator and DRAM Bender and you switched to that. What about on the other sides? What are you integrating these simulators with?
So actually, that's integrating different simulator is really a tough one because you know both simulator very well. I still remember the time, so when I was HP, at the same time, Nate Binkett joined. He was the original author of M5. And he had, I mean, he passed away several years ago, but he had real pride about the M5, which I totally agree or admire. But it's, even for him, it's kind of embracing, for example, main memory simulation. That's a top job, if I remember correctly. So what I'm saying is that I'm not talking because I'm not an expert in the simulation, the methodology itself, whether it's event-driven or cycle by cycle. For example, my understanding is a Ramulator is the cycle by cycle simulation, and for example, my simulator is event-driven. Whether it's kind of totally different or not, that's a different story. But again, I want to emphasize this, that anytime you integrate two different simulators, you have to admit that you are likely make a lot of mistakes. You have to admit that it will happen. So you have to double check, triple check, and it's better to ask original authors about whether there's any problem or not. I still remember the time that I forgot the name of the intern, but he spent several months to boot Windows within M5 and I was an HP. And through that process, that very painful process, he learned a lot because there are some instruction which was never used in any of the normal mode during the boot up. When you change the kind of 16-bit to 32-bit or 8-bit to 16-bit mode, things like that, things are kind of hang. Those kind of things happens normally. So again, maybe it is not the best answer, but the chances that you will get kind of mistakes are 100%. You have to admit, and you must not reach conclusion too aggressively or too early. That is just only thing I can say. Yep. So yep. Yep.
Thank you so much for the insightful talk. I'm Haocong from Georgia Tech. I have two questions, and first one is I kind of want to hear more about your thoughts on the interconnection network and the memory systems. I think you were running out of time, but I really was wondering what is the like your thoughts on their correlation. And the second thing is I really value your comments on the simulator work, how much effort it takes. But I also was wondering, how much do you think the author of the simulator have to put efforts? For how long, and like how much are they have to be responsive? Because I think it's really like a lot of effort for them to first publish it as a simulator and open source. But I think they also take the responsibility of any of the failure of the system. So I think it's very natural for people to not publish and then like keep it on themselves. But it's also like, yeah, it's kind of like a vicious cycle for me. So I really want to hear more thoughts on it.
Yeah, let me, great question. So let me answer the second one. So again, let me just bring Nate again. So Nate, if I remember correctly, he spent 6 years at University of Michigan. He had only one paper, but he was really proud of that. That is the M5 paper. And even for the M5 paper, because he kind of the methodology, the novelty is not from the simulator, cannot be from the simulator. He spent some effort on the network related stuff. So he wrote a paper. So the how can I say that? If somebody wanna push for academia right after graduation, kind of spend a lot of time and effort in simulator may not be the best idea, but it will be rewarded because you learned a lot. Now you can answer almost everything from all the aspects. So you becomes really a guru. So I personally, I kind of look up to him. So that was the reason why I kind of spent some time to develop my own simulator. At that time, the problem we encountered when I was in HP Labs was that was the Corona paper. This is 2008 paper. And the goal was to try to simulate the 1024 cores. It's not a big deal, but at that time it was a big deal because at that time Linux didn't support more than 256 cores or something like that. Because M5 was a full system simulation, you have to modify Linux as well, but the Linux doesn't support it. It takes quite a long time because that was the reason I decided to kind of develop a lightweight simulator because I want to make it happen. But the simulator result didn't get into 2008 Corona paper, but I learned a lot. And at the time, the main memory scheduling stuff, POP-ES, like I mentioned before, was out. I was able to understand and implemented my simulator. So it helped a lot over time. So if you want to be a kind of jump into academia right after graduation, I think it's fair to write many ISCA papers instead of spending time. But it will be rewarded. That is the only thing I can say. Even though it is from maybe just ISPAS or the IEEE CAL, but I think it's as important as, or even more important as the other top tier conference paper. If you did good thing to the community, it's hard to say, it's hard sell. So I cannot enforce my students to do that. For the first one, the relationship between the memory subsystem and the interconnection network. So interconnection network, it's about topology, routing, flow control, and router microarchitecture. For example, router microarchitecture, it really looks like memory scheduler, for example. And also, if you take a look at today's NOC-driven multi-core manifold processes, it uses interconnection network. And if there are some problem in the fairness is like essentially the big part of the flow control, your kind of simulation result will be messed up. So if you, not master, but if you have good understanding of that, then you will come up with, you can avoid the common mistake in the memory controller related or memory system related study. It's all about, you just exchange information, exchange packet. In that aspect, it's very similar. One last thing I want to say is that so the other part of the floor, there's working at the tutorial from members. I think because the DRAM is so popular, we have two very interesting tutorial happening in parallel, which is really a bummer. You can learn a lot from them, and they are talking about memory controller. The last thing I want to emphasize is the future for memory controller. If you take a look at the gist or the core idea, it's actually not any different from developing out-of-order processor, because all the scheduling mechanism is about that. So I think if you run interconnection network, you will be good at memory system as well. Thank you.
So the next presentation is by Ismail and Yuksel. Ismail is a second year PhD student in software research at DHR. He is one of the organizers of this story as well. His current broader research interests are in computer architecture, processing in memory, and hardware security, focused on understanding, enhancing, and exploiting fundamental computational capabilities of modern DRAM architectures. His recent publications show that commodity DRAM chips without any modification to the chip itself, only with modifications to the memory controller, are able to execute bulk bitwise computation and data movement operations.
Thanks a lot for the introduction. How many minutes do I have?
Doable. No, it's doable. It's doable. Hello, everyone. Thank you for the introduction. Today I'm going to present the work that I presented in Micro 2025 last year. So let's get started. So this is a typical CPU and DRAM model that you have seen many times today, and I'm going to quickly skip these. And to remind you, this is a DRAM model and how it looks like in a DRAM chip, multiple banks. We have many subarrays, and in a subarray we have many DRAM cells that are connected through word line and a bit line. And here, bit line is important for this study. So I guess you also know that read disturbance is a problem in modern DRAM chips, and it breaks memory isolation, and one of them is row hammer. And in this pictorial example, here we have 3 subarrays connected to DRAM column, sense amplifier, row. And in order to induce a bit flip, what we do is in row hammer is that we hammer an aggressor row, and then we get a bit flips in physically adjacent victim rows. And then another phenomenon is row press. Instead of keep hammering, we keep the row open longer, and keeping a DRAM row open for a long time causes bit flips in adjacent rows in the same subarray. So row hammer and row press are, as you can see, row-based read disturbance phenomena that affect only a few neighboring victim rows that are close by to the aggressor row. And most of the today's mitigations work by detecting a high row activation count or high row open time, and refreshing a few neighboring rows, for example, +4 and -4, as specified in JEDEC for DRFM. And even today, detecting and refreshing even only a few neighboring rows is shown to be a difficult problem. Even in this year's ISCA, we have many row hammer mitigation papers. So in this study, we asked the following question. What if there's a much worse read disturbance phenomenon that affects thousands of DRAM rows through the bit lines? So it turns out there is one, which we call column disturb. We observe that by repeatedly opening or keeping a DRAM row open, it is possible to disturb many DRAM cells on the same column. And with column disturb, the activation of a single row concurrently affects DRAM cells across as many as 3 DRAM subarrays, which can be also translates to up to 3072 DRAM rows. So let's start with what is column disturb. So column disturb is fundamental different phenomenon than row hammer and row press. It is a column-based read disturbance phenomenon that affects thousands of rows by hammering or pressing a single DRAM row. Why this happens? Because activating a row perturbs all the columns that are connected to that row. And as a result, cells in all perturbed columns are affected. And also, half of the columns in neighboring subarrays of the aggressor subarray are affected. Why? Why is that the case? This is because the open bit line architecture that modern DRAM employs. Columns of a single row span multiple subarrays as these columns are connected to the same set of sense amplifiers due to the aggressive DRAM scale. So consequently, column disturb affects cells that are vertically connected to the same bit line DRAM. And here, the real difference is the real difference is the columns are the victims instead of the rows are being victims. So in order to test this phenomenon, we use a DRAM Bender, a DDR4 testing infrastructure. And this one is one pictorial example of DDR4 setup. And we also test HBM2 chips in this study using the DRAM Bender setup as well to control our fine-grained control over DRAM commands, timings, and temperature. And in order to test many DRAM chips, we use our laboratory to understand such issues, including this work. And in this study, we test a total of 216 DDR4 chips, DDR4 and 4 HBM2 chips from 3 major manufacturers. Actually, I tested many more. I guess it's a course of 1 and 1.5 years because it was taking so long to find DRAM chips that are vulnerable or like more pronounced there. So I think
I can safely say that it's more than maybe 400. But in order to do these studies, I needed to test a lot of chips, and it needed a lot of experiment time. So I think the comprehensive testing is done here safely. We can say 216 DDR4 chips and 4 DRAM chips. So in order to test, what we do is that we prevent source of interference during the core test loop. So there was no DRAM refresh to avoid refreshing victim rows, no read disturbance mitigation mechanisms are employed, and no error correcting codes. Also, we filter out row hammer, row press, and retention bit flips to observe column disturb bit flips and to show they are new and unique. So you can find more details in the paper, and it's on archive. And let me give you the quick summary of the metric that we use and the access pattern. So we use the minimum time required to induce the first column disturb bit flip. Lower is worse. The translation for row hammer is that it's a hammer count first or activation count minimum. And the number of column disturb bit flips in a subarray, since column disturb affects multiple subarrays. And in order to show the vulnerability, we use this metric, and here higher is worse. And number of rows with column disturb bit flips in a subarray, and again, here higher is the worst. What we do is that in our testing, we select one aggressor row, and we keep hammer this, and we read the 3 consecutive subarrays to record the bit flips. And we use a commonly used access pattern activation of as a single-sided row hammer and row press. So we carefully sweep many data patterns at temperature 45, 65, 85, and 95, and we test different aggressor row on time. Let's say the time that we keep the aggressor row open, and we sweep the DRAM refresh interval to test how severe the column disturb is beyond the refresh interval. And we test multiple aggressor row location to really understand, is this a column-based phenomena? Do we get the same bit flips when we change the, let's say, the row location? And also we test more than 49,000 subarrays, and this, which translates to more than 4.5 million rows, and all subarrays in all banks across all DRAM chips. And we have 5 key takeaways from this major characterization. The first one is the column disturbs a wide spread read disturbance phenomenon and becomes worse as DRAM technology scales down to smaller node sizes. So here we show the first result that leads us to first takeaway. Y-axis shows the time to induce the first bit flip in a subarray. X-axis shows the DRAM die division and density, and each subplot is dedicated to a different manufacturer. And here is the result. And as you can see, all tested DRAM chips experience column disturb bit flips. And for the second observation, let's first focus on one manufacturer here, for example, SK Hynix. We observe that from A die to D die, the minimum time to observe the first bit flip reduces by up to 5.1 times. And note that 8 gigabit D die chips are newer than 8 gigabit A die. They're, I think, 4th generation compared to the A die being 1st generation, according to their datasheet. And we also observe a similar reduction in 16 gigabit A die to 16 gigabit C die. And we conclude that newer chips tend to be more vulnerable to column disturb bit flips. And this is also consistent across all tested manufacturers. From the same die density as die generation advance, we observe a lower minimum time to induce the first bit flip. So another observation we made is based on the lowest time to induce the first bit flip, and for each manufacturer highlighted as red. And we observed that in some real DRAM chips, they experience column disturb bit flips within the nominal refresh window, less than 64 milliseconds, under nominal operating conditions. And moving on to second key takeaway. So here we show that column disturb induces bit flips in thousands of DRAM rows and is different than row hammer, row press, and retention failures. So in this experiment, we compare, as I said, column disturb with row hammer, row press, and retention. On the y-axis, we have the number of bit flips now, and we have on the x-axis, we have the row addresses covering the first 3 subarrays. And the first 1024 rows belong to the first subarray, and second belong to the second below. And here, what we do is that we use a single aggressor row for column disturb row hammer and row press, and it is located in the middle row of the second subarray. And let's take a look at the first row hammer and row press bit flips. They induce a lot of bit flips. As you can see, it's around more than 7,000. And however, but in only the neighboring rows of the aggressor row, +1 and -1 rows concurrently. And for the retention, we observe that there's a monotonic trend. Retention failures are almost constant, around 500 for every row. Here in this experiment, we do this hammering, retention, and column disturb experiment for 16 seconds. And now for the column disturb, as you can see, it induces many more bit flips than retention failures and affects many more rows than row hammer and row press, namely all rows in 3 consecutive subarrays. And for the third key takeaway, the bit flip directionalities. Here on the y-axis, you see a number of bit flips in a subarray. On the x-axis, we have the refresh interval, and each subplot dedicated to direction of the bit flip. For example, the left one shows the cells initialized with 1 and experience bit flip and thus becomes 0 after the experiment. So as you can see, column disturb induces only 1 to 0 bit flips, which are the same direction as retention failures. And this is in stark contrast to row hammer and row press, which induce bit flips in both directions. So this shows another key unique characteristics of column disturb. And the fourth one, which is more important to retention-aware refresh mechanism, is that significantly more rows are vulnerable to column disturb than retention failures. So in the y-axis, we see number of rows of bit flips in a subarray at 65 degrees Celsius, which is not the highest that you can get, to show the severity, basically. And each subplot is dedicated, again, a different manufacturer. And the x-axis, we see the refresh interval. For example, let's take a look at one of the manufacturer. And as you can see, for the refresh interval of 1024 millisecond, column disturb induces bit flips in significantly more DRAM rows than retention failures. And it can go up to, let's say, for example, for this point, it can go up to more than 300 rows. And this trend is also consistent across all tested manufacturers. And we see that even in some other manufacturers, we see more than 35 times more bit flips. And lastly, as the temperature increases, the DRAM chips becomes more vulnerable to column disturb. So here, on the x-axis, we see the time to induce the first bit flip. On the y-axis. On the x-axis, we see the tested temperature results. So here, take a look at, again, the one manufacturer. We see that from 45 degrees Celsius to 95 degrees Celsius, the time to induce the first bit flip reduces significantly, namely more than 9 times. And this is also consistent across all tested manufacturers. As the temperature increases, time to induce the first bit flip becomes lower and lower. And the observations that I presented have implications for the future systems and retention-aware refresh mechanisms. So first, the implications on future computing systems. So column disturb could jeopardize robustness of computing systems since its bit flips occur in very far away rows from the aggressor row, even in nominal operating conditions, and it's getting worse. Newer chips are become more vulnerable. And the second one is implications to retention-aware refresh mechanisms. So column disturb dramatically decreases the benefits of these mechanisms because at the long refresh interval, for example, more than 512 milliseconds, a large majority of rows experience column disturb bit flips, and it induces significantly more bit flips than retention failures. So I already talked about this. For the time being, I'm gonna very quickly summarize them. The issue is that even in the nominal operating conditions, we see bit flips in 374 rows away from the aggressor row. And most of the mitigations work by just refreshing only a few neighboring rows, for example, crack. And even refreshing only a few rows is shown to be a difficult problem. So in this paper, we describe and analytically evaluate 2 solutions: an increasing DRAM refresh rate, which reduces the DRAM throughput by more than 40 times, and practically refreshing victim rows, which reduces also the DRAM throughput by more than 10%. There are more details in the paper, and here Andreas will talk about the more intelligent solutions to column disturb, which induces less performance overheads. So for the retention-aware refresh mechanisms, so to give you a quick background, the retention-aware refresh mechanism leverage the heterogeneity in DRAM cells data retention time. Most of the DRAM cells do not to be frequently refreshed, which means that for these rows, refresh interval is increased to improve the performance and energy efficiency. However, now in the presence of column disturb, by increasing the refresh interval, a lot of rows becomes vulnerable to column disturb. And these mechanisms, as a result, do not work. To make these mechanisms work, column disturb bit flips must be mitigated. If these mechanisms configured to be mitigate column disturb, now they lose their performance and energy benefits. So there is a need for more intelligent solutions with the synergy with retention-aware refresh mechanisms and read disturbance bit flips. And again, I'd like to refer you to our paper for more details on how we deal, let's say, evaluate the implications more. And there are more results, characterization results in the paper, more details and analysis on implications. And you can find the paper on archive. And let me quickly conclude my talk. So we demonstrate an extensively study a new widespread read disturbance phenomenon in real DRAM chips, which we call column disturb. And we characterize more than 200 DDR4 chips and HBM2 chips. And we see that column disturb affects all tested DRAM chips, and it's getting worse as DRAM technology scales, and it is different from row hammer, row press, and retention failures. And we describe and evaluate two major implications of column disturb, which column disturb affects robustness of feature systems and makes retention-aware refresh mechanisms much less effective. And we hope that column disturb inspires system-level, architecture-level, and device-level solutions and understanding to enable column disturb resilient feature systems. Thanks a lot for your attention. I'm happy to answer your questions. There's one.
Thank you for that interesting talk. I was wondering the comment you mentioned about the filtering out other than filter, because I'm like not an expert in silk, but for me it comes down to all like linkage, right? Like and the electron migration or like cross coupling. Those are making eventually the impact of every like vulnerability we see. And on top of that, I think there's like a lot of randomness coming from the DRAM cells. So I was wondering what was your approach of filtering out other possibility? Because I don't know, in my head it kind of correlates all together. So I want to know your insights on that. And then the second one is just I was very curious to know, because you tried so many DRAMs and then like HBM, and you've seen so many patterns of like row hammer keep going on. And were you able to find like a trend between like the density, how the denser the DRAM gets and how it is eventually going to go, and like can you even predict the future of how vulnerable it's going to be, and was it like matching when the DRAM come up?
So for the second one, so I don't know the internals, unfortunately. There are some people knows, like DRAM manufacturers. But what we see clearly is that once the die revision advances, there's the minimum time to induce the first bit flip decreases. So if I can quickly find that one. Yes, I think this one. So for example, for Samsung, as you can see, 16 gigabit A die, B die, C die. There are still outliers, as you can see, because we're testing all the rows, all the things, but maybe they're not in the worst case or anything, because there's a huge parameter space, right? But in our results, what we see is that there's a trend. In the same die density, once the die revision advances, the time to induce bit flip decreases. But that's not necessarily the case from one die density to another one. For example, in SK Hynix, 8 gigabit D die is worse than 16 gigabit A die. But in the end, we don't know the internals, we don't know the manufacturing node or other mechanisms. So what we can just do is to test this rigorously and make sure everything works. And this is coming from column disturb, and just to observe and provide some insights if possible. And for the first one, you were saying if I repeat the question again, it was, so there are many bit flips and they might be correlated to each other. How would you filter this out? So there are actually established mechanisms for example, retention. So you test, there's also variable retention time, right? So that was one of the most painful thing that I did because it was changing all the time. And it was a very long, like more than a course of years. So we were testing all the data, many data patterns as possible, fuzzing, all these things. And we were making sure that, for example, we get a column disturb bit flips here. And we were making sure that this is not retention by testing, I don't know, for a cell more than 1,000 times even. And with many, many different data patterns, not just the ones, to see that this is not really retention. And I think for the raw hammer and raw press, there are many device level works and there are many, let's say, real chip characterization works from our group, from Junhoa's group. And it's really, they're happening in physically adjacent cells. And as you can see, there's a clear trend for here. So once you do, for example, raw hammer, which you just have the TRS of 36 nanoseconds, you're just hammering it and it's there. And raw press, it's there. And others are not here. And for column disturb, what we were doing is that we were changing the aggressor row location. I told like just 3, beginning, middle, and end, but I was also fuzzing around those to understand this is really a column base. Because if it's a column base, whether you, for example, you hammer 1024, you will see the very similar number of bit flips, right? So this is how we actually also cross-check. Once we do, for example, once we change the aggressor row, their neighbors were skyrocketed from 3,000 to 7,000 or 6,000, depending on the location. But this picture was consistent. Hope this answers your question. Yeah, thank you. There's 3 more. Thank you.
And also the follow-up question.
Yes, the column keeper, the mitigation.
So the reason I talk about this is that, so because this one is showing that for label by actually showing that, and I look at my server. So I spend quite a bit of time saying that, oh, this one is here, and this about isolated environment. If you want to do it in your server, is just wondering whether you succeeded in reproducing column disturb servers.
In real systems. Not yet, not yet.
So yeah, I mean, I thought it's meaningful, but I just want to kind of have a walk from the.
Yeah, I think that's a great question. This is not really as pronounced as raw hammer or raw press right now, but what we think that this is really getting worse as all the other DRAM read disturbance phenomenon gets. And this is also DDR4, not HBM3, not HBM3, not DDR5, because there were no reliable platforms to test. And we don't know. Only thing, let's say, the best that our effort is that we can just plot this and show that this is getting worse, and we can maybe do something to mitigate it before it's getting widespread, that end user will see it. Hopefully, yeah. But that's one of the things that I would like to also do. Thank you. Yes. I want to 0, not the other way. So, to the best of our guess, if I can find it. So what we say is that this is, so for example, for retention, there are many ways to leak the electrical charge, right? And some of them are more dominant for retention. What we believe is that here, what we're doing with column disturb is that we are keeping the bit line not at, for example, pre-charge level, VDD2 level. We're keeping the bit line at ground, 0, and we increase the difference between the cell and the bit line's voltage, right? So what I think is that I don't have anything yet concrete, but this could amplify some other parts, the leakage paths that retention does not, and it leaks more and more. That's my best guess. But I believe there should be more upcoming, let's say, papers on TCAD or like what they have done for row press, row hammer, to explain the inner workings for this to better. But all I can think that is that this is because we don't see, for example, if we do instead of having the difference, what we do is that actually cell is 1, the bit line is always at 0, and this leaks more. But if the cell is 1, a bit line at 1, it's not the same. So there's a really hint there that I think, and that's my best guess, I will say. Mm-hmm.
I know there's a definition-wise.
Mm-hmm. Mm-hmm. So how do we test these? Again, let me here, I guess. Yes. So how do we test this? So 2 things also. So since column disturb is 1 to 0, right? We didn't know that. When we do 0 to 1, so basically victim initializes 0, and we were hammering. We were just seeing row hammer and row press bit flips, and retention was there still, and the retention was not there. So we were only seeing row hammer and row press, and it was really happening due to the, I think, the physical layout of 6F square. It was the physically adjacent rows because of how row hammer and row press works. What we do is that we actually added more guard bands. Basically, normally what we were seeing is +1 and -1. And in the JEDEC standard, for DRFM, the most aggressive one is +4 and -4, and there is also half double. What we did is that when we were taking this into account, we actually filter, I think, +8 and -8. And this could actually even, maybe we were finding even worse cells, but we were not account for that. But I think this is the best, again, the best effort that we can do. In the end, there might be some correlation between them. But still we don't know. So that's the best, let's say, methodology that we can employ for now. Thank you. Yes.
I want to touch upon a little bit on the GPU part, like this year there have been a lot of papers like SMP showing privilege escalation of GPUs. So I understand from problem research perspective, the time to induce these flips was quite high on the HBM that we tested. What do you expect to happen? You also expect HBM to be vulnerable to problem research into production settings. So
I mean, I would love to answer this very directly, but in the end, we need to test this, right? So the best thing that we did is in HBM2 and with some sort of temperature control, not fully. What we were seeing is that there's really still a trend that we observe in DDR4, but from 4 HBM2 chips, which is probably from 2017 or 18, something like that. But so since all those newer HBMs goes to GPUs, and some other accelerators. There's no, unfortunately, FPGA or that's, let's say, testing platform for us to implement DRAM benders like HBM3, HBM3E. All of them are booked for probably, I think. That's what I saw from news. Even the DDR5, still, there's no really that reliable as DRAM bender. That's why, I mean, what I can guess is, best guess is that, again, the DRAM scaling, again, we don't know. This is the die revision advances and there's a trend. And we can just say that this could go worse as that been happened to row hammer and row press. Yes. Yes, but in the end, HBM2 and HBM3, they are still, the array is based on the same as DDR4 and DDR5, the core DRAM array, right? The layout and everything. So yes, but still we don't have DDR5, but hopefully we will get, hopefully. Yeah, thanks. Any other questions? There is one more. Thank you.
If you had to create a ratio between, let's say, like the number of activates, what would be the ratio that all the server attack versus a traditional roaming attack? Like where roaming would be 3 times as fast, 2 times as fast. That's not a weird question, but just for like,
I think I get the gist of it. So let me first start with, why do we use the time to induce first bit loop? Because in column, we call it column lister, not hammer or press, because we're using both. So what we see is that if you have, let's say, if you increase a diagon, if you keep the row open, basically, if you keep the columns at that, let's say 0, you get the bit flips more. So basically, the thing is that you need to keep that column open as much as possible. And we try to correlate it with the average voltage on the bit line here. And as you can see, this is fraction of cells with bit flips. If you keep them as much as possible at the 0, the ground, you get more bit flips. That's why we use, let's say, we test many different aggressor at one time, but we report the time to induce bit, because there will be a lot of probably using AC min or things, there will be a lot of confusion. So in that case, if you think about that, like with row press, I think you can get fairly low threshold with the activation count. Like for example, with, as far as I remember, around 1000 to get with 7.8 microsecond or something like that. 7.8, for example, 7 milliseconds to get, or even less if you have to optimize it. So still, if I have to ratio it, it's still, I don't know, 15 x times maybe, or 10, but it really depends on where you hammer, what you hammer, how you hammer. Yes. Thanks a lot. Any other questions? Thank you.
That concludes the first half of the session. Can I get that show? Okay, good. You haven't. Cool. Oh, yeah. Yeah, sure. Is this one of the organizers? Yeah.
Testing. Test. Okay, it should be working fine. Cool. So if there are those of you who want to do the hands-on session and did not receive a piece of napkin from me, let me know. Cool. So I'd like to start this off with this statement from Edward Murphy Jr., because this is a hands-on demo. Anything that can go wrong will go wrong. And we will test this statement in today's hands-on session, basically. I hope we will invalidate it in our context, but we'll see. There are so many things that can go wrong. I hope nothing does. We will be doing some row hammer experiments using DRAM Bender. We will connect to, like each one of you will connect to a host machine via SSH in our lab and execute a program, ultimately execute a program that hammers the DRAM row. And we will vary program parameters and replicate some of the studies we talked about today. Well, replicate to a very little extent. And hopefully you will also understand how the program gets executed and gain a little bit more insight into the DRAM Bender API than we've given you today. So the typical DRAM Bender test workflow will look like in a C++ or Python executable, you will do 4 things. We will use Python today. We will initialize a platform object and then, or a board object in Python's case, create a DRAM Bender test program by appending instructions to like a list, basically, and execute this program and then read and analyze experimental data. Just as an aside, this is what one of the platforms we have look like, FPGA-based setups we have look like. So over PCIe, it connects to a host machine, and you will be SSHing or connecting remotely to that host machine. So you will send programs to the DRAM Bender logic inside the FPGA, and you will receive data from this FPGA board via the PCIe. Just like as another side note, these transfers happen over 2 key file descriptors. So the Xilinx IP that we use to manage this PCIe connection will register host to card communication, like programs in our case, as XDMA0 underscore H2C, that's host to card file descriptor, and the other way around is the other one. I think this is just like, for you to understand how communication between host and FPGA board happens. The prerequisites for our demo today are 3 things. Well, 2 things and an optional thing. First, we need an SSH-capable laptop or computer. If you have Bash, we have a script that you can run to automate the SSH setup. And you need a means for interacting with the DRAM Bender host machine. That can be a terminal session, or you can attach your Visual Studio Code instance to that machine as well. We have 19 host names. We had 19 host names available on that front desk, but I hope you all have one host name. So that's no longer a problem. Please go to this website now. On your laptops would be better, because I'll ask you to download a zip file that contains the SSH setup. And I'll give you a minute or so to do that. This is our website, event website. And then there you will see, yes, okay, that was too fast. That's our workshop website, if you have it open somewhere else. Cool. So there you will see a download button hidden under DRAM Bender machine access files. You can search for this, any of this files, or download, and find that button there. If you click it, you should be downloading a zip file that doesn't contain any malware. So did anyone not download the zip file yet? Perfect. Then we will go on and unzip that file. And that file basically contains two things. The first thing is the SSH config that you would add to your basically home directory.ssh config file that registers this host name as an entry that your SSH connections can use basically easily. And the other thing is a private key that you need to use to access our setup. If you have a Linux-like system or a Mac OS system where you have the terminal, you can just execute this /install ssh config script, and the host name there will be the host name on your napkins. So if you do that, the script will add the config file, append 2 lines to your config file, 2 entries to your config file, and then you will be able to execute the SSH host name line to connect to one of the machines we have. So here, I think things can go wrong. We will help you out on case-by-case basis. If you cannot execute the script, we will have to. I'm having SSH already. Perfect. So yes. So when you do this, you immediately get something. Okay, so for demo PK. Permission denied public key. I think the public key, the private key we have is maybe. Okay, let me try this. Let me try one. Is anybody getting authentication error issues?
I downloaded it.
Yeah. I think it's the private key that has the problem. Yeah, that's my fault. Can you look at the private key? Can you vim that? So is there something obviously wrong here? You see? No. Okay. No. Yeah, sure. Okay. In the worst case, I'll go over the steps myself, and I hope you will follow. But let's give this 5 more minutes. Yeah.
I have to.
Yeah. Yes. So if you extract this to this zip file.
Extract this somewhere. Right?
Yeah, anywhere. Download. Yeah. Extract over there.
Oh, yeah.
Yes. Exactly. So now you should
go to documents.
yes.
This, your last, this one of that's it.
You could like open a terminal session there in that directory. Because we have to run this script. Yeah. What happened?
48, yes. Just maybe we can just because if this doesn't give any.
Either it's like a private key permission error, or it's like the private key itself. When I uploaded it, I broke the format. And that's why. Does it work? Oh my. Yes. Problem is.
I have this now.
Yeah. So if you do this, install SSH config, and then Safari dash FPGA-20.
Oh, yeah.
Yes, exactly. Then now you should be able to connect to.
No, wait.
Oh, sorry.
So the SIM10 is my machine. Sorry.
Yeah.
Okay, just SSH Safari-FPGA 20.
formatting.
Okay, yeah, there's a problem with the private key format. I will try to deal with this very fast. I don't know if I can. Yeah. Oh yeah, you got it? Okay, then that's Safari-tutorial. Oh, that was on the slides here. So we got the right private key. I think it got corrupted somehow for some downloads. But if downloading again will probably yield the same result for the same machines that got this. So I'm thinking about it, but
it's not working. No capital, nothing.
Oh, wait. Okay, this doesn't work for some reason on your on top for a different reason than what we're getting in the back. So I think okay. So the issue there is even bigger. Did anyone succeed at all? No. Okay. Maybe what we'll do is I'll go over the Python scripts that I was going to take you over myself, and then this will be a Murphy. Yes. What happened? Did you succeed? What's that? The host name is on the napkin you received. Oh, you didn't receive a napkin. Permission denied. Okay, that's a different problem.
It's the same issue, no?
If it's
invalid.
Yeah, probably. Okay, I don't think I can fix that in the time we have left. Sorry for that. So I'll go back to this slide. We have validated this statement today. One of the things we had went wrong. So I'll continue with the demo myself. And I think we understand what the issue is, but probably it's going to take us a few more minutes to patch this. I would like to finish the tutorial. I can try, but I don't think we're going to. So if you contact me, I will figure something out. Yeah. So what I was going to take you through is basically 3 programs, two programs, but in three different Python scripts that read and write or write to your DRAM chips under test and then read from them, and then run a rowhammer program to cause a lot of rowhammer bit flips. I'm not gonna do the prerequisites myself, but again, if you're interested, we will open source this. New API. This is a new API, Python-based API. So we have been using C++ for now, until now. This is a new thing that we're going to release soon. I'm going to go ahead because I ran these most of these prerequisites myself. Start with the core tutorial material. The first thing I'd like you to take it through is this read-write walkthrough script. So if you look at this script and see what it does. It's using the new Python API, and the structure of the code goes like basically some arguments that might be interesting for you. Yes. Yes. A little bit less big for me to see things. Yes. It takes a bunch of arguments that are not all of them are relevant for today's tutorial, but some interesting things are like bank, row, pattern, and maybe show program we're going to explore today. So bank, row, these are DRAM organizational parameters. So which bank you want to test, which row you're targeting. And then pattern is going to be your 32-bit data pattern, as you can see on the right here. By default, it's deadbeat for this program. And show program is an interesting utility that we have that was going to show you basically almost the assembly instruction level DRAM Bender program dump when you enable that. What this program does is something very simple. So this Python API comes with a bunch of built-in programs that are very useful for you to use and build bigger programs with. We have write and read row programs, and I'm gonna take a look at these as well very soon after I take you through this whole Python script. And what's gonna happen here is we write a row to the, we write the deadbeef pattern, unless something else is specified, to this DRAM row targeted by the bank and row parameters, and then we're gonna read from it. And once we read back from it, we're gonna compare that data pattern that we read with what we wrote. And that's the whole, like when you think about the whole Python script, that's what it does. There are some additional structures here, like these are some new constructs we added. To read something back, you call this make row buffer function, and then you can create basically different Python objects. The expected data is another row buffer object that that expects the pattern that we just wrote to our DRAM chip, and then we're going to compare these two together. Then there are some other constructions like this function called open DDR4 board, because this is a DDR4 setup. You're going to be using this function call to basically get a board object that you can use to manipulate the state of the board that we're using to test DRAM chips. As far as manipulating state goes, I think the most important three functions are these. So this is reset FPGA. It's going to send a like a user reset signal to the FPGA board, all the logic inside the FPGA board, and try to get DRAM Bender to a known state. And we do this before executing almost any experiment. And then the execute function does the host to card transfers that will basically carry over the programs we've created earlier to the FPGA board for execution. This execute call is a bit special, so it will actually do two executes back to back. First, the write program will get executed because this is like an array of programs. Once the write program gets executed, it's done. Then the DRAM Bender board will be able to accept the next program. So then the read program will be executed. So I'd like to make that distinction. Basically, these are not appended into a single program and then executed. These are executed serially. The receive into function will pull all the data that the DRAM Bender FPGA board sends into this buffer we've created earlier called readback. And synchronize will ensure that the DRAM Bender setup is not sending any other data before. Basically, it's a blocking call that we can use to prevent us from making progress in this call block until the DRAM Bender board is done with what it's doing. So that's like an overview of the program. I'm going to execute this, but for that I need my Oops. So basically, this output here is saying it's passed because we wrote 2048 words into row 0, and when we read it back, and when we read it back, we got the same data that we wrote to it. Now, I'll show you something more interesting here. If you have this show program argument here, it's going to show you a nice sort of print out of the program we've created. And this is full of DRAM Bender instructions. Now, those instructions are documented on a spreadsheet that we have in the main GitHub repo, but I'm going to show you what it looks like. This is the whole, okay, it's going to come up soon. Maybe you can't see it very well, but we have the ISA nicely documented on a Google spreadsheet that you can find the link of here. And these are all the instructions that we have for DRAM Bender. Most of these are what we call arithmetic and control flow instructions. That's on the bottom side. Those are larger instructions that you can use to manipulate DRAM Bender's programmable core state. And then there are also DDR instructions, well, now DRAM instructions per se. And these are smaller, so it's like we have internally something like a very large instruction word architecture inside that you use to create batches of DRAM instructions and then issue them at once to your DRAM chips. And these instructions, these DRAM instructions, are the key that makes DRAM Bender such a flexible infrastructure to use for testing. And going back, okay, so this is the dump we've seen. So these instructions are all in that spreadsheet over there. You can find the semantics of those in that spreadsheet. But I told, so we earlier in the workshop we introduced some of the DRAM commands of what they do. So here I told you that this program was writing data to a row and then reading from it. So this is the first program. It's reading some register values. Sorry, it's loading some register values to the bank address register, for example, and row address registers. And those are arguments we supply to our Python program. So if I change the row argument here, we should see that the programs are targeting a different row now. Maybe I am missing something. Okay, it is saying that it's targeting row 1, so I'm going to trust it, but I don't see it in the dump. Anyways, we'll figure this out later. So this is useful for debugging because you will, if you're using this seriously, then you will introduce timing bugs. For example, you will mistakenly add some read command, let's say right after another read command that will not satisfy some DRAM command timing, and then you will get something back that you did not expect to see. And this sort of instruction dumps will help you visually debug that process. And in the new API, Python API, we have constructions that help with debugging timing-related issues that are much more powerful than visual inspection, but I will not cover them in detail. I'll leave that to Haocong if he wants to talk about it. But I wanted to mention that because this is the power of the new API. Yeah.
So if you really want to make sure about the time, the execute English program, of course, the minimum maximum activation, read, these kind of things. So you can be confident that you're not accidentally making time mistakes.
So I'm going to show you also one of the built-in programs and how they look like, because that's what you would really, I think, how you would really use the Python interface to create new programs. And that's going to be in built-in programs here. We'll look at read row, and this is going to look very much like that instruction dump we've seen earlier. So here we're creating a program using the program builder object. LI is a load immediate instruction. So this is going to take your bank address argument, that's bank, and create or append an instruction to this list of instructions, a load immediate instruction that fills up the bank address register with the bank ID. And the same thing for the row address. And here are some like control flow that's going on. If you're targeting an HBM2 board, then you have to do some other things. We're not going to go into this in too much detail. And if you want to create DRAM instructions, I earlier mentioned that you have to create batches of 4 instructions at once. So this is like one such structure here. We are creating a DRAM instruction or a set of 4 DRAM instructions here. The first being pre-charge command, the pre-charge command to this bank address register or whatever stored in the bank address register, and then combined with 3 other knobs. And each cycle here, or each command here, corresponds to one DDR bus command cycle. So in this case, it's going to be 1.5 nanoseconds. So these 3 knobs take 4.5 nanoseconds to execute. The first one, the first pre-charge command also takes 1.5 nanoseconds to execute. So if you immediately like appended another batch of DRAM commands here, the delay between the pre-charge command and the next pre-charge command is 6 nanoseconds. And this is very good to know or keep in mind as you create your DRAM Bender programs. And yeah, so that's what I wanted to show you. Basically, it's a very easy way to program this logic that we have on the FPGA board to create all sorts of different, let's say, DRAM experiments or DRAM Bender experiments. So going back to the tutorial, I think I showed you the dump of the instructions. I'm going to show you something interesting. This is the read-write exercise. So this is going to write something to a DRAM row, pattern A to a DRAM row, and then pattern B to a different DRAM row. And then, okay, it's not happening in this one. But what was happening earlier before, there's something I want to disclose about DRAM Bender's first bank. So that's bank ID 0. Bank ID 0, row 0, periodically gets read because of, by DRAM Bender's maintenance logic, let's say, because of AMD's, now back then it was Xilinx. Xilinx's, say, requirements to keep the PHY interface calibrated. You would need to issue a read instruction or read command every microsecond. That was the requirement in the listed in the IP. So there is some logic in DRAM Bender that does this, and it targets bank 0, row 0. So if you, in your experiments, find something shady happening in row 1, meaning you get bit flips when you don't expect to, that's our DRAM Bender maintenance command scheduler hammering row 0, thereby inducing bit flips on row 1. So I recommend everyone to test bank 1 instead of bank 0 if something like this happens. So that's good that I communicated that across. We're gonna do the row hammer code now. So this is the third part of the tutorial. Because I didn't get what I expected to see in the second part, I'm gonna switch to the third part. What you're seeing here is a bunch of like output printout lines, but we've hammered row 81 and we've seen bit flips in row 82. 61 bit flips in one row. When we hammer another row, we get 68 bit flips, and you see the variation across DRAM rows here. Yes. So that's a good question. So the default parameter, I believe, is 500,000, and we can change this and see what happens. And this is what's really exciting about DRAM Bender, I think. This was 500,000 hammers, and here you can even see VRD, variable read disturbance, where we hammer the same set of rows, and in two different instances, we got different number of bit flips from each. But if we change this hammer count, let's say we hammer twice as many times, you're gonna be right in expecting the number of bit flips to increase significantly. So you're hammering things double the amount of times. That was 500,000 hammers, now it's 1 million hammers. And it works in the opposite way also, right? So if we hammer only 100,000 times, we're gonna see fewer bit flips. In this case, even no bit flips for this specific module. And you can play with this and see how your DRAM chip reacts. In fact, you can use this program that we provide along with the tutorial to actually characterize the row hammer vulnerability across like a DIM you're interested in. You would supply this number of victims parameter with however many rows you have in your chip, and the program will run and collect all the statistics you need it to collect. That will conclude this part of the tutorial. I really wanted this to be the hands-on thing, but things went wrong unexpectedly. But I'd like to still thank like a lot of members who tried to or gave their best to get you an accessible, let's say, DRAM Bender setup in our FPGA lab in Zurich, but it didn't quite turn out as we expected it to. So moving forward, those of you that are very interested in using this platform, please contact me. I'd like to actually make the hands-on session succeed, maybe in an offline way. So we'll see how that goes. But as far as me showing you how DRAM Bender works goes with the new Python API, this is going to be it. And I invite now Richard for the Ramulator hands-on session, if you're interested. By the way, I'm happy to take questions if you have any at this moment. Okay, thanks. Yes. So assuming you have the FPGA board or no? Yeah, assuming you have the FPGA board and the desktop machine, you just need to install like any Ubuntu version, and the dependencies are quite small, I would say. So we already published the streams that you can download to your FPGA board, and it makes it readily available for use. You don't have to compile things from scratch. The only dependencies are like Python and C++ compilers.
There's something with DDR. So how can we integrate DDR chip actually? Like,
excuse me,
how to connect DDR chip with FPGA?
The DDR chip on an FPGA.
So it will be through PCI 3 bus.
Yeah. So the FPGA board, if you want to connect it to any host machine, you need the PCI interface. Most desktop machines have a slot for you to put these boards in. So that will not be a problem, I'm assuming. And then the boards already, I mean, U200 boards is the most, I think, well-supported board we have. I'd recommend everyone to get that if they can. I think they're being discontinued, so we will have to find another board to support soon. But that board comes with 4 micron RDIMMs. So it comes with modules you can test already. You don't need to buy any new modules if you buy the FPGA board. That depends on the FPGA board you're testing, but we have a lot of support, as you've seen probably earlier in the presentation. We support 6 FPGA boards out of the box. And that means if you have the FPGA board and if you have the desktop machine, you can just download the GitHub repo, run some scripts, and start using it. Yeah.
Thank you.
That's all.
I should join Zoom from my laptop.
Yeah, that would be good.
Okay, that would be best. Can you send me the Zoom link now? Okay, I'm in. So the agenda is I will first go with like a deeper introduction on the technical side and the organization of the of Ramulator 2.1, then followed by basically like a notebook that shows Ramulator 2.1, but I will just share my screen. Okay, so hello everyone. I will give like a deeper technical deep dive into Ramulator 2.1. So yeah, first I will just go over these again in case we have some new audience. It's a major overhaul of Ramulator 2.0 that improves in many aspects. It's already up as main branch in our GitHub repo, and it's code space and dev container ready. And the old version we have archived it. and we welcome your use, contribution, and feedback. So we already configured Ramulator 2 to be ready with GitHub code space. So if we go to the GitHub repository and navigate to this button and click on create code space on main, then you will get like a very cheap VM that with all the dependencies, environments, or configured that you can directly jumpstart playing with Ramulator 2. And alternatively, if you want to do it locally on your machine, you can just clone the repository, open VS Code. Because we have the dev container setup, it should prompt you to either reopen in container or like clone it in a volume to have better IO on Windows. And if this doesn't show up, you can press F1 and type reopen in. There's an option to reopen Ramulator 2 in the container. So for these two steps, it may take some minutes to build the container. So I recommend you, if you want to do it, like please do it now. And of course, like if you want to like do it real local, like if you want to like raw dog it, you can. We have like the Docker file and some post create script for you to build your own container fully locally without like maybe like Microsoft slop. If you want to participate in the hands-on session, I recommend you to do like either of these steps. And I would recommend like, if you have a GitHub account, this would be the easiest step because it's your browser. You don't have to do any installation. So yeah, and I will continue with the, let's say the rest of the deep dive. And I anticipate that when we finish talking about the code, we should have the environments ready to run the notebook. Yeah, so first let's take a look at the source tree of Ramulator 2. So we have like these, so here we list some of the most important directories for you to find the codes for. So in examples, we have like example configurations, simple O3 example trace file, and an example gem file configuration. And then we have the Python/Ramulator directory. Here, there are two kind of code. First is the automatically generated Python wrappers or proxy objects of your C++ source. Because those are automatically generated by our build system, it's not expected that you need to log over them. But there's a real piece of user-authored code, which is DRAM. This is where the Python-based DRAM specifications are at. Then we have resources, which contains a verified Gen5 wrapper. Then source Ramulator. This is where most of the simulation logic lies. So these are like the C++ code base. Here we mainly organize them by the different interfaces, except for base, where the software framework and utility of Ramulator 2.0 lies. The other subdirectories under source Ramulator, they are basically essentially the names of the interface that corresponds to the component. And for example, controller stores all the source code of the memory controller. Under that, we have like i_controller.h, that's the header for the controller interface. We also have a sub-directory called implementation. There we have a bunch of concrete implementations of many different memory controllers. And then we have DRAM. That's where the automatically generated C++ source of the DRAM device modeling code from our build system lies. And yeah, you also have other components like front-end memory system, blah, blah, and the source Ramulator directory. And then we have tests, where we organize the tests into like smoke test, device timings, controller scheduling, and latency throughput tests. And in latency throughput test, you will find a notebook called like grid.ip/mb. If you execute that, you can reproduce the grid of latency throughput plots that I showed for all the DRAM standards in the introduction this morning. And now let's dive into the software architecture, or let's say how the Ramulator models the memory system. and we will go from like a top-down approach. So the two top level components that every simulation must have is first the front end and second the memory system. So no matter how you use Ramulator, either running it standalone or integrated with your own simulator, you must have these two components for everything to function. So the front end can be either like one of the built-in core model, for example, simple O3, or a simple memory trace parser where you like just parse a text file containing the load store addresses. Or this is also where your customized wrappers for your own simulators lie. So essentially what the front end does is take whatever information it has and creates the memory request object and tries to send the memory request to the memory system. Of course, the memory system can either accept or reject the current send request. And the memory system is a high-level encapsulation of basically everything in the memory system, controller, DRAM, blah, blah. And for now, like it just a encapsulation of one or more memory controllers, and its responsibility is to send the callback to the front end upon the completion of a memory request. So now let's dive deeper into the memory system. So currently the most basic generic DRAM system, it contains a channel mapper and one or more memory controllers. So a request from the front end, it will first go through the channel mapper, where we map it to the specific channel and the scripts that the channel gets from its address. And within each memory controller, the arrived request will go through the address mapper, where the address will be constructed into an address vector, which essentially corresponds to the topology of the DRAM, for example, channel rank, bank to bank, row and column. Then it will go through a request forwarding module. Let's say if you have a later read that targets an earlier write, the later read will directly return with the contents of the earlier write without going through the actual DRAM. And if the request does not have any forwarding to do, depending on whether it's a read or write or potentially maintenance prioritized request, it will be enqueued into one of the request queues of the memory controller. And within each controller, for example, here we show like the example of the generic DDR controller. We tried our best to keep the tick function as easy to understand as possible. So first we have like some prologue. This does some common bookkeeping operation of the controller. It advances the clock, updates the queue statistics, and for the reads that have been completed, it drains them. And then we take the refresh manager, and then followed by some pre-scheduled hooks of the memory controller plugins and also the row policy. So here, if we have a closed row policy, this is where it may choose to inject a pre-charge per bank command. And then we move on to the actual request scheduling logic. So first, it will try to pick a best ready request from the active buffer, where we store all the requests that are quote unquote in flight. And if we don't find an in-flight request to schedule, we will fall back to see if we have any priority request, maybe maintenance or some other high urgency request to schedule. And if we still don't have any of the high priority requests to find, then we will go through the normal read-write scheduling logic. This is also where the, let's say, the current watermark-based write scheduling algorithm is implemented. So after this cascade of buffer checks, we may end up with a candidate request. So if the candidate request is ready, we will first query the row policy. Let's say if we have a closed row policy, it may choose to upgrade a read or write to the auto pre-charge version. And then we update the statistics related to this request. Everything goes okay. We finally issue the request to the DRAM device. And after the issue, we will call the on-issue hook of the memory controller plugins and the role policy. So this is where all the customized function that needs to be updated when we issue request work on. For example, for many of the row hammer mitigations, it needs to monitor the, let's say, the like when and where the activations are issued. So this is where it can be implemented. And finally, we have some epilogue, like we will retire a request if we have already scheduled the last DRAM command needed to finish this request. And if we schedule a DRAM command for a request that opens a row, we will promote it to the active queue so that we mark it as in-flight, which will prevent this request from being preempted by other requests which may cause useless activations. And finally, we have the post schedule hooks for your plugins. And now let's take a look at the most important pick best ready from function, which lies in the key of the scheduler. So this function takes two arguments, a reference to a request buffer and a customizable filter function, lambda. So what it does is that it basically queries the scheduler, which is the interface for your scheduling policy, for example, FRFCFS. It tries to find the best request based on your scheduling policy, plus your customized filter logic. So we pass like the filter to the get best request function of the scheduler interface. So if it finds a request, we do additional checks of if the timing is ready. If everything works, then that's our candidate to be scheduled. And what happens on issue command, that basically does two things. First, it updates the timings of the DRAM device based on the command and address you scheduled. And then it applies the corresponding action that this DRAM command basically does. So these two functions, what it does at the high level is they will recursively walk the tree hierarchy of DRAM nodes. For example, it starts from the channel, goes through different ranks, different band groups, different banks until it hits the lowest level or hits the organization scope of the command. And to update the timings along the way, it does so by, for each DRAM node at each level, it updates the earliest ready cycle of any of the following commands that are defined by the timing constraints. And for the apply action command, it just applies, it essentially executes the action lambda of the function on the involved nodes that will basically change the states of the node. That's like what you see in the state machine figure of the JDEC standards. Okay, now we will move on to the hands-on material. So I hope everyone already has the, let's say, the dev container already set up. If not, I will also do it on my side, so you can just follow on screen. So if you go to the ISCA tutorial branch of the repository, under examples, there's like a tutorial notebook. Yeah, this is something that looks like this. So let me just clear all output. So maybe I zoom in a bit. So if people, so yeah, first, like we just execute each cell. We do some basic setup. And then we have an example cell that shows an end-to-end simulation. Like the first cell just generates some random input trace. We can just ignore that. And then here comes the actual simulation. Everything happens in Python. Let's say first you define the DRAM that you want to simulate. You can pick from organization preset, timing preset, and followed by any of the organization or timing constraint override. Then you specify your front end. Here we pick the simple O3 core model. You specify the clock ratio, what are the traces, number of expected instructions. So the core will stop after this number of instructions have been retired. You configure the in-flight basically ROB, and the last level cache size and address translation. Then you configure your memory controller. You will tell that, okay, this controller is controlling the DRAM that we specified. The scheduler is an FRFCFS row-hit. So this scheduler essentially adds additional check to prioritize row-hits over the literal definition of FRFCFS. And there are some very interesting cases where the literal definition of FRFCFS will fail to prioritize row-hit requests, and that can be left as a maybe take-home exercise or some like food for thought. That, yeah. In the ISCA tutorial branch under example.
What's the different data? I'm on the other side. Okay, later.
Oh yeah, okay. So maybe after the demo, I can come down and show you. Yeah, thanks. And then after you configure your controller, refresh policy, row policy, address mapper, then you put your controller in your memory system to encapsulate them. This is also where you can have multi-channel. If you want to have multi-channel simulation, you just use Python list comprehension to have a list of controllers. And then you just run a simulation, and you get your stats as a native Python dictionary. So if you want to, let's say, analyze plot, this is super straightforward. Okay, now let's move on to the next example. So here we will use the latency throughput test and demonstrate how different configurations or parameters of the memory system will affect the performance of DRAM. So you first execute this setup cell. Then in the next cell, we investigate how different number of banks affect latency and throughput of the DDR5-based memory system. So the configurations that we pick by default has 32 banks. And we also create variants where we have 16 and 8 banks. And then we run the simulation using the existing code that will plot the latency throughput plots. And here's our result. So as we see, if we have 32 banks, then we have the lowest latency and the highest throughput. As we reduce the number of banks, because we have less bank level parallelism, more requests are being queued as a memory controller, you will see overall higher latency. And in the case of 8 banks, you may not even be able to saturate the full throughput of your memory system. Next, we will show the effect of memory controller queue depths on memory system performance. So here we sweep queue depths from 1 to 64. Then we plot all these results. Maybe zoom, reset zoom. So here we see that if we have a really small memory controller queue depths, you don't have enough in-flight requests to schedule to fully utilize all the bank level parallelism, so you cannot achieve the full throughput of your DDR5 memory system. As you keep increasing the queue depth, you have more queues that can be parallelly issued to different bank groups, different banks. Then you start to see we can utilize more and more throughput, and up until a point where keep increasing the queue depth doesn't keep increasing throughput, but increases the tail latency. That's because once you have fully utilized all the available bank groups banks, the other requests just have to wait in the controller, which causes the increased latency. Yeah, so that summarizes the hands-on part of the Ramulator 2.1 tutorial, and I'm happy to take any questions or help you debug any issues that you may encounter. Really? Is it not under ISCA tutorial? Let me just quickly check. Oh shit, okay. Maybe I would just like upload it right now. So I remembered I dragged the. Oh, on my side it's still okay. It's weird because on my side this should be, let me push. Is it there now? Okay, so maybe I would just put the notebook in a file, like some like empirical file sharing service. Is it updated? Because on my code space, it 6 hours ago.
This is the public feedback.
Yeah. Yes. Okay, I think something is 6 hours ago. Okay, I think like I would just upload this notebook to an empirical file sharing service, and we can just scan a QR code to download it. Yeah, I'm sorry. So. Yeah, and also like if you just download this and drag it into your code space, you don't have to let's say, reopen a new code space. So I will share this. Can I zoom in, or I will share part of the screen. So portion of screen. I hope this is big enough, or even bigger. Yes. Or yeah, I'm sorry about. I have zero idea why like it says update 6 hours ago. Yeah. Yeah, just like drag it in and it should work. Great. Yeah. Why does it say 6 hours ago? I have zero idea. 6 hours. Yeah. and like if you encounter any issue with the code space, etc., please also let us know. We will improve, let's say, the code space dev container configurations.
Yeah. You can put any other example. This is the last one. Sure. Anyway, next question. I have one more question.
Only a couple of people working. Okay.
Yeah. Yes, or I can stay close. That's what.
Yeah, you can talk about examples, but not finance something. Even that is something that
Okay, I think it's good that people are interested in doing hands-on work, but it's been a long day. And you can continue doing it, by the way, but we should probably close the workshop so that for tutorial, so that people prepare for tomorrow's tutorials. So it's been a good day, I think. If you have any feedback about the tutorial workshop, what we should cover next, please let us know. It's great to see two of the DRAM manufacturers represented. We have the good guys from Micron. Yeah, that's how we should talk about. And the rich guys, apparently, yes.
we don't bite, we promise.
Say it again?
We don't bite.
Oh, okay, you don't bite. Definitely, yes, yes. Definitely don't bite. Yeah. Any remarks anybody wants to make before we close? Anything we should consider for the next iteration? I know we had some hiccups in the DRAM Bender setup, but hopefully we'll fix that for the next time. Okay, that sounds good. So basically we'll have a better tutorial session next time. The basal, yes. Yeah, that may be good actually. But if you have any questions, you can always, now you know the people and you can reach out to them. We're always very interested in helping the community. I think there's a lot of opportunity in these areas that we've discussed, as we've discussed. So if you want to contribute, we welcome all contributions from academia, industry, anyone, independents. And if you have any questions, you're certainly welcome to ask them on GitHub. And just to remind, it's best for people to switch to Ramulator 2.1 so that it can consolidate efforts more and more. And you can see that there's a community growing around it based on Prashant and Jim Huang's thoughts. And we have featured talks from other people who use these infrastructures. It's good to make it stronger by consolidating a little bit more going forward. So thanks for attending. It's good to see so many people. There were many more people, of course, but you're the stragglers toward the end. Hopefully we'll see you next time at another workshop. And if you're one comment that I'll make is, if you're interested in presenting some work related to these infrastructures, we're always very open to including new people. We know only so much, we can reach out to only so much, we can do the calls for presentations and then get people who actually submit. But you can also reach out to us, basically, because we don't know exactly who's doing what. At the ICS, for example, there will be folks from national labs presenting their work on integrating Ramulator into their simulation infrastructure. So we're looking forward to that. They couldn't be here this time, but so if you're interested in contributing, we welcome those contributions also. Okay, thank you, and have a great rest of the conference. Tomorrow we'll have two workshops. I'll pitch that also. Memory-centric computing systems, which has a lot of synergy with this, and DRAM sec, which also has a lot of synergy with this particular workshop. And unfortunately, if you attended this one, you missed the DRAM bus tutorial on DRAM, which I heard went well. Okay, thank you very much. I'll see you hopefully tomorrow.